Hi everyone and welcome back to PrepFusion. So few of you guys were demanding that I should provide the performance of transmission line as well on YouTube. So on popular demand, this marathon will cover completely the performance of transmission line. Also, now let me know if you want few important topics from parameter of transmission line, because mostly it is theoretical, few things are theoretical there, but how to solve the questions, what are the tricks involved. If you want those short videos, you can let me know in the comments below. I can provide that video. This will cover comprehensively the performance of transmission line, and with this all the marathons, I think we have covered almost roughly around 45 to 55% on YouTube. Okay, so that should be more than enough, like, for the YouTube guys. Also, if you want to avail the course, get access to the course completely for free for 30 days, this offer will be valid only for the next day. Okay, this offer will not be valid after that. So there are two links provided in the comments below. In the first link, it's a free trial, so it's a free trial of 30 days. The trial will be accessible to you for 30 days only. In that, complete course content will be available to you of power system. You can watch it as many times as you want. Okay, so try to finish it within the 30 days. You can download the notes as well. All the notes are downloadable. Now if you don't want to have any headaches and stuff, if you just want the course till validity till get 2026, then you can go to the second link, that is a comprehensive course. There, if you apply the code POWER, you will get the course at the lowest possible price, that is 669. Okay, that is the lowest price. This is nothing, right? This price is nothing. And here also the course price will come out to be 1 rupee, but if you apply the code, sorry, not free, sorry, you have to apply the code power. You have to apply the code power. If you apply the code power, then the course price will become free. It will completely be free. You don't have to pay any single rupee except for creating an account on our website. Nothing other than that. Okay, so if you apply the code power, the course price will be totally free. This will be a free trial for 30 days. In these 30 days, you can finish the whole course. You can download the notes. You can watch it as many times as you want. Whatever you want to do, you can do it. Okay, and if you want to buy the course, if you want to buy the comprehensive course, you can buy from the second link in the comments below. So that was it basically from my end. Now let's start with performance of transmission lines. Hi everyone and welcome back to PrepFusion. I am Anish, and today we will start with the second part of power system analysis. So we have completed PSA 2, where we have completed the fault part, fault analysis, and the power system stability part. Both of those have been covered comprehensively. Like in the PSA 2, there is one more chapter, that is load flow analysis, but that we will study after we complete the PSA 1. Okay, there is a reason why I am following this sequence, because we are trying to cover the important topics first, and I want you to get an idea how to understand the subject even better. Because sometimes what happens, why didn't we start it with PSA 1? Because PSA 1 is bit of boring. There are a lot of derivations, there are a lot of formulas. PSA 2 does not have much formulas, right? It's concept and concept. So that's why we started with PSA 2. But if someone is starting from PSA 1 and they want to start from PSA 1, right, if it's in your semester, then of course you can start with PSA 1, no problem with that at all. But I will recommend everyone to follow the sequence as I have in the course. Okay, so yeah, let's start with basically the PSA 1. What is PSA 1? PSA 1, we will discuss mainly about the transmission line parameters, right? In PSA 2, I did not discuss how are the transmission line, the resistance, how is it calculated, the impedance Rx, the reactance of the line, the capacitance of the line, all those things we have not discussed. So in PSA 1 we'll discuss all those things. We'll discuss about power factor improvement, we'll discuss about load side, about source side, we'll discuss about the distribution distributors. Also we'll discuss about different kind of things. What happens when my transmission line is very long transmission line? What happens to the voltage waveform? Will there will be some wave kind of phenomena? Okay, so all those analysis we will do. So in today's lecture we will not discuss about these things. I will talk about these things, but today will be basics. So the first lecture will be basics, then in the next lecture onwards we will discuss about short transmission line. Okay, so a few basic things I know you already know, but we will quickly revise those things. That regarding the power, types of power in AC system. So we have two kinds of power. One is active power, another one is reactive power. So active power is measured in watts and reactive power is measured in volt ampere reactive, right? So what does active power do? Active power is a real power, the power that you actually have to carry weights and stuff, right? That is the active power that performs the actual work, like rotating a fan and lighting a bulb. Okay, and what is the reactive power? Reactive power is actually not directly used to perform the work, it is indirectly used. So reactive power is just like, if you remember, we have a fan, right? And the fan rotates. So rotational power is active power. But to rotate the fan, we need magnetic field. So to generate the magnetic field, actually it is not directly rotating the fan, but it is useful, right, to rotate the fan. So directly we are not like that, directly this magnetic field is not helping, but indirectly it is helping. That's why it is called reactive power. Okay, so yeah, one more thing, what does your active power depend on? So your active power mostly depends on the angle difference. I will show it to you as well, and we know already. So if I have two voltage sources and I have inductive link, this we have discussed in the PSA 1 as well, that the whatever is a delta, whatever is a delta here, right? If delta, your active power is a function of the power angle delta. Okay, and your reactive power will be a function of what? Your reactive power will be a function of voltage. Why? Because what actually is the main thing about reactive power? Reactive power is the generation of flux. Generation of flux, right? Phi. Okay, reactive power is the generation of flux, phi. So what is flux dependent on? For transformers, you know, it is 4.44 n phi. So basically I can say that my flux, right, is a function of voltage. Like we define like our voltage is a function of flux. Otherwise also I can write that if I have voltage, flux will be generated, right? So I can say flux is a function of voltage, correct? Or I can say that my reactive power R is a function of voltage. So this also we have proven in the formula as well, right? Previously, if you remember. So if I want more reactive power, there needs to be more voltage difference, that is delta V. I will show it to you using formula later on. Okay, just giving you intuition for now. So the same thing is written over here, that my EMF is this, so my reactive power will be proportional to the voltage. Okay, let's see, let's take few cases and try to understand this fact about active and reactive power even better. What is the reactive power and active power if the voltages are like this, if there is an angle difference, if there is a voltage difference, right? So let's take for the first case. Okay, for the first case, what is the active and reactive power? So we will not use any formula, we will do basics. So I will directly write the formula of complex power. Okay, what is the formula for complex power? I'm taking it for the case A. Taking it for the case A. So for the case A, I think it comes out to be yeah. For the case A, what is the apparent power formula? It is VA into IA conjugate, right? VA into IA conjugate, that is how much power is this delivering, how much apparent power is this delivering, generator G1, right? I want to measure that. It will be VA into IA. VA I know, that is 1 angle 30, but IA I don't know. What will be IA? So IA will be what? IA will be simply this voltage minus this voltage divided by the impedance between it, right? Very simple. So 1 angle 30 minus 10 angle 0 degree. Divided by impedance between it. Okay, now I have to do the conjugate of this, right? IA conjugate. So what will be IA conjugate? IA conjugate will be this 30 minus j angle 30 whole conjugate divided by conjugate. Okay, remember all this I have taught, like how to do the conjugate and stuff. So I'm directly doing the things here right now. So this will come out to be, right, this will come out to be 1 angle minus 30 minus 10 angle 0, and this will become minus of j, and this will go at the top, so this will become plus of j. This will become plus j, right? So if I multiply now this number j a plus j into, like I will just copy this, we're not getting enough space. So this will be, this plus 30 and minus 30 will become 0, plus j will be still here. This will be 1 angle 0 minus 10 angle, okay, maybe this numbers we have taken a bit wrong. This will become 10 angle plus 30, right? J is there, cos 30 is off. I have taken the number bit on the higher side. It cannot be that high, okay? That's my bad. We cannot take the number that high. We can take it like, can we take 2? Or still we can take it, I guess. Okay, let me check. Okay. So this will be right. This will be j minus 10 angle 120. Okay. So what is cos of 120? Cos of 120 is, I think, something negative. Yes. Into 10, this becomes 5. So this actually becomes 5 plus 5, and sine of 120 will be again positive into 10. This is negative plus 1. So this is minus j 7.66. So what it says to me? It says to me that my generator is delivering active power, because active power is positive. So generator is delivering active power, right? And generator is delivering reactive power. When reactive power is negative, right, Q is negative, that means what? It is delivering lagging reactive power. It is delivering lagging reactive power. All these I have taught in the PSA 2, right? That's why I have told you to follow the sequence. So it is delivering the lagging reactive power, and in machines as well I have taught this very well. Okay. So what does P positive means? P positive means that generator is delivering reactive power, right? Generator, P positive basically means generator, like P positive basically means active power flows. Like if let's say this point is 1, right, this is 1 and this point is 2, active power flows from 1 to 2, right? What about reactive power? So positive reactive power, if you remember, if reactive power was positive, that basically meant that the generator delivers lagging reactive power. Lagging reactive power. But here Q is negative. That means what? That means either you can say that generator is delivering leading reactive power, or you can say generator is receiving lagging reactive power. That means reactive power is flowing from B to A. So Q lagging reactive power not B to A, sorry, 2 to 1, right? Lagging reactive power flows from 2 to 1. So let's take few more examples. Okay, let me take the question B, where this time the voltage is lower side and the angle is also lower, right? Now what happens to the active and reactive power? Let's see that. So same thing I will do. Okay, first of all I will calculate the IB, right? IB will be what? Or IB conjugate I will write directly now. So IB conjugate will be divided by J whole conjugate. Okay, so this will be 1 minus 30 minus 0.5 divided by into J, basically into J, right? So my power, apparent power, this will be voltage is 1 angle 30, right? And this will be there IB conjugate. So this will be okay, this will become J into 1 minus 0.5 angle 30 degrees. So this becomes J minus 0.5 angle 120 degrees. Okay, so now this will be okay, cos of 120 into 0.5, and again there is a negative sign, so this one becomes plus. So active power is still plus only, but it has become lower, but it is still plus only. What about the reactive power side? So reactive power 0.5 into sine of 120, right? So this becomes minus 0.433 and I have plus j, right? So this is becomes positive now. So this becomes positive plus j 0.567. Okay, so here what I observe, P is positive and my Q is positive. Okay, P is positive and my Q is positive. So if P is positive and Q is positive, right, that basically means that active power flows from 1 to 2 and your reactive power also flows from 1 to 2, that is lagging reactive power. So active power we know, lagging reactive power flows from 1 to 2. Okay, now let's check for the option for the final case, for the third case, right? For the third case, if I copy and paste again, I will do the same thing, same analysis, everything will be same, but this time if you see the voltages are equal. What will happen if the voltages are equal? So like all this, right, is only for purely inductive link, right? If the link changes, then all the conclusions will change. Okay, I will explain that as well. If the link changes, conclusions also will change. Okay, we will see that. So yeah, I think where is it? this, yeah, that I will show, but I think we should have actually changed this angle as well. I will try to change this angle because otherwise I will not be able to show you this, right? Let me change this again to -30, right? Because I want to show you something, that when does my active power becomes negative. That conclusion is also very, very important, right? So let me change it to -30. Okay. So okay, now again the same procedure. Let me first of all calculate the IC. Okay, so IC will be equals to V. So IC conjugate will be equals to this, right? 1 minus 30 minus 1 angle 0 divided by J whole conjugate. So this will be plus J 1 angle plus 30 minus of 1 angle 0. Okay, so yeah, now your apparent power will be, this will be 1 angle minus 30, this will be J. Okay, this I will copy directly. This becomes J into 1 minus 1 angle minus 30. So this becomes 1 angle 90, or simply J minus 1 angle 60. Okay, although the reactive power here will not be 0 actually, but in certain conditions it can be 0, but here it is not exactly 0. If I find out the active power, what is active power? Active power this time, if you observe, it is negative. So cos of 60 is negative minus 0.5, so active power comes out to be negative. That means it is receiving active power now, it is not delivering active power. And what about the reactive power? So reactive power, if you see, it is almost near about 0, right? So Q reduces, so it goes to 0. So if your delta V reduces, then your Q also will reduce. That is what we can observe from here, right? Delta V is what? 1. It is not exact actually, because there is phase angle. We have done some approximations, but if delta V is reducing, Q also will reduce. That much I can intuitively say. Okay, and if your angle is lower, so if power will always flow from higher angle to lower angle. This I have taught in my PSA 2. So power will flow from this to this direction, but I am measuring the power here. That's why the power is becoming negative. So power P is negative, right? P is negative. So the conclusion is power will flow from higher angle to lower angle, that is 2 to 1. So this is 2 and this is 1. So 2 to 1, and your reactive power, right? Reactive power Q reduces if your delta V reduces. Now what is the conclusion? The conclusion is very simple. Conclusion, I have wrote down the conclusion. Active power will flow from higher phase angle to lower phase angle. Reactive power flows from higher voltage to lower voltage, right? Or I can say reactive power is a strong function of the voltage difference. reactive power is a strong function of the voltage difference. Generally, if you see in the first case, which one was the higher voltage? This, right? So that's why if you see, lagging reactive power flows from 2 to here if you see it is negative. If it is negative, that means lagging reactive power will flow from 2 to 1, not from 1 to 2, right? Here the voltage was highest, right, in the 1. So that's why lagging reactive power flowed from 1 to 2, right? And here they are equal, although here also lagging reactive power is flowing from 2 to 1 only, sorry, 1 to 2 only, but it is very low because the voltage difference has been reduced. Okay, but all these conclusions are valid only for a inductive load, inductive link. Please keep this in mind. Whatever we have discussed is only valid for inductive link. Okay, for capacitive link, what will happen? Just the dual. Just the dual. I prove it to you. Okay. Now I don't want to prove it to you. Okay, because I have other things to do as well. Like I mean, I have to teach other things as well. So this one is the homework for you. You do the same whatever I have done. Try to come to the conclusions, and you will get to the same conclusions. Are these conclusions for a capacitive load? Will be dual. Power will flow from lower angle to higher angle. It will just be dual. It will just be the opposite. And your Q flows from lower voltage to higher voltage. This will be homework. I will do it in the notes, but this will be a homework for you. Please do it. Please repeat the same exercise, whatever I have done. Okay. If voltage magnitudes are different, if voltage magnitudes are equal, and the connection is inductive, then active power will flow from higher angle to lower angle, but reactive power flows from both end. Okay, so how is that possible? So that I will show you in some other case, because if you see here, so here if you see, the reactive power is coming out to be positive. Okay, let me calculate the reactive power here as well. Basically, because your line, right, your line will not be just a simple inductive link, right? Your line will not be just a simple inductive link, right? What will happen is, if voltage at both the ends is same, most of the cases what happens is we have capacitances as well parallel. Yes, there will be inductive link, but in parallel there will be capacitances. There will be capacitances. So what will happen is, if the voltage difference if the voltage magnitudes are at the both end is same, what will happen? This will also deliver reactive power, and this will also deliver reactive power. Both will deliver reactive power. If this was lower voltage, then only this generator G1 would have delivered reactive power. But if both the voltages are same, then both will deliver reactive power. Okay, not a single machine. So that was the case of your capacitive link and inductive link. Let's now move on to the next topic, that is regarding line losses. So you know one thing, that losses are mainly resistance dependent, right? Resistance, like we know there is I square R loss, right? So in this kind of losses, I square R loss, what do I want? I want my losses to be minimized. So if I want my losses to be minimized, that means my R has to be reduced. But there are few other kinds of losses as well. If you remember, in transformers, there was a loss named as eddy current loss. And if you remember how I used to model my transformer, right? RE, this was the core resistance, right? Eddy current loss was dependent on the core resistance. So this core resistance, actually, what is the loss in this? So here, what do I know? Do I know the current? No, I directly cannot comment about the current, but I definitely know the voltage across it. I definitely know the voltage across it. So the losses in this case is V square by R, right? So here, what do I want? Do I want my resistance to be higher or lower? In this case, I want my resistance to be on the higher side so that the losses, overall losses reduces, right? So here what I can say is, what I can say is my so in case of, that's why we provide laminations, right? That's why we provide laminations, right? Why do I provide laminations? To increase the resistance, further. That's why we provide laminations, right? Okay, to increase the resistance further, that's why we provide laminations. So because here the loss is voltage dependent, so there are two kinds of losses here. In a winding, I know the current is fixed because current is delivered, right? Current is fixed because current is the measurement that I understand from the load, right? Basically, the load takes some rated current, so that's why current is fixed. If current is fixed, then the loss will be I square R. Okay, that is the series circuit loss, current constant. And if the voltage is fixed, then the loss will be V square by R. Then we want the resistance to be higher. If it is a current dependent loss, then we want the resistance to be lower, right? So these things you should understand, because this is a very, very important point that can be used, and that will be used in any case in the second, like whenever we will derive the losses and stuff, right? So what are the applications of reactive power? What are different kind of applications of reactive power? So first kind of application of reactive power is to reduce the line current. How can I reduce the line current? So let's assume that I'm providing some 10 volt, right, uh, to this load, and let me assume, like I'm just taking a very simplified example. Of course you will say, how is your load purely reactive, right? It has to be some resistive part, but I am just simplifying the example, right? You can take a resistive load, you can follow along, you will see, you will get the same result, right? So in this kind of cases, right, what happens is, what is the current here? IL, magnitude of current. Magnitude of current is 10 divided by magnitude of J, that is 10 ampere. 10 ampere. Okay, that is what my magnitude of IL is. How much reactive power is it delivering? The whole power is reactive power only. This will be V into I, and I is totally lagging basically. What is the I? Not in magnitude, but in exact value. If I want to calculate the I in exact value, it will be minus of J10. Correct. Now, what is the power? What is the reactive power? Because there is no real component. So reactive power will be what? V into I conjugate, V into I sine theta. So angle between them is 90. So it will be 100 VAR. Right? This is the reactive power that it is delivering. Right? V I sine theta. Okay. Because current is lagging, so it will be a lagging reactive power, positive reactive power. Now, what if I change this circuit, right? Now, what if I design a additional load that will deliver 50 VAR? 50 VAR. Will the current reduce? Because of course, in reality, what will happen? There will be some resistance here, right? And due to that, there will be some I square R loss. Correct? So I cannot change the resistance here because it's transmission line. How can I reduce the resistance, right? It will be fixed. I have to reduce the load current. So what I can do, I can connect a reactive power compensator in the across the load, so that it delivers the additional reactive power. Okay, so this is 100 VAR. Now my QL changes to 50 VAR because QC, the compensator, delivers 50 VAR, right? So now what will be my IL? IL will be, again, it will be QC by V sine theta. Again, your load, if you see, it is purely real. So sine theta will be 190 degree. So I'm just doing rough calculations. You can do the exact calculations. So it will come out to be, sorry, QL, whatever is the like generator delivering. So it will be 50 by V sine theta, that is 10. So it becomes 5 ampere. So your current reduces by half. Previously, the magnitude of current was 10 amperes. Now current reduces by half. So your IL square, like your power will be what? As your magnitude of IL reduces by half, right? Your power will be, power loss will become 1 by 4. Okay, power loss will become 1 by 4. So that is the case over here. Okay, so yeah, so that is one use case. So we will obviously use this, don't worry, in questions we will use this. I'm just giving you an overview. Okay, one more thing is to improve power factor. Of course, if my generator is delivering, right, let's say 10 watt of active power and 10 VAR of reactive power, if I somehow, because what is my cos theta? Cos theta will be P upon S, right? If I somehow deliver some reactive power across the load, so I will reduce my reactive power, because additional, that of course load reactive power demand is fixed. It will take the same amount of reactive power only, right? It will take the same amount of reactive power. Load reactive power is fixed. So if load reactive power is fixed, right, this is P, this is Q. If load reactive power is fixed, because of course I will not say, like, you are in your home and I will not come from the, like, let's say your electricity supplier will not come to you and tell you to turn off the fan because there is too much reactive power. Your electric supplier cannot order you that, right? Your load will be fixed. Whatever load you are using, fan, TV, AC, whatever loads you are using, that will be fixed, right? So your Q is fixed. But what I can do, that I can break this Q into two parts. One will be QG, another one will be the additional QC that will be sent from a reactive power compensator. Okay, we will see this. So if I break it down, so overall the reactive power sent from the generator reduces. If the reactive power sent from the generator reduces, so your SG magnitude will reduce. If SG magnitude reduces and your active power demand does not change. Okay, so what will happen? Your cos theta, like your P by S, right? S is reducing, so your cos theta will simply increase. Okay, magnitude of cos theta S will simply increase, right? So yeah, that is the case over here. Magnitude of cos theta S will simply increase, so your power factor will simply improve. Okay, we will take few examples from there also, you can understand. Like, this is your power triangle, and out of this the real part will be P, the imaginary part will be Q, and this will be your apparent part. Okay, and of course we know few formulas. This is my phi, right? So your cos phi will be P by magnitude of S. Your tan phi will be Q by P. Okay, this will be used multiple times. How much reactive power we need to do? We will take few examples. We'll see from that. Don't worry. Okay. So why do I want to improve my power factor? If the power factor is improved, in turn it reduces the line current. How? So what is my power? Because active power is fixed, right? Active power is fixed. If active power is fixed, it is VI cos phi, right? It is VI cos phi. So I know active power is fixed. So what is my current dependent on? Current is dependent on P divided by V cos phi, right? So if your active power is fixed and your cos phi improves, that is it increases, so in turn your current will reduce, and if your current reduces, in turn your line losses will simply reduce. other way around, or what you can see directly from here, I can see that I'm reducing my reactive power. If I'm reducing my reactive power, your apparent power reduces, and what is your apparent power equals to? It is magnitude of V, magnitude of I, right? Your magnitude of V will not change, so magnitude of I will be Sg divided by magnitude of V, correct? So your magnitude of V is constant, your Sg reduces. If your Sg reduces, then your I also will reduce. Magnitude of I also will reduce. Same conclusion. Okay, nothing different. Same conclusion. Okay. So if we are able to supply some reactive power, right, the power factor improves. Like they are doing the same thing only. They're saying the same thing only. Like that is the purpose of reactive power. Reactive power has many applications. Of course, it has applications of generating magnetic field, but in power system as well, it has applications. So now let's discuss a bit about transmission lines. We will not discuss about the transmission lines today. I mean the parameters of transmission line in this chapter. In the next chapter, we will discuss about that. What do I mean by transmission line? So if you see this, right, near your home or somewhere in the road, you will see these kind of towers are there. On these towers, there are multiple wires. These are what? These are the wires through which the electric power is transferred from the generating station to the load station. Now, of course, this is a wire. So wire will have a resistor. That is simple, right? Wire will have its own resistance. Now, what happens? This wire, as some current is flowing, right, from generating station to load station, the current is very high. If the current is very high, there will be some magnetic field, because if you see, so let me first discuss. There will be some magnetic field, because I know that my magnetic flux phi is proportional to I. I will prove it to you as well. Like I will show you, because we have done this in magnetic circuits as well, right? Flux is proportional to current. So higher the current, higher will be flux. Due to flux, there will be some inductance, because flux is related with inductance, right? N phi L di L N d phi by dt is equals to L di by dt, right? Okay, so that is sorted. So line will have a inductance. Now, as this line is just above the ground, right? This transmission line is just above the ground, and this is a high voltage line. This is a high voltage line. So there is some potential difference across the ground. So this is ground, right? This is 0 volt, and this is 30 kilovolt, 30 or higher kilovolt. So if there is some potential difference, what will happen? I know, due to the dielectric stress, right, the air will also behave as a capacitance, although the capacitance value will be very low, right, but air also will behave as a capacitance. Why? If the voltage is very high, let's say the dielectric strength of air is 30 kilovolt per centimeter, that is the electric field dielectric strength of air, right? So if the voltage increases beyond this, right, there can be some current flowing through the air, right? So due to this, two things will happen. First is your capacitor, there will be some capacitance. Due to this, some charging current will flow, and there will be some conductance, because the air has breakdown has occurred across the air. So there will be some conductance, due to which the current will directly flow to ground through air, right? Although this, right, these are not that high voltage, but if the voltage is very high, like we do some protective measures, so that like it's not like that some current will flow like this. Okay, so we have some protective measures. Okay, it's not that simple that current will directly flow, but still it will have a conductance. The value of the current will be very low, but it will have some conductance. So that is what they have discussed over here. Transmission lines are evaluated on how they manage and propagate voltage, current, and power. So basically these lines, right, are used to transfer the power, both the active and reactive power. Now there are many classifications. There are many classifications which I will show you in this lecture only. Depending on the classification, the transmission line will behave differently, because I have told you the dielectric strength of air is 30 kilovolt per centimeter. So if the voltage is on the lower side, then there is no conductance, there is no capacitance. If the voltage is on the lower side, if the length is on the lower side, if the length is on the higher side, there will be some conductance, there will be some capacitance. So we will discuss about all those things. So what are the desirable properties of a transmission line? So whatever power I am sending from the generating station, I want maximum of it to be received at the load, right? I don't want it to get lost in the transmission lines. That is the purpose, right? So that's why the first priority is to minimize the power losses. Okay, and I know through the transmission lines current flows, right? I flows. Voltage is not fixed. Through a single line, voltage is not fixed, right? Current is fixed. So I want to minimize the current. Why? Because I want to minimize the losses. How will I minimize the losses? I equals to S root 3 if it's a three phase line, root 3 into V L cos phi. Now there are two ways to minimize the losses. One is to increase the power factor, another one is to increase the VL. Okay, one is to increase the power factor, another one is to increase the VL, right? So if I increase the voltage, line voltage, then also the current will be reduced, because ultimately your power is what? Power is voltage times current. Power, active power has to be constant, but your, sorry, this will be P, right? Obvious. Yeah. So your active power is constant, but if I increase my voltage, then also the current will reduce, so it will reduce the I square R loss. But I cannot increase my voltage very high, because you see there are parameters that will come into effect. Like current will flow from the lines, transmission lines to the ground. So that is also we have to take care of. Okay. So we will operate within the safe limits. And of course, by improving the power factor, how can I improve the power factor? I have already shown to you. By connecting a uh, by connecting a reactive power compensator on the load side. It will deliver the extra reactive power so that the voltage is improved. Again, I've told you, right, reactive power is a function of voltage, delta V. So if the reactive power reduces, right, if the reactive power that the generator deliver reduces, what will happen? Then this delta V will reduce. Basically the difference between the voltage at the sending end and the receiving end. If the reactive power reduces, right? So whatever voltage I have here, the same voltage will appear across the load as well. That is what I want, right? That is the second parameter. That's why I have told you, that's why I had to teach you that reactive power depends on the difference of the voltage if it's a inductive link. So if the difference reduces, if the reactive power reduces that the generator is sending, then the delta V also will go down. So there will be very less amount of drop in the line, transmission line. Because let's say I am providing here 11 kilovolt at the generating station, of course, or like we do some step up, step down, but ultimately after step down at 11 kilovolt I am supposed to get 400 volt at the load side. But due to there is some transformers, step down, step up transformers, right? So those are in between. I am not explaining that. So you might have a doubt. So I'm providing 11 kilovolt, how am I getting 400 volt? So 11 kilovolt is at the generating station, 400 volt is at the load station. There are some transformers in between, step up, step down. Okay. So if what happens if the 11 kilovolt here is increased? So what happens at 11 kilovolt? I'm expecting 400 volt, but as soon as I load, right? As soon as I load at the loading station, what will happen? That voltage drops to 390 volt. That is not desirable. My load is not rated to operate at 390 volts. My load is operated to rated at 400 volts. Okay. So yeah, that is the thing here. That is the thing over here. So you have to understand that. So that's why will there be voltage drop? Because let's say the load demand has very high reactive power, 100 kVAr. So if the reactive power demand is high, then the delta V also will be high. The difference voltage also will be high. If the difference voltage is high, then this voltage is fixed, and difference voltage will go up, right? It is V1 minus V2. So if this is fixed, right? So this has to reduce because delta V has to increase. So the load side voltage will reduce. Like individually also you can understand, or I have proven it to you as well, right? So that's why here, right, we have to add a reactive power compensator. So we will see that, and ultimately balance operation. Though three phase are physically separated on transmission towers, they are treated electrically as a balanced star configuration for analysis of load and operation. Okay, so actually three phase lines, they are just separated 3 wires, but we assume them to be connected in star for easier analysis. Okay, this is not any desirable characteristics, this is just a property, actually. just a property, not a desirable characteristics. Okay, this I think I have explained it later on as well. Okay, so for easier calculation, right, this is what we do now. Why not always use high voltage? Because like instead of doing all this, right, instead of reducing the power, instead of increasing the power factor, improving the power factor, why not always use the higher voltage? Let's understand why. Using extremely high voltage everywhere would make the system uneconomical, because as the voltage increases, the insulation required also increases, because I've told you the dielectric strength of air is 30 kilovolt. So we have to insulate the wire. It's not like I will just connect the bare wire. We have to provide some cover to it, right? Cover, so that current does not flow from the wire to the ground. That is expensive, right? So we cannot just increase the voltage very high, right? That's why we don't provide any like cover. The wires are bare. If you see here, you will see, observe here, the wires here are actually are bare meaning they have no cover with them, because that is very costly to us. I think that is the reason. Maybe we will provide some cheap cover, not very expensive one. Okay, and the system will become very bulky, and transformer designs also will become very bulky, because higher voltage, higher rating, the system will be bulky and costly, increased cost, and there will be safety risks, because of course I have told you the dielectric strength of air is 30 kilovolt. If there is a breakage in the dielectric strength, then current will flow from the line to the ground. Okay, that's it. So hence extra high voltage or ultra high voltage UHV is used only for long distance bulk power transmission, not in local or urban transmission. So this extra high voltage will be used in long power transmission. Okay, because in long power transmission the current will be actually very huge, because it is delivering heavy power. So in those kind of cases we generally use high voltage. Okay, so the same thing that I have discussed over here, that three-phase transmission line will be connected with star. We will assume they are connected in star, and then we can say that the rated voltage will be what? Voltage rating will be what? V line divided by root 3. That is for a star connection. Rated current will be same as the line current. I phase will be IL, and your MV rating will be root 3 VL IL for a three-phase system. So your current rating becomes S divided by root 3 into VL. Okay. So let's solve a very basic question, like whatever we have discussed, few basic questions on this concept, right? So when a fixed amount of power is to be transmitted, the efficiency of transmission line increases when, okay, when a fixed amount of power, so power is fixed, right? And they are asking me the efficiency of transformer. What is efficiency of transmission? So what is efficiency of transmission? So one more point I forgot to discuss, that efficiency of transmission, although I think I will discuss this later on as well. So transmission efficiency. Transmission efficiency is what? Transmission efficiency is the, like, simple formula for efficiency, P out upon P in. So P in will be the power sent from the generating station, and P out will be the load power, right? P out will be the load power, and P in will be the power sent from the generating station, right? Power from the generating station. Now what I can further write this, P load will be so P load is fixed. P load is fixed. Now what is your generating power? So your generator power will send, of course it will send the P load plus the line losses, right? Plus the line losses. What is your line losses? It is simply IL square R. Okay. but this is for a single phase, right? So single phase generator power will be this. For three phase, right, your P generator will be P load plus 3 times IL square into R. Why? Because it's a three phase, I have three lines, so there will be losses in all the three lines. So it's a three phase. This is a single phase, and this is a three phase. Okay. So here in this case, the load power was also single phase, but here the load power will be three phase. Okay, and most cases this formula will be used, right? Don't remember, mug up the formula, understand conceptually what I am telling. Okay, so most cases they will give you the three phase power only by default if nothing is mentioned. So you will use 3 IL square into R. So your efficiency comes out, P load is fixed, right? Three phase power divided by P load plus three IL square into R. Okay, into 100%. Okay, so that is the case over here. Okay, I have understood. So what are they telling now? They're telling me that the efficiency of transmission increases if the power is fixed, right? How can I increase the efficiency of the transmission? By reducing the resistance, right, or by reducing the line current. Then only this will increase, because your load power is fixed, P load is fixed. So there are two variables, either IL or R, right? How can I reduce the IL? The efficiency of the transmission line increases, right? Power is fixed. So what is my IL? IL will be power divided by VI cos V cos phi, right? Okay, root 3 into V cos phi if power is in three phase. If it's a single phase power, then you will just write V cos phi. If the power is three phase, then you will write root 3 V cos phi. Okay, so when a fix is to be transmitted, the efficiency of the transmission line increases when voltage decreases. If I reduce the voltage, the current will increase. If the current increases, the losses will be more, efficiency will decrease. So this is not correct. Voltage increases, power factor increases. Yes, if I increase both the voltage and the power factor, the efficiency will improve, right? So both voltage and power factor must be increased. So of course option B will be correct. This we have already discussed in the previous topics, right? Previous parts. So it's very simple, both voltage and power factor must improve. Okay, so now let's do a very basic derivation. So for a fixed value of complex power, okay, complex power is fixed, so these kind of questions will get asked in GATE, right? So basic question also will get asked. So it's not like I'm teaching you something and it will not get asked. Every single point is important. So complex power is fixed. What is complex power? Complex power is simply complex power flow in the transmission line is fixed. Okay, so it is simply sending end voltage into complex conjugate of the sending end current. Okay, so now they are asking me which is having a sending end voltage of V. So it is having a sending end voltage of V into IS conjugate. The real power loss will be proportional to what? The real power loss. So I know what is the magnitude of apparent power. Magnitude of apparent power will be V into magnitude of IS, right? And what is the power loss? Power loss is magnitude of IS whole square into R, right? Whatever is the line transmission line efficient, whatever is the transmission line resistance. So from here, what I can say, what is my IS, magnitude of IS proportional to? it is magnitude of S divided by magnitude of V. Okay. So now basically my magnitude of Is is inversely proportional to magnitude of V because your complex power is fixed according to the question. So here your power loss is proportional to magnitude of Is because of course resistance I cannot change, or it is proportional to 1 by magnitude of V square. Okay, so your power loss is inversely proportional to 1 by V square. So which is present in the option C. Okay, these kind of simple questions also can be asked. Now let's solve, not solve, let's discuss about the parameters. I briefly discussed about the parameters, about the inductance, about the resistance and capacitance. Now we will discuss just a little bit to give you a bit of intuition. So I know if I have a current carrying conductor, this you have studied in class 11th or 12th. If I have a current carrying conductor, it will develop a magnetic field around it, right? And what will be the value of the magnetic field? The value of the magnetic field, if you remember, it was B into mu naught mu r I divided by 2 pi, whatever is the distance here at this particular distance, right, dA. At this particular distance is D. So this is 2 pi D. Okay. So of course there is a magnetic field, and if I know what is flux, flux is basically B dot A. If I have some cross section area over here, the flux cutting through it will be B by A, right? So this will feel some inductance of the line. So wherever there is some flux, there will be some inductance, right? Although the value will be very low because it's just a straight line, there is no turns here, number of turns is very low. But as the current is very high, so still it will have some effect. Because what do I know about inductance? So inductance is what? So I know that my VL is equals to N d phi by dt, or it is L di by dt, right? And if I assume that my this there is no saturation because air, the medium is air, right? Air is the medium. So if air is the medium, there is no saturation, right? There will not be any saturation. So your BH curve will be a straight line. Why will it be a straight line? Because air is the medium. Of course, the magnetic field will be very low because the slope will be very low. Okay, but still it will be a straight line. If it is straight line, I can directly convert this, right? This will be N into, let's say I'm starting from here, phi minus 0, right? Final minus initial, phi minus 0 divided by any time t will be equals to L I minus 0, right? So basically from here I can get the value of L, right, divided by any time t. This will be N phi by L. Like this is just a rough derivation. I'm not doing the proper derivation over here. But what is the difference between a normal wire, normal coil and a straight wire? So if I have a coil, right, because your flux, overall flux is N into phi. If I have n number of turns, overall flux will become N into phi, right? Or overall, like overall H will be N into I, right? Okay. Current enclosed will be N into I. I'm not deriving it. EMFT, you will see all this. Okay. So here your flux also will be higher. So your inductance also will be higher. But here it's a straight line. So your current enclosed is only I. So your flux is lower. So your inductance also will be lower. Although value will be very low, but still, as the current is there, still there will be some inductance. Okay. Intuitively, I'm explaining you all this. Okay. So in a straight wire, the inductance is relatively low. In a wound wire, that is like coil, the inductance will be higher. But here the straight wire has very high current. If it has very high current, then there will be the inductance will be actually, you cannot neglect the inductance, it will be considerable. You cannot neglect the inductance, it will be considerable. Okay. So now let's discuss about capacitance. So I know that our transmission line is here. Okay, this is my transmission line and this is my tower, Where is the picture? So this is my tower, this is my transmission line, right? Between, if you see, if you observe here, between tower and transmission line, these, right, these are basically insulators, or sometimes they are supports or insulator. So this tower is just there for mechanical support. So this tower is there for mechanical support. Tower, mechanical support. So previously, if I told you that capacitance is going into the ground, there will be a ground capacitance as well. But mainly we discuss about the capacitance from the conductor to the support. Because support is what? Support is a metal plate. It's metal, right? Metal. Tower is made of metal, right? Your conductor is also made of metal, correct? So if I have two metal plates and there is huge potential difference between them, then what will happen? What will happen? There will be some capacitance, right? So there will be some capacitance, and that is what we discuss. In the next chapter, we'll discuss the derivation of this capacitance, right? So capacitance comes due to insulators. Capacitor comes due to insulators. Okay. So due to this, there will be some, like I can draw the equivalent diagram of the insulators as a capacitor. Okay. And there will be some capacitance here as well between the directly between the tower and the insulator and between this line. Okay. So I'm just telling you intuitively how that circuit diagram will look. So due to this, there will be high amount of charge storage, right? And of course, there will be some capacitance, and due to this, there will be some leakage current. Whatever current flows through the capacitance is called as the leakage current, right? Leakage current. Leakage current. Why? Because my main purpose was to, there should not be any current flow between the conductor and the tower. But I have a metal support, two metal plates, and there is huge potential. There will be some displacement current due to capacitance, but that the purpose was to avoid this by using insulators. But still there will be some, whatever you do, there will be very small amount of leakage current that can be modeled with the help of capacitors. And this is very significant in medium and long lines. Why? Because here the voltage will be higher. If the voltage increases, then this is actually significant. Okay. So I hope that is clear. Resistance is very simple. I have a wire. If I have a simple wire, then of course it will have a resistance of the wire. That's why it is a series resistance. The loss will be I square R, and this will be present for all kind of lines: short, long, medium transmission lines. Conductance, again, this represents the leakage current through the insulating medium. Okay, kind of same only like the insulator, but this happens mostly at extra high voltages. At extra high voltage line, what happens then? Like here, right, the current for the capacitor, the current flows through the air, okay, through the two metal plates. But in case of conductance, the current will flow through the insulators directly. Current will flow through the insulators directly. Okay, so that is the difference. Current will flow through the insulating medium, and here current will flow through the air, not through the insulating medium. It will flow through the air. That's why it is called as leakage current. This is also called as leakage current, but remember here current is flowing through the insulating medium, basically through these insulators. Okay. So yeah, these things will be there. That is conductance. Conductance is generally modeled PAL. It is written in G. What is its unit? Its unit is ohm inverse or Siemens per meter. Okay. So yeah, this is the electrical model. Basically, I will have R, L, C and G. Okay, and I will have series resistance. Like this is the series resistance, series inductance due to the magnetic field. Series capacitance between the conductors, between, like, there is this between the conductor and the metal plate, and there will be two conductors. If you see, there are two conductors, right? Where did it go? Yeah, there are two conductors here. So between these two conductors also there will be some capacitance. Okay, so that's why the capacitance is modeled. If the voltage is high, then only this will come, and there will be some shunt leakage conductance that will be flowing through the insulation. Okay, so this is the model of transmission line. Now important fact is this is the model of a long transmission line. What do you do? This is a distributed circuit, because at each point there will be some resistance, small inductance, small conductance, small capacitance, right? At each point. But for a short transmission line, what we can do? We can totally add all the effects of the resistance. We can add all the effects of the resistance. So your overall, this will become R, right? And overall reactance will become a simple L. So this becomes, for a short transmission line, this becomes a lumped circuit. Why lumped? Why lumped? And why this is distributed? Because I am just representing the small resistance, small inductance at each point, right? Here I am lumping all of the small resistance together, and I am lumping all of the small inductance together to a simple circuit. So in this I can do KVL KCL, right? Here KVL KCL will not be possible. KVL KCL will not be possible. So what do we have to do? We have to simply do some other method of analysis that we will discuss. So this is a distributed circuit, this is a lumped circuit. Okay, this is a model of short transmission line. So you will say, sir, why did G and C gone? So in a short transmission line, the voltage is on the lower side. So if the voltage is on the lower side, then the leakage current through the insulators also will be low, because there is less voltage difference, and the capacitance also will be low because there is less voltage difference. Okay, so that's why we can ignore the shunt parameters. Okay, so one more important point regarding the units. So in transmission lines, everything is per meter, right? Per meter. So your R will be ohm per meter, your L will be H per meter, G will be mho per meter, and your C will be in farad per meter. So let's now discuss how do we decide the voltage rating basically. So how the voltage rating gets decided, how the voltage rating gets decided. First thing is, your voltage will be proportional to the level of insulation. Higher the voltage, higher insulation. Why? Because if let's say here the voltage is 100 kilovolt, I am only providing one insulator, then there can be leakage current between this insulator will not be able to support, will not be able to resist this much amount of voltage difference. I need more insulators in series so that it is able to resist 100 kilovolts. Okay, that is the problem here, that is the problem over here, right? So that is the thing over here. I hope you have understood. More insulators means more voltage rating. I can provide more voltage rating to the conductor. Okay, so your voltage rating of the conductor will be proportional to the insulation of the tower. Okay, so it's not like I can make my voltage rating to be very high, because I need to provide more insulation. If I need to provide more insulation, the cost will increase. So you have to have a trade-off, right? You have to have a trade-off, how much I can increase the voltage level. Of course, it has a good thing as well, that the line losses will reduce, but I need to provide more insulation, that will be more costly to me. So you have to decide according to your needs. So that's how you decide the voltage rating. Now let's discuss about the classification of transmission line. There are mainly three classification of transmission line. Now this is rough, these numbers are not exact in other books, right? The numbers can vary, but rough idea I will give you. may vary. Okay, rough idea what I can give you is length is less than 80 kilometer, and for short transmission line, so length is lower than 80 kilometer. For medium, length should be between 80 kilometer to 100 and 200 kilometers, and for long, the length will be higher than 20 kilometer. But remember, all these classification is based on 50 hertz. This classification is based on 50 hertz. Why frequency is important? So if you want to classify short, long, medium transmission line, the best way to classify will be the product of frequency into length. Why? I will explain here why FL product is important. Very basic thing. So as the length of the line becomes very higher, we know here is my sending end point and here is my receiving end point, right? This is the ground basically. So let's say initially my sending end point was here. Initially my sending end point was here, receiving end point was here, right? So if there is, I'm providing some sinusoidal waveform here, this also will be a sinusoidal waveform. But remember one thing, that if I'm providing a voltage at this node, the voltage travel, right? Voltage also has a speed. To travel to this point, it will take some time. But as it is short transmission line, the time will be very low. This time will be very low. So whatever is the voltage here, right? Let's say if the voltage here is 1 volt at t equals to 1.1 second, here also the voltage will be 1 volt at t equal to 1.1 second. There will be minute difference in time, but that will not be observable. But as the length increases, if the length increases, what will happen? Now my sending end point is here, receiving end point is here. So what will happen now? Now if I provide some voltage here, right, it will take this wave will take some time to travel from point A to point B. It's not like there is the anyway door of Doraemon, right? Doraemon has an anyway door. So that door you open, and whatever place you want to go to, you think about that place and you directly go into that place. No, it's a physical wire. The current waveform needs to travel from point A to point B. So there will be some time consumed here. So if I have some 1 voltage over here, it's not like at the same t equals to 1 second, this point also will be at 1 volt. No. Then what will happen? There will be some reflections. There will be some problems which I will discuss. I'm not deriving it. Students who have studied EMFT, they will actually know this. But for you, the thing that you need to understand intuitively is there will be some deflections. There will be some transit time delay. So due to all those things, your parameters will change. You cannot lump the parameters then like this in short transmission line. But in long transmission line, you have to actually solve it rigorously using the distributed distributed model. I will show you. Now one more thing, why is the frequency important then? Why is the frequency? So if your frequency increases, right, then what will happen? Then the waveform will change much faster, right? So if the waveform changes much faster, then there is higher probability, like let's say if the waveform is changing much faster, now you don't, although the time here let's say was 1 nanosecond here, like I'm just taking a rough number, 1 nano, or what do you want to say? Yeah, let's take 1 nanosecond only, and here let's say it's 10 nanosecond, right? But if the frequency is very high, then what happens? Your time period of the waveform reduces. Now this time period will be comparable to the transit time of the wave. It is comparable, right? If it is comparable, now this also will behave as a long transmission line. If I increase the frequency, although the length is lower, length is only 10 kilometer, but if I increase the frequency of to 100 megahertz, it will behave as a long transmission line. This is what the communication guys study, right? So that's why not communication, sorry, EMFT. This is what EC students will study in EMFT. Although they use very small components are connected in this phone, right? Small components, small length, but this also behaves as a long transmission line. Okay, you might say, how sir, this is a very small device? Yes, because the frequency is very high. That's why this product actual classification is with respect to the product. Okay, but in our case, the frequency of current and voltage will be 50 hertz. So you can classify with name with length, but actual classification is with respect to product of frequency and length. I hope I am able to explain intuitively how why is it important. You don't need to go into the derivation, because in gate no one will ask you, in interview as well no one will ask you the derivation. Just intuitively understanding why is this product of frequency to length is important, that is the most important portion. Okay, so I hope you have understood. Now voltage in a short transmission line will be lower. Why it is lower? Because the current the resistance, right, transmission line resistance also will be lower because the length is lower. Hence I don't need to provide very high voltage. Here the voltage will be moderate, it will be between 100 kilovolt to 20 kilovolt, because the transmission line resistance increases, because the line length increases. Higher the length of the wire, higher the resistance, right, because my resistance is proportional to rho L by A. And of course in the extra high, in the long transmission line, I will provide the maximum voltage. Okay, so in like I will show you in short transmission line, there will not be any capacitive effects. In long transmission line there will be moderate capacitive effects, and in long transmission line there will be complete capacitive effects. We cannot ignore the capacitance. Here we can neglect the conductance as well. Conductance as also we can neglect. And here we can in medium transmission line as well we neglect the conductance is neglected here, but in long transmission line nothing is neglected. In medium transmission line capacitance is considered, Rx is already there, reactance and inductive reactance and the series resistance is there, but conductance is neglected. But in long line everything will be considered. Okay, so this is the model. Okay, approximate model. These are all models of transmission line. Okay, if you see here, in short transmission line only the resistance and inductance is present. In medium transmission line resistance, inductance, capacitance is present, conductance is not there. In long transmission line every single thing is present, we cannot ignore everything. Now this was the classification of transmission lines, right? Now there are few more classifications. Okay, based on function. Transmission lines we have already discussed. It is the link between the generating station and the main substation. There are a few more lines like feeder. So actually what happens, transmission line is the main link between the generating station and the substation. Substation then has, like, we don't directly connect the substation to the load, right? There are feeders, like few feeders are there, distributors. So this is the distributor. Then from substation there are individual distributors, right? So what is the example? Let's say in Bangalore, right, the generating station is somewhere in Andhra Pradesh or somewhere, I don't know where exactly, somewhere in Andhra. It will come to the main city Bangalore, right, in a substation. Then from here it will go to the distributors, right, distributors. So distributors will be the, let's say, small locations where the power is delivered to individual houses, right? Let's say in Bangalore there is MG Road, there is Kormangla. Okay, you can also name your district or personal district, right? Kormangla, this are all there, right? Small districts. So it is not like directly will connect the substation to the load, right? Kormangla, I don't know the spelling. Okay, I don't know the spelling. So the thing is, this, right, this link between the generating station and the substation is known as transmission line, and the link between the distributor and the substation is known as the feeder. That's why it is called feeder here. Connects the substation to the distributed system local networks, and your transmission line connects the generating station to the main substation. There is reason behind isolating this thing, because if some fault happens in the transmission line, right, only this generating station will be totally disconnected. There can be other generating station, right, that can deliver the power. Okay, that is the reason why we separate this out. Okay, so minimize losses. Of course there is now what are the features? So it is designed for high voltage. Transmission line will be designed for high voltage because generally it is long transmission line only, and we generate the voltage at high, and then because your generating station is very far away from your locality, you will not see a generating station in Kolkata, in Bangalore. It is very far away. So if it is very far away, length is very high. So voltage also have to apply very high. So that's why you see the voltages will be higher. Okay. And your feeder operate at lower voltages. Okay. So it is designed for high voltages, low current, and it is designed for low voltage. And here also we have to reduce the current, right? Primary goal in both the cases will be to minimize the losses, okay, to basically reduce the current. So that was a example basically. So if you see, here is my generating station. First we step it up, and then it goes to the transmission line, and through the transmission line it reaches the substation, and from the substation it goes to the distributor, right? So I hope that is clear now what happens, how there is link, right? So here I have my substation, and this is my feeder. Okay, so like from here I get my feeder. So from here I get my feeder, right, after the substation, the line connecting, this is my feeder basically. So this line, right, this line is the feeder that is connecting your substation with the distributors. Okay, I hope it is clear. So distributor has a very important purpose. The purpose is, in the case of distributor, the current is not constant, because I disconnect the loads. It depends on the person, if I want to turn on the fan or turn off the fan, but the voltage must remain constant, because all the load is rated to operate at 220 volts or something like that. So we have to keep the voltage constant at any cost, right? Current will keep on changing in the load side. So that is the purpose of a distributor. Now let's do few questions, and with this we will end this lecture, and in the next lecture we will discuss about short transmission line, performance of short transmission line. Okay, so a transmission line rated at 800 kilovolt has a maximum power transfer capacity of P. Okay, so maximum power transfer capacity is P. If the line is now operated at 400 volt, so previously it was operated at 800 kilovolt, but now they are telling me I am operating the line at 400 kilovolt with a series reactance remaining unchanged. So it has a series reactance, right? What will be the approximate new maximum power transfer capacity? What will be the approximate new maximum power transfer capacity? That is what they are asking. What will be the approximate new maximum power transfer capacity? So the voltage has reduced, right? Voltage has reduced. So do you remember what was the power transfer capability? Do you remember this formula? Uh, the formula was what? The formula, I have already discussed this anyways. What is the current? Current is power divided by V cos phi, right? And they are telling you that the power also has reduced. Okay, if X is constant. So this formula, I hope you remember, this we have used in PSA 2 as well, that it is Vs VR by X into cos of delta into sine of delta, right? This formula we have used multiple times in PSA 2, right? So from here, of course, if it is operating at 400 kilovolt, my expectation will be roughly here, if I am providing 400 kilovolt, roughly this also will be equals to 400 kilovolt only, right? There will be some drop, I do agree, there will be some drop, but roughly it will be equals to 400 kilovolt only, right? So because what is fixed is the reactance. So if reactance is fixed, right, Then accordingly you have to write the formula. This formula is for a fixed reactance. Now I know basically what I can say, that the maximum Pmax will be what? Pmax. What is Pmax? Pmax, delta is not there. Pmax is proportional to VSVR, delta will be 90, VSVR divided by X, right? X is constant, so it is basically Vs into Vr. Roughly we assume that Vs and Vr are roughly the same. So basically it is proportional to the magnitude of the voltage whole square. So your maximum power transfer capability of the machine, of the transmission line, depends on the voltage whole square. Other things are fixed, right? So I can simply take out the ratio. Pmax 2 divided by Pmax 1. So this will be Pmax 2 will be magnitude of V whole square. So voltage has been reduced to half, right? So now it is magnitude of V by 2 whole square, and previous voltage was, like, basically it is 400 kilovolt, right? And previous voltage was 800 kilovolt. So this will be 1 by 2 whole square, so 1 by 4. So your maximum power transfer capability reduces by 1 by 4. So it will become P by 4. The new maximum power transfer capability will become P by 4, reduced by 1 by 4. Right? So this is just a simple formula that we have used previously as well. That's why I'm not deriving it, because we have already used it. Right? So one more thing I want to discuss uh, regarding the current rating. How can I derive the current rating, right? So for the same power transfer using same material, same line length, if the transmission voltage is increased by a factor of n, how does the cross sectional area of the conductor change? Okay, if it's the same transmission line, I know, right? And if it's the same resistor, I know your current rating, right? I rating dependent on what? I rating is basically into J dot A. What is J? J is basically the current uh, density. J is the current density, right? Current density. J is the current density. So what I can say is this has to be constant, because in a particular cross sectional area, if the material is fixed, the current that can flow has to be fixed. So basically I by A is fixed. That is why my J is fixed, right? So if you increase the amount of current, you have to increase the amount of area, right? So that the area, like the current density is fixed, because the amount of current that can flow through a particular area will be fixed for a particular material, right? Now let's read the question. They are telling that for the same power transfer, same material, same line length, transmission voltage is increased by factor of n, right? So your transmission voltage becomes nv, right? How does the cross sectional area of the conductor change? Okay, how will the cross sectional area of the conductor change? That is what we have to discuss. So if I am increasing the voltage and power is same, so if power is same, I know what is my power. Power is, what is my current? Current is basically V cos phi, right? So current, if voltage is increasing by a factor of n, and of course cos phi will not change, so current will reduce by a factor of n. So I will become I by n, right? Now I know my current density will be constant. J will be constant, that is I by A. So I can take the ratio. Here what will be my J? So let's write this I dash. So I dash will be I by n. So my j dash will be what? J dash will be I dash upon E dash, correct? Which is equals to j only, that is equals to I by E. Okay, so this will be my E dash will be I dash. I dash is I by n into uh, now into E divided by I, right? I'm just equating this relation. So your I will get cancelled. Your area will reduce by n. Your area will reduce by n. Okay, I hope that is clear. So the answer to this question will be area will reduce by n. Okay, area will reduce by n. Now from this, right, the answer is area will reduce by n. From this I can maybe I should have discussed this before, not after. What is the current? I want to discuss what is the current rating of uh, a conductor, right? So basically I have told you, right, your current density must be constant, because the amount of current that can flow through a particular area must be constant, otherwise the conductor will simply get damaged. So current density, the unit of current density is ampere per meter square. Ampere per meter square, right? So what is your current density? It is simply I upon A. So what I can say over here, that your current density is constant, so your current, right, current is proportional to area. So if I want that the transmission line should carry more amount of current, I have to simply increase the area. If the other things are constant, length and all those things are constant, then I have to simply increase the area, right? So your current rating is proportional to the cross sectional area of conductor. Okay, so it is proportional to the cross sectional area of the conductor. So that is the important factor. Now considering the fact, considering the fact fact that my length is constant. Okay, so these things you should keep in mind, considering the fact that your length is uh, constant. Okay, now yeah, one more thing is that how can I minimize the losses? So your losses is dependent on what? So your losses, minimize losses. minimize minimize minimize. So if you see, if I want to minimize losses, what is your losses? It is I square R. So your R must be minimized. So what is your R? R is proportional. R is equals to rho L by A. Right. Again here, the length, right, distance between the sending end and the receiving end will be constant. So your R is inversely proportional to A. I have to reduce my R, so I have to increase my area. Right. So increasing area has advantages. Right. It helps us minimize the losses. Okay. So if the current rating of the if I increase, because I know, so basically what is it is telling what is area proportional to, area is proportional to the current rating. So losses will be, remember I will just tell you again, losses will be minimized if the if we increase the current rating. Okay, so remember, it is current rating, it's not like I'm increasing the current. Increasing the current will increase the losses. If I increase the current rating of the transmission line, then the losses will be reduced. Okay, current rating, very important point. Current rating, not the current that is flowing, the current rating of the transmission line. Okay, of the transmission line. Okay, very important. Current rating, not the current of the transmission line. Okay, so these things you should keep in mind. So yeah, let's solve another question. So let me delete all this. This is not required. For constant power transfer using the same material, same line length, and maintaining the same power loss, the voltage of the feeder is increased by n. How many times? Okay, this is the same voltage. Okay. Oh, it's the same question only. Okay, it's not a different question. Same question only. Sorry. So this will be 8 actually. This will be 7. If a wire with resistance R is uniformly stretched n times, like this kind of basic questions will be asked. This you have solved in JE as well, I guess, I hope. If a wire of uniform, if a wire with resistance R, right, it is stretched to n times to its original length, right? So if previously the length was L, now the length has become n into L. It is stretched. Same wire is stretched. If the wire is stretched, the wire will have its own volume. What is the volume of the wire? It will be area times L, right? So if the length has been stretched, the volume will be constant still. This volume will be constant. So if the length has now increased, if I'm increasing the length of a certain wire, what will happen? The area will reduce, right? To keep the volume constant. Same, right? If you ever have a stretchable, anything stretchable, right? This, if I have stretchable, if I increase it, right, what will happen? The area will reduce. So if I increase the length, the volume needs to be constant. So volume is what? A into L, right? And the new length is n into L, and new area will be A dash. So your A dash will become A by n. So your new area becomes A by n. Now they are simply asking you what is the new resistance. Very simple, right? If previously the resistance was rho L by A, right, the new resistance R dash will be the new length. Rho will not change for a material, rho will be fixed. Rho L dash divided by E dash. Okay, So this will be rho L dash is N into L divided by E dash is A by N. So this will become rho N square L by A. Okay, so what is rho L into A? Rho L into A is R. So basically your resistance is N square times R. So your resistor increases by R. Like this is a JE question. Okay, just wanted to give you a feel what will actually happen to the resistor. So resistance will be N square into R, N square times the previous resistor. So these were the questions, basically like few basic questions I took, right? In the next lecture we will do the complete performance analysis of short transmission line. We will see whatever I have discussed, right? By connecting a external capacitor, how can I improve the voltage, how can I improve the power factor, all those things we will see in the next lecture. Today was just an overview, just a brief, just to give you the intuition what will be coming next. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the short transmission line. Okay, so in the previous lecture we discussed, I have given you overview what kind of parameter we neglect, what kind of parameter we don't neglect. So I have told you the reasons as well, but today we will dive more deeper into it, especially for short transmission lines. And of course, in the next upcoming lectures, we'll discuss for long transmission lines and for medium transmission lines as well. Okay, so in short transmission lines, our transmission line is modeled like this only. There will be R, L, G, C. How each component comes, that we have discussed in the previous lecture. Right now, in case of short transmission line, I will neglect my conductance and I will neglect my capacitance. I will neglect my conductance and I will neglect my capacitance. Okay, so what is my conductance? Depends on conductance, right? Mainly is leakage current, right? Leakage current. So leakage current is a function of voltage, right? So leakage current, I leakage, is a function of voltage. And I have told you that for short transmission lines, we don't provide that high amount of voltage because the resistance is lower. So I don't need to provide very high voltage. So I leakage will not, like the voltage will be lower, right? So if voltage is lower, then I can neglect the leakage current. I leakage also will be very low. If I leakage is very low, that means I can neglect the conductance, like whatever current, right, leakage current that will flow, I can neglect that. What about capacitance? Now the capacitance, right, here the capacitance actually is written in capacitance per unit length, right? It is basically equals to C1 into L1, where C1 is the capacitance per unit length and L1 is the length of the line. Capacitance depends on the length, right? So what is the reactance? Reactance is equals to 1 by omega C1 into L1. So in case of a short transmission line, C1 into L, sorry, in case of a short transmission line, I know my length is low, right? Length is low. If length is on the lower side, then XC will increase. XC will tend towards infinity. And if I have very high impedance, I can neglect that branch if the impedance is very high, right? So that's why we neglect the capacitance and the conductance in case of a short transmission line. So in short transmission line, only R and L is present. So same thing is written over here, justification. Whatever I have explained, same thing is written over here. So this is the electrical model of a short transmission line, which is very simple because this is similar to the synchronous generator, right? Synchronous generator. So whatever derivations we did in synchronous generator, that will be utilized. That will be utilized here. So I will tell you which lecture to revise. Okay, and in transformer as well, this was the series impedance, right? So the same reason. Now, of course, the shunt components will be neglected, but the series component I cannot neglect. I can never neglect the resistor because current will flow and current value is always high, right? And of course, there will be some reactance, there will be some inductance, inductive reactance, right? So these we cannot neglect. So we will do derivations depending on these two parameters. Now, before starting this, I want to explain one thing, that what is the, like I want to derive the ABCD parameters for a short transmission line. Okay, because transmission line, right, that's how the name transmission came. It is similar to the transmission, like we want to write everything in terms of transmission ABCD parameters. Through that we will do our calculations, we will do our power calculation, we will do our voltage calculation. You will see in this lecture we will derive, and from there we will see what is the performance of the transmission line. Okay, so we have to derive the what do you call the ABCD parameters of this R like simple short transmission line, right? This is the equation for ABCD parameter. Now standard method, how can you find out the standard method? So as my transmission lines, right, few things I know. This network is symmetrical, right? I'll not explain how it is symmetrical. This network is simply symmetrical, right? From this side I can see series combination of R and XL. From this side also I can see a series combination of R and XL. So network is symmetrical, right? Network is symmetrical, right? That means what? That means one thing, that my A will be equals to D, and of course it consists of components R, L and C. It does not consist of anything else. It consists of R, L and C. So if it consists of R, L and C, basically your network also will be reciprocal. So I'm expecting that you have studied two ports from me. So what does these terms mean? I have explained over there. So network will be reciprocal. So what is the condition for reciprocity in ABCD parameters? It is AD minus BC equals to 1. Okay. Now what else can I say? I can say that how do I find out? Like I just need to find out two variables. Other two I can find it out from these two equations, right? So let me say, how can I find out the parameter A? How can you find out the parameter A, right? So you can simply calculate the value of A if I open circuit the load. Okay, if I make the IR 0, that is there is no load connected, at no load, right? If I measure Vs and Vr, I will be able to get the value of A. So A will be equals to what? If I put IR equals to 0 here, A will be equals to Vs by Vr. So A will be equals to Vs, magnitude of Vs divided by not magnitude, sorry, complex number Vs divided by Vr. Okay, Vs divided by Vr. Now what I can say is that this is actually complex number. It will be magnitude of A into alpha. Okay, magnitude of A into alpha. So that's how you will find your A, and if you know your A, you know D, right? D is sorted. Now how can you find out C? C is again, you can simple, right? C is again simple. How will you find out C? If you make like at no load, your C will be what? C will be simply the ratio of the sending end current divided by the receiving end voltage, right? So from here you will be able to get the value of C, right? This will be some magnitude of C into theta C. So if you know, like if you are able to get C, you will be able to get B, right? From these two equations you will be able to find out your B. So that's the standard way, right? Standard way. But of course there are a few formulas that I will discuss, don't worry. Your B will be what? B will be simply magnitude of B into beta, that will be equals to So your B will be here A square, because A is equal to D minus A square, yeah, A square minus 1 divided by C, right? That is what your B value is. Okay, so B value is actually pretty important. While you will derive the power flow, you will understand. So basically what you have to do, you have to make the receiving end operate it at no load. So receiving end, right, receiving end should be open circuit. Like this I am talking about if you don't know how the circuit is. If you just have a black box, right, of the transmission line, and you have to find out the ABCD parameters, that's how you will find out the ABCD parameters. Okay, open circuit. Now of course we will not do it like this, right? Of course we will not do it like this. I have derived in my two-port networks chapter the transmission line parameters for a network like this, Z1, Z2, right? I have derived this. I will not explain it over here again. Okay, so two properties I will use. First of all, this thing you have to memorize. This I have derived this in the two-port networks network theory, that the ABCD parameters of a standard network like this is 1 plus Z1 divided by Z2, Z1, 1 by Z2, 1. How will you remember this? Very simple. So we know what is A. A is the ratio of two voltages. So A will be unitless. This component will be unitless. And your B, if you see, B is the ratio of voltage divided by current. So this has a unit of ohms. Okay, and your C, if you see, it is the inverse. It is the current divided by voltage. So this will have a unit of ohm inverse. And your D again will be unitless. Why? Because it is the ratio of current and current. So it will be unitless. Okay. So the thing is, and one more thing, the network is not symmetrical, right? Because from here Z2 is parallel, but from here Z1 is in series. Okay, network is not symmetrical, but it is reciprocal. So this property has to follow, that AD minus BC will be equals to 1. Okay, AD minus BC will be equals to 1. So it has to be reciprocal, right? It has to be reciprocal. So the thing is you have to remember this one, this part, first term you have to remember. How will you remember? So you must remember that 1 will be there, okay, and it is unitless. So there cannot be 1 by Z1 or Z1 or Z2, right? There has to be ratio. So it will be simply Z1 divided by Z2. So first series will come, then the parallel component will come. So 1 plus Z1 divided by Z2, that is done. Then I know that the next, the B parameter is just in ohms. So it has to be the series impedance. So that's why Z1 is here. And I know the C parameter is ohm inverse. So it has to be the shunt impedance, that is 1 by Z2, ohm inverse. And at the end I will have 1. How? I will use that property. Or if you ever tend to forget this, right, at least remember that I have 1 at D, it is unitless. I have 1 by Z2 here because it is ohm inverse. I have Z1 here because it is ohm. Now you just apply this property, you will be able to find out your E. So whichever way you like, you can do that. So this is the first thing that I want you to remember. The next point is, I want you to remember the transmission line parameters of two cascaded networks. If I cascade two networks, what will be the overall transmission line parameters? It will be simply the matrix multiplications of the individual transmission line parameters, right? If I cascade two networks, the overall transmission line parameters will just be simply the matrix multiplication of the individual transmission line parameters. I hope it is clear. So now let's derive the ABCD parameters for a short transmission line. This method will be used when you don't know what is inside this circuit, but I know the circuit, short transmission line. So I will directly write down the expression. What is the expression that we get? Okay, so here I can write this, right? Z, it is just a series combination of R and XL. I can write this as R plus JXL. Okay, so okay, so yeah, so this is my Z basically, right? What is my Z2 here? Can you tell me what is my Z2 over here? So my Z2 is actually not present, right? Z2 is actually not present over here, right? Because it is infinite. Basically Z2 is infinite. So Z2 is infinity because it is open circuit, right? You don't have a Z2 here, it is open circuit. So what is the transmission line parameters for this? Very simple, right? It is 1 plus Z1 divided by Z2. So Z1 is finite, Z2 is infinite. So finite upon infinite will be 0, 1 plus 0. Then I have Z1. Then I have 1 by Z2. Z2 is infinity, so it will be 0. And then I have 1 at the end, it is fixed, right? Same, I'm using the same formula that I not derived, I explained. So basically your transmission line parameters E will be 1 angle 0, right, for a short transmission line. Your B will be simply Z1, right? Okay, that is simply R plus JXL, and your C will be 0. And your D will be 1. Okay, so these are the ABCD parameters of a simple short transmission line. I hope it is not that difficult to understand, right? Okay, now you might have a question, sir, we have analyzed the transmission line with ABCD parameters, why we don't analyze the generators and motors as ABCD parameters? You might have a question. Okay, so ABCD parameters are called transmission line parameters. They are generally used to model two-port networks, that is input and output, that is the transmission line. Now for a generator, what is input? Input is the mechanical power. Transmission line, the input is the electrical power and output is also electrical power, right? Transmission line, I'm just transferring electrical power from one point A to point B, right? For generators, the input power is mechanical, so and the output power is electrical. So I cannot model the generator with ABCD parameters. We have to draw the equivalent circuit. Right? Although that's also a electrical model only, but I cannot exactly model the generator. And for motor as well, the input is electrical power, but the output is mechanical. So this involves energy conversion. So we cannot exactly show that with ABCD parameter. So what do? We draw the per phase equivalent model. We use the power angle equations. We draw the torque speed characteristics. All this information we do to model the generators and motors. So this was about a quick like trivia why we don't model ABCD parameters with for generators and motors, right? Why only for transmission lines? So this was the ABCD parameters for short transmission line, not that difficult, right? So I want you to quickly go and revise the lecture 18 where I discuss about voltage regulation. Okay, if you already have watched that, very great, very good. But lecture 18 of electrical machines, I wanted to revise because there I have derived the voltage regulation formula, everything. So I will not do that again. So voltage regulation will be same. Why? Because it is simply R plus Jx. There also it was R plus Jx, same, right? So voltage regulation derivation will not change. Everything will be same. I will use the same formula. Okay, here. So my recommendation will be quickly go through the notes or revise it. Okay. Now, what is voltage regulation? Voltage regulation is the no load voltage minus the full load voltage at the receiving end divided by the full load voltage into 100%. That is the voltage regulation, right? So uh, now now I can write the generalized expression for voltage regulation. I will derive the voltage regulation for a short transmission line, but this expression is the generalized generalized for regulation. Okay, what do you mean? This will be for valid for any transmission line. In the next few slides, I will explain. I will derive the voltage regulation for short transmission line. That formula will not be valid everywhere. Okay, but this will be valid for any transmission line. How is it valid? So, what is the receiving end voltage at no load? The receiving end voltage, if I see right here, if I make the IR receiving end voltage at no load, basically means making the IR 0. If IR is 0, what is VR at no load? It will be Vs divided by A, right here or here only. At no load, IR is gone, so VR no load will be Vs divided by A. So I have just replaced my VR no load to Vs divided by A using the ABCD parameters, and of course the full load voltage will be given to you. It's the rated voltage that will be given to you. So this formula is valid anywhere. Okay. And one more thing I wanted to explain it to you. Why are we comparing this with respect to the full load voltage receiving end? Because receiving end basically means where the load is connected, and generally we assume that the load side the voltage must be fixed. That's why we are calculating the voltage regulation with respect to the receiving end full load voltage. So as load is connected at the receiving end, okay, as load is connected at the receiving end, hence we compute voltage regulation. With respect to the load side. Okay, with respect to the load side. So like this, right? I have derived this in the machines lecture. You go and watch that lecture. So I will not explain it over here again. So there I derived that the exact expression for Vs for a simple series RX circuit, right? This circuit, right? The voltage regulation for this circuit comes out to be this. VR cos phi r, that is a load power triangle, plus I into R whole square, plus VR sin phi r plus I into X whole square. Okay, this is the exact value of Vs, and if you want to compute the approximate value of Vs, right, it will be VR plus IR R cos phi r plus X sin phi r. And at no load, what happens at no load? At no load, your VR will be equals to Vs, right? So at no load, in a short transmission line. In a long transmission line, maybe we are not equals to Vs because there will be a parallel branch through which some current will flow. But in case of a short transmission line, there is no parallel branch, so Is will be equals to Ir, and at no load my Ir will be 0. That means your Is will be 0. If Is is 0, right, there is no drop here. So at no load, Vr no load will be equals to Vs no load. Okay. Okay, Vr no load will be equals to Vs no load. So I hope that is clear. I hope that is clear by you, right? So that's why, well, like Vs is equals to Vr no load, so not Vs no load, sorry, Vr no load will be equals to Vs because there is no drop. Isn't this what we derived here as well? So in short transmission line, what is your A? Your A is 1, right? Short transmission line, your A is 1. So if A is 1, it is simply magnitude of Vs minus Vr full load by Vr full load. So your voltage regulation comes out to be Vs minus Vr full load because A is 1, right? So same, the formula will be valid there as well. Vr full load divide by Vr full load into 100. Percentage. Okay, so that is the voltage regulation basically in case of a short transmission line. Okay, so what is Vs minus Vr? So Vs minus Vr, I can directly use the approximate formula because you're sending in voltage at the full load, right, will be something else. So that I can derive from this formula, that it will be like Vs minus Vr will come here. So it will be Ir r cos phi r plus x sin phi r, right? This will be the approximate value. So it comes out to be magnitude of, like this I have derived in the machine, so I'm not explaining it over here again. So it comes out to be magnitude of Ir r cos phi r plus x sin phi r divided by magnitude of Vr into 100%, right? Which in per unit, because it is a current upon voltage, this is the Z base and this is R divided by Z base will be Rpu, X divided by Z base will be Xpu, right? So it will be Rpu plus Xpu, Rpu cos phi plus Xpu sin phi r into 100. Okay, this I have derived in the machines lecture. Now there are two things. What is the condition for zero voltage regulation? Why do I want zero voltage regulation? Because then only the voltage at no load and voltage at full load will be same. So there will not be any voltage variation, right, at full load and no load, right? So that is what I want. That's why I want zero voltage regulation, because I want my voltage at full load and voltage at no load to be same. Okay. Okay. So 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 what I can say is, what I can say, I want to make it 0. So if I want to make it 0, basically this needs to go to 0. This needs to go to 0, right? So this needs to go to 0. So basically my Rpu cos phi r plus xpu sin phi r will be equals to 0. then your basically what do I get? I get the okay, tan phi r is equals to minus of rpu divided by xpu, right? So it comes out to be something negative meaning what? Your phi r is negative. Phi r negative meanings what? It means your load has to be leading. For leading load I will get zero voltage regulation, because the transmission line itself is lagging in nature. I have to provide additional reactive power to the transmission line so that the delta V goes to zero. Intuitively, that is how you can understand, right? So again this, right, RPU XPU, this I can rewrite this as minus, I can multiply by Z base both the numerator and the denominator. So this will become minus R divided by X. Okay, that is what my tan phi r is equals to. Okay, so I hope that is clear to you. Right, so this is the condition for zero voltage regulation. This I have derived there as well. Now one more thing we do, generally we assume that the resistance, right, is much lower than the series reactance. That is what you will observe, that is the practical case. So if that is the case, then this, right, almost becomes zero. So your phi r is zero. If phi r is zero, basically your cos phi r will be 1, that is unity power factor. That's why, that is also another reason why we want to improve the power factor. If your power factor is lagging, very low power factor, 0.2 lagging, right, that is not actually good for us. We want to reach to unity power factor so that our voltage regulation is good, near zero. Okay, that is also another reason why we want to operate in higher power factor or unity power factor. So there is another condition for maximum voltage regulation. So this is actually desirable. This particular condition is desirable. And this particular condition is actually not desirable. This is undesirable. This is undesirable. Okay, this is not desirable. So what I can say is, why it is not desirable? Because then the, like, then voltage regulation is maximum. Basically the difference of the voltage V full load minus V full VR at no load and VR full load will be highest. That is, the no load voltage will be very high, full load voltage will be very low. So there is a drop off, right? That is what we don't want. We want the load side voltage to be constant. So this is undesirable. But we can derive the condition when it will be maximum. When it will be maximum, simply I have to differentiate this. So I will write this, my voltage regulation is equals to this, right? This value. I have to differentiate this with respect to phi, because my load, right, the power factor of the load is varying. So we are varying the load power factor and seeing in which condition I am getting zero voltage regulation and maximum voltage regulation. So this is my function, right, and I will differentiate this function with respect to phi. So this will be RPU sin pi r plus XPU into okay, sorry, this will be minus of sin phi r because differentiation of cos is minus of sin, and XPU cos phi r. Okay, so this I have to equate with 0, then only maxima will happen. And I observe that I get the same condition, something similar condition, but it's quite different. It is basically equals to, this time it will be x pu divided by r pu, which is positive. If it is positive, right, it is positive, that means your phi r is positive. That means maximum voltage regulation, that is undesirable factor, undesirable phenomena, will occur at lagging power factor. This will occur at lagging power factor, right? So that's why we actually tend to avoid lagging loads. So one more thing, again we can apply the same thing. I can multiply and divide by z base on both sides. Multiply and divide by z base on both sides, both numerator and denominator. This will be x by r. Okay, I hope it is clear now. It is x by r. So now what are the conditions basically? Now yeah, the thing is, again the same approximation if I do, that my r is much lower than x in series short transmission line. So this x by r goes to infinity, that means your phi r will be tending towards pi by 2. So when the load is purely lagging, right, then I will get the worst possible voltage regulation. There will be more fluctuation on the line. Okay, so the statement is, right, the main statement is purely lagging. When the load becomes purely lagging, uh, voltage fluctuations increases. Okay, so that is what we don't want. That's why it is a undesirable condition. Okay, so I'm just varying my power factor with respect to power factor. If I keep on varying, you will see that that's how the voltage regulation changes. So voltage regulation becomes 0 at leading load. That's why here at certain leading load, just when the power factor like phi angle is negative, right, pf angle is negative, the voltage regulation becomes 0. And if I reduce my angle further, it will go negative. That is also undesirable, right? That my load side voltage is higher than the source side, that is also undesirable. And if I increase my power factor angle, load angle, power factor like load angle, then voltage regulation becomes more and more positive, that is also undesirable. We want to lie somewhere around here. That's why we need to make our load leading. Of course, you cannot control the consumer and tell him to connect a leading load. So we have reactive power compensation to fix the voltage regulation. So I hope it is clear why we use reactive power compensation. Just to lie near this region, so that whatever reactive power that the load is demanding, reactive power compensator will deliver that. The generator side will not deliver, so that our voltage regulation is maintained. Okay, I hope it is clear. So let's do few questions. This is the first question, that the voltage regulation of a system is 0 at 0.85 leading power factor. The voltage regulation of a system is 0, okay, at 0.85 leading power factor. So cos phi is 0.85. I can find out the phi from this, right? What will be the phi? Phi will be, remember, negative, not positive. Phi will be negative. So it will be 0.85 cos inverse phi will be 31.79 degrees. Okay, that is what your phi will be. Now your what is your sorry, minus, right, negative, because it is leading load, right? Leading load voltage regulation will be 0 at leading load. So what will be the nature of the voltage regulation at 0.75 leading, right? So they are actually not asking me some values, they are just asking me what is the nature of the voltage regulation. Will it be positive, negative, 0? Data insufficient. So data insufficient. So I'm worsening my power factor. So from 0.85 it is going to 0.75. So the phase angle phi is actually going, magnitude of the phase angle is increasing, right? That means it is becoming more leading, right? If I'm increasing my phase angle further, what is happening? If I'm going more leading, what is happening? The voltage regulation is becoming negative, right? If I'm going more leading, the voltage regulation is becoming negative. If let's say here I told you that the power factor has now been increased to 0.9, that means what? I'm going towards unity power factor. So here it is some leading power factor. If I'm going towards unity power factor, that means I'm going on the right hand side, because the power factor angle will be 0. This is the point of unity power factor, right? So if I'm going towards the right hand side, then the voltage regulation will be positive. If I'm going towards the left hand side, the voltage regulation will be negative, because I'm making the load more leading. That means I'm going on the left hand side. Okay, so here voltage regulation will be negative. So it will be negative. Option B will be correct answer for this question. Okay, so pretty simple. I hope not that difficult for you to understand. Now let's solve this next one. Find the sending end power factor for the following power system. So I have to find out the sending end power factor. Now there is a difference between the receiving end power factor and the sending end power factor. What is the receiving end power factor? Receiving end power factor is the load power factor. So receiving end power factor is simply the load power factor. Receiving end okay, that's very simple, right? But what is the sending end power factor? Sending end power factor cos phi s will be basically the sending end power divided by the sending end complex, magnitude of the sending end complex power. Okay, two things are very different. Okay, this I have taught in power electronics as well. Here again I am teaching you. Okay, so what is the sending end power? How do I calculate the sending end power? For that I have to calculate the compute the current, because current is same, it is a series circuit. So what is the current here? So current, right, I will be equals, now here, right, one thing is there, have they mentioned whether it is a three phase load or a single phase load? They have not mentioned this. That's actually pretty bad. They should have mentioned. So the load is a three phase load, they should have mentioned it, right? Assume the load to be three phase star connected load. Okay, assume the load to be three phase star connected load. Now here, what is your current? Current will be, as it is a three phase star connected load, IL, line current is same as the phase current, will be the power 5 megawatt divided by root 3 VL cos phi. Basically it is P upon root 3 VL cos phi R, the receiving end power, receiving end power factor. So which is equals to, P is given to me, that is 5 megawatt. Let me do one thing, let me change it on the assignment side as well. So yeah, let us find out the current. So I'm talking about the magnitude of current. Angle I already know, because I know the power factor angle, because I will assume that the receiving end voltage is at reference. So receiving end voltage will be magnitude of VR, angle 0 degree. Okay, so this will come out to be, here this will come out to be magnitude of VR cos phi. So what is magnitude of VL? Magnitude of VL is 10 kilovolt. Cos phi R is 0.8. Okay, so this will come out to be 5 into 10 raised to power 6 divided by 10 raised to power 4 divided by root 3 divided by 0.8. So your current comes out to be 255.15 ampere. That is the magnitude of current. Now what will be the angle? So IL will be magnitude of current 255 15 angle will be what? Angle will be it is, remember, it is a they should have mentioned, actually it is a lagging load, right? I have not mentioned 0.8 lagging. Okay, should have mentioned it, lag, right? So this will be minus cos inverse of 0.8, right? Power factor is cos phi, so cos inverse will be phi, and minus because it is lagging load, so 0.8 cos inverse is 36.255 0.15 minus 36.86 degrees. Okay, so that is what your uh, load current is, that is what your IL current is equals to, right? So now what I can do, I can find out Vs from this, right? I can easily find out my Vs because I have to find out the sending end power factor. So how will I find out sending end power factor? So what will be my SS? SS will be simply Vs Is conjugate, and I know Is is same as IL, so it will be Vs into IL conjugate. Now what is my Vs? So Vs will be this drop I have to consider, right? So my Vs will be, you can use the approximate formula. You can always use the approximate formula, but I will recommend, if the circuit parameters are given, don't go by the approximate formula. I will show you the approximate formula as well. Your Vs will be Vr, just applying KVL, right, into IR R plus XL. Okay, so Vr will be 10 kilovolt plus IR. IR is already, I know what is IR, 255.15 minus 36.86 into R plus JXL. So what is R plus JXL? R is 3, so R plus JXL, this will be 5 angle 5 angle 53.13. Okay, so okay, 10 kilovolt plus this, right? So this will come out to be 10 raised to power 4 plus 255 into 5, that is 1275.75. This will be 36.86 plus 53.13, 16.27 degrees. Okay, so this will come out to be cos of this into 1275. So this comes out to be 1 point, okay, 224 into 10 raised to power 4, right? Am I correct? So it was, sorry, it was 10, sorry, it is actually 1 into, no, this is correct only 2 point, no, it is 1000 something, right? Oh, sorry, this will be 1.12 into 10 raised to power 4 plus j 16.25 sine 16. sine into 1,275,175. So this will be 357.42. So this divided by 1.1224, okay, and divided by 10 raised to power, what happened, 12240, sorry, 11224, 11224 divided by, sorry, 357.42, this inverse. So your Vs, right, the angle of Vs comes out to be 1.8239, and this magnitude will be almost same only, like almost the real portion only, 224 whole square plus 357, it will not change, whole square under root, yeah, it is almost same, 1.1229. Okay, into 10 raised to power 4 volts. Okay, so yeah, sorry, so this will be, yeah, this is my voltage basically. Now I can directly write what is my apparent power. Current I already know, so apparent power, like that's why I derived you that formula as well. Like sometimes you will see that formula is useful, especially when the power factor is very near to the unity power factor. We'll use that formula. Okay, so here if I see, your sending end apparent power will be Vs into Is conjugate, which is IL conjugate only. So Vs is this value, 11.229 kilovolt, angle 1.8239, degrees into Is. Kilovolt is there, I am just writing here kilowatt, kilo kVA, and your current is, I can write this current also in kilo ampere, right? Current is how much? 0.255, so this will be in MVA, 0.255, 0.255, angle minus 36.86. Okay, so this will be equals to into 0.255, so this comes out to be just hold on, 11, just give me 1 second, 11.229 into 0.255, yes, just 229, right, 2.864, angle will be what? Angle will be minus 36.86 plus 1.8235 minus 35.35 degrees, right? Okay, so that is what your apparent power is. Now you can break it down, right? It is PS plus, or you can directly from here you can directly find out what is your uh, sending end power factor. So what will be sending end power factor? So this angle, right? This angle is the angle difference between the voltage and the current, right? So your cos phi s will be what? Cos phi s will be simply cos of minus 35. Now negative means what? Here what was the angle? Uh, this will be Ia conjugate, right? Sorry. I made a mess of it. This will become plus. So 36.86 plus 1.82. Positive means it is simply lagging, right? So this will become actually 38.68. So it will become plus 38.68. Actually, I did not need to find out all this. I just needed to find out sending it power factor. This will be this, right? Which is cos of this 0.78. It worsens because I have to deliver bit of reactive power to the series reactance as well, because this is demanding some reactive power and some of the reactive power is getting utilized in this inductor. So that's why the power factor worsens. So it will be 0.78 and it will be lag. Why it will be lag? Because this angle is positive, right? Or your current lags the voltage. As your current lags the voltage, it has to be lagging power factor, right? Is there a simpler way to calculate? Because anyways you will need to find out this angle, right? This angle is the main thing. Without this angle you will not be able to calculate. So I don't feel there is any other simpler way, because magnitude you can calculate, magnitude of Vs you can calculate with approximation, but angle if you have to calculate, you have to use the simple uh, formula, right? You cannot actually use that, but we can use something else as well. I think, yeah, I can derive something if I am thinking that if I do some can I find out the sending in power factor? That is what I am thinking, right? How can I find out the sending in power factor? So if I draw the phasor diagram here, right? If I draw the phasor diagram, that this is my receiving end voltage. Is there any other way to solve? I'm thinking with the help of a phasor. This is my receiving end voltage and I have a current that is lagging. Okay, that is phi r. Okay, so what will be the sending end voltage? Sending end voltage will be further just beyond this, right? It will be, if you see, sending end voltage leads the receiving end voltage by plus 1.82. So it will lead. Why? Because it has to supply the additional reactive power, right? So the angle between the current and the voltage further increases, phi increases, hence the power factor will worsen. This will be phi s, right? So this is my Vs. Okay, so what I can do is, how will I find this out? So what is it? Basically there is a drop of IARA, sorry, IAR after this VR, right? Because this is my circuit basically. Where did it go? This is my circuit, right? So I hope you know how to draw the phasor diagram. R plus Jx. Okay. So there will be a drop along this resistor which will be parallel to the I, like this drop is what? This is IR into R. So R is just a constant number, so it will be parallel to the this vector, IR vector, right? So that's why I'm drawing it parallel to the IR vector. IR into R. Then I will have this drop IR into J, so it will be 90 degree anti-clockwise, because I have plus j, it will be 90-degree anti-clockwise, right? All this I have explained in machines how to draw the phasor diagram. So here I am not going into the details. I am directly writing it. So it will be 90-degree anti-clockwise, and here actually this drop IR into X. Here actually my Vs will lie. Now can I find out the value of this cos phi s? Is it possible? Yes, it is possible, because if I shift this here, right, it is along this IR into R, and this VR also I can break it down into two components. This VR, sorry, this VR I can break it down into two components. So VR will have a component that is along IR. So basically this, right, VR will have a component that is along IR, that is VR cos phi R, and this drop is there, right, IR into R. So this drop is there, IR into R. These two components together actually match up to this Vs cos phi s. So if I take the projection along I, right, that will be Vs cos phi s, that will be equals to the individual Vr cos phi r plus IR R. So from here I can write Vs cos phi s will be equals to Vr into cos phi r plus IR into R. So for this actually you need the value of Vs, otherwise you will not be able to find out. So Vs actually is needed. Vs we can calculate. I will tell you the shortcut for calculating the Vs as well. So your this is magnitude of Vs, right? Magnitude of Vs, magnitude of Vr, magnitude of I, everything is in magnitude. So cos phi r, cos phi s comes out to be magnitude of Vr cos phi r plus magnitude of R, IR into R divided by magnitude of Vs. Okay. So what is magnitude of Vs? Magnitude of Vs I have derived, right, in the machines lecture there, that your magnitude of Vs is actually Vs, sorry, Vr cos phi r plus IR into R, magnitude of IR into R whole square plus so this will be equals to this. So this will be Vr cos phi r. So now if I calculate this, right, what is Vr? Vr I already know. Vr is 10 kilovolt, right? 10 kilovolt. Kilovolt, like everything is in kilo, okay, everything is in kilo, into cos phi. Cos phi is 0.8, right? What is IR? IR is, I will write in kilo, right? It is 0.255. 0.255. What is R? R is 3 ohms, right? R is 3 ohms, then plus VR. VR is 10 into sin phi r. Sin phi is 0.6 plus IR is 0.255 into j x, right? X is 4 whole square. So this will come out to be 0.255 into 3 plus 8, right? This is 8.765. So this top side is 8.765. I think this is exact. This is not even approximate. This value is exact. That VR plus IR cos phi r, that is approximate, right? This is the exact one. Yeah, this is the exact one, right? This is what I am doing, but you can simplify this with this as well, right? This is the approximate one. You calculate with the approximate one, you see how much difference is there. I am following the exact one. So this will come out to be, right, 8.675. This is 8.765. 255 into 4 plus 6. This is 7 point. This will be whole square plus 8.765 whole square whole under root. So this comes out to be 11.23 kilovolt. Okay, 11.23 kilovolt, right? So yeah, that's this voltage basically. So now, yeah, now we have got this value 11.23. I think previously also we derived the same thing only. So now I can directly I can put in this formula, right? What will be cos phi s? Cos phi s will be, the top side is 8.765 and the bottom side is 11.23, right? This will be equals to into 8.765 cos cos of this 0.78. Same answer you will get, right? No matter what, you get the same answer. So you try with approximate, that is your homework. Try with approximate. Now I will derive the power flow. I will derive the expression, because I have used this power flow equation in PSA 2, right, while explaining few things in the fault analysis. So now I will derive the power flow, right? So with the help of ABCD parameters. Okay, so I will derive the expression for receiving end power. So receiving end complex power, right? Okay, so receiving end complex power SR, right? SR will be equals to what? SR will be equals to PR plus J QR, that is equals to VR into IR conjugate. Okay, VR into IR conjugate. So what are the values? I have to write down the values of VR, IR, all these things. So I already know what is my VS, IS, right? These things are known to me, correct? From here I will derive, basically. From here I will derive. Okay, so this is for a general transmission line, any short, long. After this, I will simplify this and derive it for the short transmission line. Okay, so what is my IR? What is my IR? IR, from this equation I can get the value of IR, right? So first of all I will write the values of A, B, beta and D. Okay, So I know it will be I'm assuming that it's a symmetrical line. That is my assumption is it's a symmetrical line. Okay, and in long transmission line also will be symmetrical, and few models of medium transmission line also is symmetrical only. Okay, so assume is symmetrical. Okay, assume transmission line is symmetrical, that means your A will be equals to D, and let me write the complex values of A, B, C, D. So A will be magnitude of A, angle of alpha, let's assume that it has an angle alpha, and your B will be magnitude of B, angle of beta. Your C will be magnitude of C, angle gamma, and your D will be magnitude of D, angle some delta, or not, let's not take delta because I have told you it is symmetrical, so it will be magnitude of A, angle alpha, same only, right? And of course network will be reciprocal, but I am not going into that reciprocity condition. Without that I am deriving. Okay, so let's now derive our things basically. So what is my IR? IR will be what? Vs minus AVR. Vs minus AVR, which is magnitude of A, angle alpha, and VR has an angle of magnitude of Vs angle 0, right? And Vs has an angle of magnitude of Vs angle, so Vs will have an angle of delta, right? It will lead basically. So this will have an angle Vs angle delta, and VR, let's assume VR VR angle 0 degree. Let's assume that the receiving end side is the reference, right? So this will become Vs angle magnitude of Vs angle delta. I have B multiplied, right? I am dividing by B, so if I am dividing by B, this will be magnitude of B angle beta, and here I have magnitude of A angle alpha into what do I have? VR, right? VR is simply magnitude of VR only, angle is 0, and again I am dividing by B, so this will become magnitude of V angle beta. Okay, so your from here your IR actually becomes this will be what? This will be magnitude of Vs divided by magnitude of B angle delta minus beta minus magnitude of A, magnitude of VR divided by magnitude of B, and this will be alpha minus beta. Okay, so what will be IR conjugate, because I have to find out IR conjugate. So IR conjugate will just be the reverse of this angle, right? IR conjugate, because I'm interested in the conjugate, because here for complex power I have to take the conjugate, right? So if I take the conjugate, this sign, the angles will just get swapped, signs will reverse. Basically delta minus beta will become beta minus delta. I have to multiply a extra negative sign, so this will become beta minus delta, and this will become beta minus alpha, right? And this I will multiply with my VR, sorry, VR, right? So SR will be VR, that is angle 0, right, into IR conjugate, so this will be magnitude of VR, magnitude of Vs divided by B, angle beta minus delta, then I have minus of A divided by B magnitude of VR into angle of beta minus alpha. So now I will just compute the real and imaginary parts. This will be VR square, right? Why? Because I'm multiplying VR here, so a extra VR will get multiplied because VR is getting multiplied, so this will become VR square. Now what will be the active power? Active power will be the real part, so cos of this, right? Cos of this will be the active power. So receiving end active power will just, I will just copy this thing, right, and I will just add a extra cos angle, that's it. Okay, cos angle, right, that is beta minus alpha. So I hope that is clear now. What will be the reactive power? Reactive power will just be the sine part, right? Reactive power will just be the sine part. Okay, so these are the like equations, basically these are the general equations, right? Now I'll derive it for short transmission line. Okay, I will derive it for a short transmission line. Before that, let's take few things, let's understand few things, that what is the condition for maximum receiving end power. Okay, because what are the variables here? ABCD, right? ABCD are just transmission line parameters, those will not vary, those are constant. These are transmission line parameters, this will be constant. Okay, this will be constant, right? So now this will be constant, this is fixed. Now our receiving end voltage, right, that is, we have to keep it fixed, that is desirable. So receiving end voltage also is fixed, right? Receiving end voltage is also fixed, and generally our excitation is also fixed for a fixed excitation, because like what is this Vs? Vs is the voltage of the sending end, right? That is generated from the synchronous machine. So for a fixed excitation, right, your Vs also will be fixed. So Vs also is fixed for a fixed excitation. Okay, for a fixed excitation the Vs is also fixed, right? So now what about what about what is the variable then? What is changing? So all this alpha, beta, Vr, AB, this Vr, Vs, B, beta are fixed. Only delta, delta is what we vary, right? So delta is the variable. Delta is the variable. Delta is the only variable that we can see. So when will like, so basically the purpose is, what do I have to change if the load demand increases or decreases? That is what I want to come, because excitation will be fixed generally. So basically if load demand changes, we have to change the delta. And isn't that what we know, right? In the synchronous machine we vary delta, and we saw how the power was changing. So that's why that is the reason delta is called as the load angle. Okay, sorry, not load angle, sorry, power angle. That is the reason. So that's how the name power angle came. Okay, so now I hope it is clear how the name power angle came. And we want to like, we want to see the condition when this will be maximum. When will this be maximum? Because everything is constant, right? We want to see the condition for PR max. When will our load will be maximum? PR will be maximum when, now this is constant, only this is varying, right? Because the delta is varying. So I have to maximize this term. When will this be maximum? When this will be, cos is maximum when it is 1. That means your angle will be 0 when, so that means your beta has to be equals to delta. So your beta has to be equals to delta for maximum power. Maximum power transfer, beta has to be equals to delta, or delta has to be equals to beta for maximum power to transfer. Okay, so I hope that part is clear. to you. Okay, so now I want to uh, draw the locus of this, locus of power flow, right? Locus of PR and QR. So if I have this graph over here, right? If I have this graph over here, and this is, let's say, my PR, and this is my QR, right? It's just like, what is your complex power? Complex power is PR plus JQR, right? So we are plotting it in the complex plane basically, right? So if I put it over here, right? If I put it over here, what do I see? So what is my PR? PR is equals to this, and PSA, because I want to plot it in terms of your beta minus delta, right? Okay, cos beta minus delta, cos beta. So this is a constant term, right? This is a constant term, right? This is also a constant term. Beta minus delta, all these are constant. This is also constant. Only this is varying, right? So if I somehow eliminate this variable, I'll be able to plot my PR and QR. So what do I mean? So let me assume that this is a constant C1 and this is a constant C2, because these are not varying, right? Okay. So PR will be equals to this minus C1 and QR will be equals to this minus C2. Okay. Now I can take this C1 and C2 on that side. So this will become PR plus C1 equals to whatever this value is, right? And QR plus C2 into whatever this value is. Right. So this will be if I square both sides, right, both these two, and add them up, this will be sine square plus cos square, so this will become 1. So ultimately this will be PR plus C1 whole square plus QR plus C2 whole square equals to VS VR by B whole square. Okay. So what is this? This is simply, let's say this is x plus C1 whole square plus y plus C2 whole square equals to r square. It is just a circle, right? This is the locus of a circle. Locus of circle whose center is minus C1 comma minus C2 and whose radius is magnitude of Vs, magnitude of Vr divided by magnitude of B. Okay, magnitude of V is magnitude of Vr divided by magnitude of B. That is the radius basically, and this is the center. Okay, so you can, I hope you can draw the circle. How will the circle be? So what is your C2 and C1? So your C1 actually, oh sorry, this is negative, so this will become, no, this is fine, this is become plus, no, that is fine. So your, let's say your center is somewhere around here, C1 C2. I don't know exactly what are the coordinates C1 C2, I don't know that. Okay, so your C1 C2 will be somewhere around here, right? This will be the center of the circle, correct? And you will draw the circle from here, right? This will be the center, this point will be C1 C2, and from here you will draw, about this you will draw a circle, right? Okay, so that is what your like power flow is. It is a circle about the center C1 C2. So a graphical question can be asked, might be asked. Okay, it's good to know these things. So graphical questions can be asked, but till now they have not asked, but it's good that you understand these things. Okay, so I've already discussed about the maximum power condition, right? That is delta equal to beta. For a short transmission line, what happens? For a short transmission line, right? What is your ABCD? Now I am deriving for a short transmission line. Power flow for a short transmission line. Okay, power flow for a short transmission line. So for a short transmission line, I know that what is my transmission line parameters? It is simply one Z01. Okay, so now what I can say is that, so my A is 1, B is Z angle, magnitude of Z angle theta, right? So that is my magnitude of B and this is my beta basically, and your C is simply 0. It is very simplified. C is simply 0, right? C is anyways not required actually, only A and B are required. So here, right, your equation simplifies to a larger extent. Beta will be theta only, because theta is the this line angle, theta TL, theta transmission line, right? So your A is 1, and your beta beta is magnitude of Z, so this will be Z, this will be Z, this will be theta. I can write this as Z as well, that's not a problem, theta Z. This is what we derive, right? If you remember, this is what we derive in the machines chapter. So this is a generalized expression. This will be theta Z this will be sine of theta z, right? Okay. So I hope now it is clear. So what will be the maximum power transfer condition here? Here the delta must be equals to theta z, right? That is what we derive in the that case as well. Delta must be equals to theta z, then only maximum power will happen. If delta is equal to theta z, this becomes 0. Here also, if delta is equals to theta, if beta equals to delta, right? This becomes maximum and this becomes 0. If this becomes 0, right? If this becomes 0, then you see this negative sign is there. Negative sign is there. That means your reactive power will be leading. Okay, so here also you can see your reactive power QR is negative, hence it will be a leading, right? Load has to be leading. Okay, so yeah, I hope it is clear now. So these kind of questions will be asked to you. They will ask you this question, they will give you the transmission line, and they will ask you that tell me the power factor at which, or tell me the load angle at which power transfer will be maximum. Okay, so you will say delta equal to theta z. So you can take example, you can take any example here. Let's take example, if I have a example like if my transmission line has a resistance of 0.5 and has a reactance of J2, right? Can you tell me the value of the delta, right, for the receiving end power to be maximum? What will be the value of delta for receiving end power to be maximum? So also one more thing, alpha will be what? Alpha will be simply 0 degree, right? Because it is constant, one angle 0. So here alpha will be 0, so this will become theta z. Simply become theta z. So here I see for maximum power transfer, my delta must be equals to theta z, that is basically tan inverse x upon r. Okay, tan inverse x upon r, 2 by 0.5. Okay, so this will be equals to tan inverse 4, right? 4 tan inverse. So it becomes 75 point. Delta x actually is quite high, right? This is not desirable at all. We would never want to operate in this region because we are on the verge of instability. Okay, 75.96 degrees. Okay, so now one more thing is there. If let's say your line is purely inductive, if your line is purely inductive, what will happen? Then what will be the delta max? Then what is your theta z? It is simply r by x, so x by r, right? Tan inverse x by r. R is 0, so it is tan inverse infinity. So tan inverse infinity is pi by 2. So theta z will be 90, right? So that is what your delta has to be equals to for maximum power transfer. Okay, so I hope that is cleared. I hope that is clear, right? Okay, so I want to leave you with few questions as homeworks, because we have already derived the power transfer power flow through the short transmission line. I don't feel we have to derive anything else. This already has been derived, right? Yeah, I don't feel we have to derive this. I want to leave you with few homeworks. So try these questions. This one is the first one. This is a ESC question. This one is the second one. Okay, not that difficult. And okay, efficiency of short transmission line. So what will be the efficiency of a short transmission line? So in a short transmission line, I simply have a resistor. right? So in the previous lecture, I actually discussed about the efficiency, but this is valid. That formula was actually valid only for the short transmission line. Actually, it won't be valid for long transmission line. I made a kind of mistake there. Here I forgot to explain what is the efficiency actually. Where did it go? Where did it go? Where did it go? Yeah, here, right. So this, right, this actually is only valid only valid for short transmission line, because shunt parameters are neglected. Then there will not be any parallel current, right? Because shunt parameter are neglected. Okay, so yeah, just keep in mind. So efficiency will be same here, because load current, receiving end current and the sending end current will be same. So what is the power loss component here? Only the series resistor. Inductance cannot consume any power. So the power loss component here will be just the series resistor. Okay, so the power loss component here, if you see here, my receiving end current and sending end current is same. There is no shunt parameters, so the power loss will happen in the resistor. So it will be 3 IR square into R, and your efficiency will come out to be P L, right, load power, or the receiving end power, divided by, that is P output upon P input. Input is the power delivered from the source side, that is PR, plus the additional loss, that is 3 IR square into R into 100 percentage. So your remember here, my PR is three phase power. Okay, it is not single phase, it is three phase power. Okay, I hope it is clear. So roughly here also a few things. Okay, few things I want to discuss. That if I assume for a short transmission line only, if you assume that R is negligible, the resistance is negligible, then what does my PR becomes? If you see, if you neglect R, right, what happens? Your magnitude of Z is what? R plus JXL. So magnitude of Z becomes magnitude of X, that is X only, and your theta Z is what? Theta Z is 90. If you see here, theta Z is 90 if it is purely reactive. So this will become sine of theta Z. So this will be, PR will become this, we have already derived previously as well, that is magnitude of Vs Vr divided by X into sine delta. Okay, and your QR will be what? QR will be, if you see, theta z is theta z is 90, so this will be minus Vr square by Z by X, and this will be cos of delta, right? So Vs Vr cos of delta minus uh, Vr square Okay, so yeah, from this roughly you can say, like, if you take your VR to be common, right, VR by X to be common, this will be Vs cos delta minus magnitude of VR, right? And if you assume that your delta generally operates in the region 0 to 30 degrees, we don't go beyond 30, right? So here the approximation is your cos delta, you can approximate to be 1. So you can see your reactive power is, what is it? It is VR by X into Vs minus VR. This is 1. So it is basically proportional to delta V, and your active power is proportional to the power angle. So same thing which we discussed intuitively in the previous class, I am deriving it with the formula. Okay, so that's why reactive power is used to control the voltage and active power is used to control the power angle. I think this I have said like 10,000 times in the whole power system, right? I'm really sorry if I'm repeating, right? But this thing is very, very important. Okay, this thing is very, very important. We generally don't go beyond 30 because I know that delta 90 is the steady state stability limit. We will not, we'll never go near that because our generator will be in the verge of instability, so we don't want that. Correct? Okay, so these questions are homework. Do these questions as homework, and that's it from my end for this lecture. In the next lecture we will discuss about medium transmission lines, and also we will discuss about the, we'll do more questions, and of course we will start with medium transmission lines. Thank you and happy learning. Hi everyone and welcome back to PrepFusion. So today we will continue along with the short transmission lines. So today we will solve the questions, right? So this will be a assignment lecture, assignment 8, and also we will solve the homework questions, right? Before starting, uh, here, right, I mentioned something. This is valid for a short transmission line. Now what is the actual formula of efficiency, right? So this I did not mention. Actual formula efficiency will be equals to magnitude of Vs into magnitude of Is into cos phi s, the sending end power factor. That formula will be valid everywhere else. So it will be magnitude of Vs into magnitude of Is into sending end power factor divided by magnitude of Vr into magnitude of Ir into receiving end power factor, cos phi s and cos phi r into 100%. Okay, equals to 100%. So this, right, this formula is the general formula. General formula valid everywhere. Okay, this I forgot to mention in the previous lecture. So I'll copy and paste in the starting, right, in that particular page where I was discussing about the efficiency. Where have I discussed about the efficiency? Somewhere around, yes, here. So like because at that point of time we did not know what was the sending end power factor and receiving end power factor, right? That's why I did not discuss about it. So let me add this. Let me do this thing. Let me add this here. Now this will be for the short transmission line, right? And the general formula will be this. Okay, so this is for the short transmission line. Okay, so yeah, I hope that is clear by you. Now let's discuss about the homework questions. So let's discuss one by one. So yeah, let's discuss about this question, 10th question, right? So here it's a ESC question. So here they are telling the active reactive power delivered at the receiving end are shown. Okay, this is what we already have derived. Now VSVR being the magnitude of voltage sending and receiving end, delta being the power angle at maximum power condition, maximum of PR, uh, leading VARs goes to load for any value of VS and VR. At maximum power condition, leading VAR goes to load for any value of VS VR. Is it correct? My load will behave as leading, right? That is what we discussed at maximum power. So yes, my generator or my sending end is delivering leading power factor, or it is receiving lagging power factor. Delivering leading power factor or receiving lagging power factor, both are same thing. So option A will be correct. Let's read the other options. Leading VR goes to the load only for VS equals to VR. No, for any value of VS and VR. Here, right, we just derived. For any value of VS and VR, if you see your any value, this will always be negative, no matter what. This is magnitude of VR square divided by Z, and this sin theta Z will be something positive, because the transmission line will be inductive in nature, not capacitive, right? Because the transmission line will be inductive. That's why your transmission line, although they have not mentioned it over here, but your transmission line is inductive. If it is capacitive, then it will be opposite, but I know the transmission line is inductive in nature. That's why I will deliver leading reactive power for any value of VSVR. Just the maximum power condition needs to happen, that is delta must be equals to theta Z, right? Lagging VR, no, wrong. Lagging VR, no. Okay, this one, lagging VR goes to load for any values of VS, for any value of VS equal to VR. Lagging VR goes to the load, no. Lagging VR does not goes to the load. Lagging VR is received from the load, no. These are wrong. Option A is only the correct answer. Okay, so let's solve the next question. So we have been given this power system, and they're telling me the rating of the external capacitor that must be connected here, so that the voltage here is maintained to 1 volt, right? They're asking me this, what is the rating of the capacitor that I must connect, so that the voltage is maintained to 1 volt. Why are they telling that if I don't connect the capacitor, the voltage may not be maintained to 1 volt? Why is that the case? To understand that, let's see what is the reactive power at this node, right? So some of the reactive power will come from this. I will copy this. Some of the reactive power will come from here, right? Some of the reactive power will come from the capacitor side. Now ultimately, right, here the load reactive power is 0, because load is taking only active power. I should have mentioned here, this is only active power, right? Active power, demand of the load, active power. Where did it go? Not here. Yeah, active power. Okay, so load is taking only active power. So let me see what is the reactive power at the receiving end if I don't consider the capacitor for now, right? So the receiving and reactive power, this formula, right, we have just derived this formula yesterday only, I mean in the previous lecture only. VR divided by magnitude of X. If it's a purely inductive link, this will be magnitude of Vs cos delta. How do you remember that here Vs will come? Because Vs always will be somewhat higher, like that is the assumption. Then only there will be some drop. That's why Vs I'm multiplying with cos delta to reduce it. Then I'm subtracting for VR. So VR always will be somewhat lower than Vs. Like that is intuitively how you can remember the formula. That's it. It's just a way to intuitively remember the formula. So this will become, now for this, right, I need delta, because I know all the information. I know what is magnitude of Vs, I know what is magnitude of VR. I don't know what is delta. So for delta, how will I calculate the delta? I know that a load, right, receiving and load, that is equals to 1 pu, that is equals to magnitude of Vs magnitude of VR divided by X into sine of delta. So your delta, right, sine delta will be what? Sine delta will be 0.5. So your delta will be 30 degrees. That is what I will replace it over here. I will replace delta 30 degrees over here. So here this will become QR will be equals to 1 divided by 0.5. This will be root 3 divided by 2 minus 1. Okay, so this becomes actually root 3 minus 2. So which is actually something negative. If you see, root 3 minus 2 will come out to be something negative here. I'm just calculating. It is minus 0.268. What does it mean basically? It means that the load is receiving some leading reactive power, right? Load is receiving some leading reactive power. Someone needs to fill this void. Someone needs to deliver this because load reactive power is 0, right? But at this point QR we have derived that I am receiving a reactive power is of 0.268. Okay, someone needs to, like, what does this minus mean? Minus means that minus basically means that load has a demand of leading reactive power. What kind of load has a demand of leading reactive power? Capacitance, right? Capacitance absorbs leading reactive power, delivers lagging reactive power, right? So here, as if I have a load connected that has a requirement of 0.268 leading reactive power, but actually the reactive power is 0 for the load. So I have to connect an external capacitor that will absorb this leading reactive power, right? So what shall be the rating? So basically I have to connect a external capacitor that will absorb the leading reactive power. So rating of capacitor, power rating, because in rating, right, if they're talking about rating, they are basically talking about the power rating, not the voltage. Voltage is anyways 1 pu. Power rating, they're talking about the power rating. Okay, power rating of capacitor will be basically QC. Oh, sorry, not power rating of capacitor, not power actually, uh, because it is not active power, reactive power. Rating of capacitor will be 0.268 pu. Remember, this is in VR, this is the reactive power, right? So that is the rating basically, that is the answer. Okay, so I hope it is clear. So these were the homework questions. So now we will move on to the today's assignment questions, right? So this is the first question where they are telling us that if the sending end magnitude voltage is increased, if the sending end voltage magnitude is increased while all the other parameters remain constant, what will happen to the source power factor? So we derived the source power factor, if you remember, in the previous lecture, cos phi s for a short transmission line. It was basically in the top I had VR, like how do you remember this cos phi s? Just remember it like this, right? So my Vs is what? Vs is magnitude of VR cos phi r plus IR into R whole square plus VR sin phi r plus IR into X whole square. Okay, so your cos phi s will be what? This is the real part, this is the imaginary part. So cos phi is what? Real upon the magnitude. So real is this one, magnitude is this Vs, correct? Real is this and magnitude is this. So real will be Vr cos phi r plus Ir into R by Vs, right? Magnitude of Vs. This is what we derived in the previous lecture. So what will happen basically? They are telling me that they are increasing the magnitude of Vs. If the voltage magnitude is increased, right, other parameters remaining constant, that means load IR and R, all these will be constant, your VR has to increase, right? VR has to increase. It has no opportunity, it has no other option than to increase. So this will increase actually, VR cos phi, this has to increase because other parameters are constant, IR into R is constant, cos phi R will be constant, it is load dependent. VR will increase, right? So this value will increase, this value will be constant, but this Vs will increase. But how much will be the increase basically? How much will the increase of VR be? So because VR is coming here and here, can we determine, because both are increasing, can I say what will happen to the reactive power, what will happen to the sending in power factor? What will happen to the sending in power factor? So we can understand this in a other way as well, that if I am increasing the sending end voltage, right? Okay, if the sending end voltage is increased, this is Vs angle tilde, this is Vr, angle 0. So if the sending end voltage is increased, what does that mean? That means your delta V is increased, that means your reactive power demand will increase, right? If reactive power increases, what is the, like, cos phi? Cos phi is P upon Q, or P upon S, right? Or if I want to write in terms of tan phi, what is tan phi? Tan phi is Q upon P. Active power demand will be constant, this is constant, right? Reactive power demand has increased, so your phi has increased. If your phi has increased, your cos phi will reduce. So your source power factor will actually decrease, it will be worsened because the voltage difference is more, so the reactive power flow will be more, hence the active power is constant, reactive power flow is more, hence what will happen, the power factor will reduce. So intuitively, that's why all these are very important, you will not be able to directly solve it. Okay, so you have to intuitively understand. So here for the given circuits we have to find out the sending end, like for the given circuits they are asking us which one will have the higher sending end power factor. Okay, they are just simply asking us which one will have the higher sending end power factor, right? So how will I calculate, because we need to provide voltages, right? If I don't provide voltages, we will not be able to calculate the sending end power factor. Or I don't know. Okay, which one will have the higher sending end power factor? So what is the cos theta s that we derived? Cos theta s that we derived was Vr cos phi r, that is load dependent, plus IR into R, right, divided by Vs. So what I observe, in case of A, this is the formula, right, because R is not 0, but in case B, R is 0. So in case of B, R is 0, R will be 0, then this will be Vr cos phi r divided by Vs. So simply the numerator reduces, this also will reduce. So your sending end power factor will be lower in the second case than in the first case. Okay, so your sending end power factor will be lower in the second case than in the first case, right? So this will be the part B, this will be the part A. So your answer will be cos phi SA will be higher than cos phi SB. Okay, so if the line is purely inductive, then the power factor worsens in case of a sending end power factor will worsen basically. Okay, that is the answer. Let's now solve the next one. A short transmission line has per phase impedance of this, right? The sending end line to line voltage is 3.8 kilovolt. Okay, per phase impedance they have given me transmission line, short transmission line. So it has a resistor that is 0.2 ohms, and it has a inductance that is J 0.45 ohms. Okay, and the sending end voltage is 3.8 kilovolt. That is what they have given me, 3.8 kilovolt, and the receiving end voltage is 250 kilowatt per phase. Receiving end power, receiving end load is receiving 250 kilowatt per phase. It is a per phase, right? It is per phase. So I have a load connected, right, that is receiving 250 kilowatt at a power factor of 0.8. Okay, so calculate the receiving end voltage. They are asking us to calculate the receiving end voltage. What is the receiving end voltage? So I know what is the receiving end power, right? Or I can use the current formula. That also I can do. But with, okay, because delta is not given, I don't know what is delta, so it will be foolishness to use that formula, because again it is not a purely inductive link. So I will not use that power is VSVR by X sine delta, because it is not a purely inductive link, right? So I will simply use basic formula. What is your magnitude of Vs? Magnitude of Vs is under root magnitude of Vr into cos phi r plus IR whole square plus sin phi r plus IR into X whole square. So I know what is my IR, right? Do I know IR? I don't know IR. Okay, I don't know what is my IR. So it will be difficult. So this will be difficult. Let me think of any other way. So is there any other way? Okay, so I can use a KVL, right? So I know what is my VS. VS will be VR angle 0 plus this R plus JX 0.2 plus J 0.45 into IR. Do I know the current? I actually don't know the current. I don't know current. So this will be IR. This is also complicated. Everything is complicated. Okay. Everything is complicated. But I think this one will be a bit simpler than the previous one. Both are same only. Won't matter. Okay. Okay, what is my IR? Magnitude of IR. Magnitude of IR will be, this is a per phase power, right? 250 per phase. So 250 divided by magnitude of VR into cos phi basically. VR cos phi into cos phi is 0.8. Right? So 250 divided by 0.8. So this comes out to be 312.5 magnitude of VR. Okay. Okay. I know cos phi r, sin phi r, all these things I know. If I replace it over here, I will be able to find out my VR. So here, right, Vs I know, Vs is 3.8 kilovolt. VR is also in kilo. So kilo, right? This is in kilo, this is in kilo. So current is in amperes. But that won't be. VR is in kilo, right? Kilo. This will be in amperes, but amperes won't be. I have to divide by another 1000. Or let me keep it. No, let me keep it kilo. I have to divide by simply 1000, right? Because I want to make it in kilo amperes. So this will be 0.312 per magnitude of VR kilo amperes. So in this case, we are actually stuck, right? We are stuck. This will be very difficult for us to solve. So in this case, we have to use that approximate formula. What was the approximate formula, right? The approximate formula, if you remember, my Vs was equals to VR plus IR cos phi r plus I into x sin phi r. Unfortunately, we have to use this approximate formula. Okay, there is no other option. Otherwise, this will this will be like, it will take a whole day to solve this. Now, one more mistake I have done here. Remember, here they have mentioned line to line voltage, right? If they have mentioned line to line voltage, nothing is mentioned, so you will assume that it is a star connected transmission line, is always star connected, or generator is star connected, right? So here I have to divide by an extra root 3. I forgot to divide by extra root 3. Okay, my bad. So here this will be 3.8 divided by root 3 equals to VR. VR is what? VR I have to find out, right? IR is what? IR is this value, right? 0. Everything is in kilo amperes. 0.3125 divided by 0.5, and R, it is basically R cos phi r plus X sin phi r. R is how much? R is 0.2, cos phi is 0.8, right? Plus X sin phi r, X is 0.45 and sin phi r will be 0.6. Okay, so this value will be equals to 3.8 divided by root 3, so 2.912, something like that. This is 3.8, right? Yeah, 3.8 divided by root 3, 2.194 into VR. I'm multiplying VR on both sides. This will be VR plus, now what will be this value? This will be VR square, because I multiplied by VR on both sides. So this, right, will be 0.2 into 0.8 plus 0.45 into 0.6 into 0.3125. Okay, so this will be 0.134375. Okay, so your VR square, right, VR square minus 2.194 VR 134,375 equal to 0. Okay, yeah, so now I can solve the quadratic equation. From this I will be able to find out my VR. I will neglect the negative solution because negative is not possible, negative VR is not possible, right? It will not be exact value, right? It will be approximations, but we have to go by that. We will not be simply able to solve it, right? Okay, so first of all we have to find out the receiving end voltage. So receiving end voltage will be this. I have to solve the quadratic equation. This will be VR, this will be minus B, so 2.194 plus minus B square, that is 2.194 minus 4 AC divided by 2A, right? That is basically 2. So this will be 2.194 whole square minus 4 into 0.134375 whole under root, and there are two solutions here, right? Two solutions, plus minus 2.06788 divided by 2. So which one will you choose? So your VR, I'm only talking about the magnitude of VR, right? VR will come out to be this, right? Plus 2.194 divided by 2, that is 2.131 kilovolt, or there is another one, 8 minus 2.06788 divided by 2, so that is 0. 063 kilovolt. Okay, which one will you choose? So this is too low, right? This can't be possible. Too low value. How can the voltage go this low? So of course you will choose this one. This is the nearest one, near the 2.313, near your phase voltage, right? So this will be the correct answer. This will be the correct answer. Your voltage, receiving end voltage will be 2.313 kilovolt, angle 0. Okay, per phase voltage is this. That is what they have asked. They have asked us the receiving end voltage. Now I will compute the line voltage. Receiving end line voltage, it will be just root 3 times this, right? So root 3 times 2.131, so it comes out to be 3.691 volts. Okay, that is what it comes out to be, 3.691 volts. Okay, I hope it is clear. So now this is the answer basically. Let's solve the second part, right? Second part, what they are asking, second part they're telling the line current. What will be the line current? Line current is very simple, right? It is simply power upon, because it is single phase load, I will not divide by root 3. It will be power upon V cos phi, right? V receiving end, line to line receiving end, by cos phi, right? So the power is how much? Power we already know, that is 0.3125, right? And here here there will not be any root 3 because this power is single phase power. If this power was 3 phase power, then there would have been a root 3 over here, but this is a single phase power. This is a single phase power, so here I will have a phase voltage. I will not have the line voltage because this is a per phase power. per phase power. Okay, so this divided by the VR, that is 2 point, remember this is kilovolt, 2.131 into cos phi. Into cos phi. Cos phi is zero point 0.8, right? Power factor is 0.8 kilo amperes, right? It is in kilo amperes. I can write this in amperes as well. I just have to multiply by 10 cube. So this 0.3125 divided by 2.131 divided by 0.8 into 1000. So this comes out to be 183.3 amperes. Okay, 183.3 amperes. So yeah, now now this is a line, this is a line current basically, that is that. Now what else they are asking? They are asking me, I guess they are asking the efficiency of the transmission line. It is a short transmission line, so I can use the simple formula, right? Efficiency will be single phase efficiency, right? Single phase, everything is in single phase, so I will not multiply 3 I square by r, I square r. I'll just multiply I square r. I'll just add I square r, not 3 I square r, because all the power is in single phase. So it will be P out upon P in, that is into 100, that is equals to P out is divided by P in. P in is 250 into 10 cube plus the losses that I need to supply. It as it is a per phase equivalent, I will just multiply I square r. I will not multiply 3 I square r. Okay, per phase, right? Into 100. So into 10 cube divided by plus I square r. So I square into r. R is how much is r? R is 0.2, right? Divided by 10 cube, 6.72. This comes out to be 6.72 into 10 cube, right, into 100. So your efficiency, right, will come out to be this plus 250 into 250 into 100, 97.38. So your transmission efficiency comes out to be 97.38%. Okay, so that will be the answer for this particular question. I hope everything is clear. We had to use this one, right? We had to use this approximate formula. So sometimes this approximate formula can bail you out, okay, especially in gate examination. And I don't think this question will be asking gate, but if this, something like this gets asked, right, where you are stuck, so use the approximate formula. So that's why knowing everything is actually kind of important, okay. So let's now move on to the next one. So in this next question, we have a 3-phase short transmission line. Per phase resistance is 4 ohms and your reactance is 6 ohms, right? And your sending end voltage is 110 10 kilovolt, your receiving end voltage is 100 volt line to line. Okay, these are all line to line voltages. They are telling me these are line to line voltages corresponding to a load operating at 0.8 power factor. Okay, so I have, first of all I have to write the per phase equivalent. So this will be 110 divided by root 3, right? So here the per phase equivalent will be 110 divided by root 3. What is 110 divided by root 3? So this is 63.5. Okay, and the receiving end voltage is 100 kilovolt, line to line also. So 100 kilovolt divided by root 3, this will be 57.73. Now angles are not given. Whenever this delta angle is not given, right, you have to use the approximate formula. You don't have any other option. So I will tell you in this here, right, I will make a note of it here. Whenever Vs delta is not given, so where is that voltage regulation? Here, right here. Approximate formula. Use this if delta is not given. And R is not equal to 0. If R is equal to 0, then it becomes simpler. We will use that Vs Vr by x sine delta, that formula, right? But if R is not equal to 0, it becomes a bit tedious. So use this formula, right? If delta is not given, use this formula. Okay, approximate formula. So yeah, let's now move on to the next one. Basically, the same question. Let's now move on to the solution. Okay, so here, right, output power, they are asking me what is the output power. How will I calculate the output power? For calculating the output power, I need to calculate the current. I need to calculate the current. So how do I calculate the current? So I know this formula, that Vs equals to Vr plus IR R cos phi r plus IR into x sin phi r. Okay, so okay, I know Vr, I know Vs, I know power factor. Power factor, they have told me power factor is 0.8. Cos phi r I know 0.8, right? 0.8 lagging. So I just need to find out IR. I will be able to find out the load current from here, right? So what will be the load current from here? So Vs minus Vr, right? So 63.5 minus 57.73 divided by R cos phi r. R is how much? 4. Cos phi is 0.8 plus 6 sin phi r 0.6 equals to my IR current. So plus 63.5 divided by 4 into 0.8 plus 6 into 0.6. Okay, so yeah, your IR current comes out to be 0.8477. Remember, all these are in kilovolts, right? All these are in kilovolts. So this also will be in kilo amperes, right? Because this is not in kilo, this is in kilo, right? So this is actually IR is actually 0.8478 kilo amperes, right? So it is actually equals to 847 kilo amperes. Okay, so IR is actually equals to this. This is what my receiving end current is equals to. So that is the first part of the answer. But they are actually asking, not they are not asking IR, they are asking the power. So what is power? So power will be V into I into cos phi, per phase power, right? Per phase power. This is the per phase power. For three phase you will multiply 3, but they have not mentioned what kind of power they want. So I am assuming per phase power, or they are telling three phase. So I will write both the powers. So Vi cos phi, Vi cos phi will be what? V phase into I phase. V phase is this much, right? 50 load power. So load voltage is how much? 57.73. Load current is how much? 0.8478 kiloamperes. So I am writing in mega. So 84 into cos of phi. Cos of phi power factor is given to me 0.8, right? So this into 57.73, just hold on, 0.8478, 57.73 into 0.8. So this comes out to be 39.155 megawatt. Okay, so that is what my per phase power is. What is the three phase power? Just simply multiply it by 3, right? So three phase like load, three phase power will simply be 3 times 39.155 megawatt. So this comes out to be into 3, so 117.464 megawatt. Okay, so this will be the three phase power basically, right? Now what else they are asking? This is the answer for the first part, right? What else they are asking? They are asking the sending end power factor. What is the formula for the sending end power factor? It is cos phi s will be magnitude of Vr cos phi r plus IR divided by Vs, right? Magnitude of Vs. So this will be okay, so I know what is my magnitude of Vr. Magnitude of Vr is 57.73 into cos phi r. Cos phi r is 0.8. IR I already know, that is in kiloamperes, that is 0.8478 into R. R is I think 4 ohms, divide by, all these are approximate results. Vs we have calculated, sorry, Vs they have given us, that is 63.5. Remember, like here, right, actually you cannot put here line voltages, you have to put phase voltages because your current is there, right? You cannot put line voltages. Okay, just be careful while using this power factor formula. So yeah, 63.5. So everything is in kilo. This is also in kilo, this is also in kilo, this is also in kilo. So this right will come out to be 57.73 into 0.8 plus 0.8478 into 4 divided by 63.5. So cos phi is 0.78. So your sending end power factor will be 0.78 lakh, because of course your load, like inductive load, is connected. So it will be 0.78, somewhat worse than the receiving end power factor. What is the transmission efficiency? So again, the transmission efficiency, right? It will be basically the load power, right? Single phase load power is 39.155 megawatt. Okay, 39.155 megawatt divided by the load power, that is 39.155 megawatt plus the line losses. As this is single phase power, I will not write 3, I will write I square R, right? I square R, and I will put I in kilo amperes. So kilo whole square will be mega, because this is in mega, so everything must be in mega. So this will be 39.155 divided by 39.155 plus I square, or I in kilo is 0.8478 whole square into R, R is 4 ohms, right? R is 4 ohms. Okay, so yeah, so this will be 0.8478 whole square into 4 plus 39.155, this into 39.155. so this is in, of course I have to multiply 100, don't forget the 100 in percentage. Right, so this will come out to be, like, this is actually not that good, 93.16 percentage. Okay, that is the answer, that is the transmission efficiency. Okay, so these kind of questions will come if they ask from start. These are the like toughest one that I'm taking. Questions will be easier side only. We're not solving it because questions will be on the easier side only, don't worry. Okay, trust me, don't worry. So this is the next question. A single phase 11 kV line, transmitter line of length 15 kilometer is used to transmit this much amount of load kVA, load of this kVA. The line has inductive reactance of this much per kilometer and resistance per kilometer, right? And the length is given. So I can lump, right? Because your resistance is divided throughout the line, I can lump the resistance and reactance because it is a short transmission line. For a long transmission line, you will not be able to do this. So overall resistance of the line, right, because it is a short transmission line, because length is 15 kilometer only, will be 15 into 0.6, right? 15 into 0.6, that is 3 by 5. So it is 9 ohms. 15 into 0.6, so it is 9 ohms. Right, and then we have this reactance. Sorry, this is the reactance only. 9 ohms is the reactance, and the resistance is 0.25. So 0.25 into 15, 3.75. Now this is my short transmission line, and 11 kilovolt, single phase 11 kilovolt. 11 kilovolt generally is called as the rated voltage at full load, right? 11 kilovolt, and nothing is mentioned, so I will assume this to be star connected, so it will be 11 kilovolt divided by root 3. Okay, I'll assume this to be 11 kilovolt divided by root 3. So they are asking me to find out the voltage regulation at different power factors. So what is the exact formula for voltage regulation? If you remember, what was the exact formula for voltage regulation? VR, right? It was equals to okay, it is delivering a load of 500 kVA. Will I be able to find out the magnitude of IR? Yes, I will be, because VR is what? VR, if you remember, it was divided by the full load receiving end voltage, right, into the current, the operating current, into R cos phi R plus X sin phi R. This was the exact formula. It is not approximation. This was the, sorry, this is the approximation only. Yeah, this is the approximate formula basically. Of course, you can do it using the exact one. We will see. We'll try to solve with both exact and the approximate one. How much are we further from the exact formula? We'll see. First of all, I'm solving using the approximate formula. Okay, so here, right, what it will come out to be, this will come out to be, what is IR? IR is basically S, right? It is a three phase, it is a, okay, it is a single phase. Okay, sorry, it is a single phase transmission line. So sorry, so there will not be any root 3. It is a single phase. We are accustomed to three phase. It is a single phase. Simply my current, right, will be S, apparent power by the voltage. Okay, so apparent power will be 500 kV divided by the voltage, that is 11 kilovolt, right? kVA. So current in amperes, it comes out to be 500 divided by 11. So this will be 45.45 amperes. Okay, so this will be this will be 45.45 amperes. Yeah, so now I can solve this, right? So 45.45 amperes divided by the full load voltage, that is 11 kilovolt, that will anyways be there, into, so here, right, this has to be multiplied by 100 percentage. Sorry, into R cos phi R. What is cos phi? Cos phi is given to me, okay, cos phi in the first case, it is 0.75 lagging, right? So in the first case, cos phi R is 0.75 lag. So what is my sin phi? So 0.75 lag, right? 0.75 cos inverse sine of this. So this will be 0. Sin phi R will be 0.66143 lead. Okay. Sorry, not lead, sorry, lag, whatever. Okay. So 0.6646, right? Now I can easily find out the this voltage regulation. So 3.75 into cos phi R, 0.75 plus x. into sin phi r. Sin phi r will be 43. Okay. So this value will come out to be this value 45.45511, sorry, this rate into 3.75 into 0.75 plus 9 into 0.66143, this into 45.45, this divided by 11 and divided by 10. So it comes out to be 3.6 percentage, right? Let's now find out the exact value. How will I find out the uh, exact value? So to find out the exact value, you have to compute the Vs, right? Because for a short transmission line, I have derived that the Vr no load is simply equals to the receiving end, sorry, sending end voltage, right? No current is flowing, so simply whatever is the voltage here, same voltage will appear across it at no load. So what is Vs? Vs, the exact formula for Vs is Vr cos phi r plus I into r, IR into r whole square plus Vr sin phi r plus IR into x whole square. Okay, so now here what you will do, you will so what is my Vr is 11 kilovolt, right? Into cos phi r, that is 0.75 plus IR, right? IR into r, IR in kiloamperes, that is point, okay, this will be very low actually, 0.005 into r. R is 3.75. Okay, plus VR. VR is VR is this one, right? 11 into 0. What is sin phi? Sin phi is 0.66143 plus IR. IR is again 0.0455. IR is actually pretty low value. Yes, okay. Into x. X is 9, right? Okay, this will be a task. Okay, so this value comes out to be 0.0455 into 3.75 plus 11 into 0.75. So this comes out to be 4206 and 0.0455 into 9 plus 11 into 0.66143. Okay, so 7. 523 whole square, right? So your VR plus 8.420.625 whole square, 1 under root, this comes out to be 11.4 kilovolt. That is what my VR no load is. Okay, here, right, we actually did not calculate VR no load, so I will directly calculate the voltage regulation now. Voltage regulation will be VR no load, that is 11.4 minus VR full load, that is 11 divided by 11 into 100%, right? So it will be minus 11 divided by 11 into 100. So it actually almost comes out same, right? 3.64%. Here it was 3.6%. So turns out you can approximate it, right? If your power factor is near unity, if the power factor is near unity, this approximation will definitely work. So here also it will work, here also it will work. Okay, so for leading I will solve for, okay, for all the above cases I will solve only. Okay, for leading, right, again, like this is also not that lengthy, right? It's very simple actually, not that lengthy, not that lengthy. So what will be the exact value? So exact VR no load, right, for leading load. If load is leading, right, this sign will go to negative. I have taught this in machines. So I will not explain how this goes to negative. So simply what will happen, everything will be same, just this sign will go to negative, right? Because your power factor cos phi r is also same, right? Sin phi r also will be same only. Cos phi r is same, just it is leading instead of lagging, it is leading. So your sin phi r will be equals to 0.66143. Okay, so here instead of plus it will be minus, that's it. Okay, how I'm not explaining, already has been explained in machines. So this value will remain same, right? This will be what? This will be same as the previous one. This one 8.42, right? This will be same 8.42 whole square. But what about this one? This one will change actually. So this one will be VR, right, 11 into 0.66143 minus, it will not be plus anymore, it will be minus into 0.0455 into 9. So this becomes 6.86623 whole square. So your no load voltage will actually now reduced, right, because the load is leading, so voltage regulation will improve. You will see voltage regulation will improve, so there will be lesser voltage fluctuations. 8.42 whole square whole under root, so this becomes negative. I mean your no load voltage is less than full load voltage. That's why, like, this phenomena we know, right? In case of leading load, the no load voltage is lower than the full load voltage. That's why your voltage regulation comes out to be negative. Okay, so what will be your voltage regulation? It will be 10.865 no load minus full load divided by full load into 100%. Okay, so minus 11 divided by 11 into 100, so it comes out to be minus 1.23%. Of course negative, we have, like, we have seen this in the graph. Voltage regulation for leading loads comes out to be negative, right? So that's why here voltage regulation will be negative. For unity power factor, simply your cos phi r will be 1 and your sin phi r will be 0. So if your sin phi r is 0, this is gone. Sorry, this is gone, right? Only IR into X is there. This is simply gone. Okay, so your VR no load, right, will be equals to 11 into 1 because it is unity power factor plus IR into R. I is 0.0455 into R, that is 3.75. And this will be 11 into 0 because sin phi r is 0 plus into 9. Okay, so 0.45 into 3.75 plus 11, so this becomes 11.17, right, whole square plus this will be very low value, 0.0455 into 9, so this will be 0.495 whole square, this square plus 11.17 whole square. You can do it using the approximate formula as well, right? Your voltage regulation will be positive, but it will be very near to 0%. That is what we want, right? You can verify this using the approximate formula as well, right, whether they are matching. So most cases when your power factor is near unity, right, your approximate formula will match. Okay, so voltage regulation will be percentage, it will be 11.1775 minus 11 divided by 11 into 100%. Okay, so this minus 11 divided by 11 into 100%, so it comes out to be 1.613%. Okay, which is better actually. 1.613% is better. So this is the answer basically for all the three cases. You verify this with the approximate formula. Let's now move on to the next one. So what are they asking? They are asking a three-phase overhead transmission line has the following ABCD parameters. Okay, it does not seem like it is a short transmission line, because for a short transmission line your C is 0, but C is a finite value. C is a non-zero value. Okay, what are they telling? Under no load conditions, a shunt reactor is connected at the receiving end. Okay, under no load condition, a shunt reactor is connected at the receiving end voltage to ensure that the magnitude of the receiving end voltage is same as the magnitude of the sending end voltage. Determine the ohmic value of the shunt reactor. So basically I will have the transmission line here, right? Transmission line is here somewhere, it is a black box, I don't know what kind of transmission line is there, right? It has ABCD parameter, it has supply voltage Vs, it has receiving end voltage Vr, and they are asking me, I am drawing the per phase equivalent, right? What is the parallel capacitor that needs to be connected so that this Vr and Vs are equal, right? So let's see, like, what is the power, because they are discussing at no load, right? Under no load condition, at no load what happens? At no load we know that your power, right, receiving end power is 0, because it is operating in no load. It will not consume any power, it will not consume any power at no load, correct? So it is not consuming any power at no load. Now what is the formula for power using ABCD parameters, right? Don't worry, a summary will be there at the end of this whole chapter, that what formula you need to remember. So here, right, what is the power? If you remember, few things you have to remember. Normally it is VSVR by X sine delta, right? But sine delta, how did delta came? Sine delta, it was 90 minus delta, so there is cos, because it is real, there will be cos, and there will be magnitude of Vs, magnitude of Vr, right, divided by this will be magnitude of B, right? And here cos, it was beta minus delta plus VR whole square, or it was negative minus only, I believe. It was minus only, right? Yeah, it was minus. Here there was magnitude of VR whole square, and to compensate that there used to be magnitude of A. Divide by B will be common, and this will be again cos of, this time alpha minus, sorry, beta minus alpha. So how do we verify this? Verify this using the short transmission line formula, right? So in short transmission line, your A is simply 1, right? And your alpha is 0, it is real, and beta is 90, right? If it is purely inductive, right? So this goes away, only this one is there, so it is 90 minus delta, that is sin delta, and this B becomes x, so Vs VR by x into sin delta. So that's how you can verify this. So this will be whole square, and unfortunately you have to remember this, every time you will not be able to derive this. So this is 0. If this is 0 and your sending end and your receiving end voltage also, it is mentioned in the question, it is equal. So from here I can directly say that my this also will get cancelled, right? This will get cancelled. So cos of beta minus delta, delta is given to me, no, delta is not given to me, but beta value, beta is 90, beta is 90, so cos of 90 minus delta, VR and Vs are equal, so simply this will get cancelled, will be equals to magnitude of A. Magnitude of A is simply 0.9 into cos of beta minus alpha. Alpha is 0 and beta is 90 again, right? Am I correct? Yes. So what has to be your delta, right? What is your delta value? That is what I want to calculate. What is my delta value, right? So okay, sin delta. So this has to be 0 basically, because this is 0, right? So sin delta has to be equal to 0. So delta has to be equals to simply 0. So now I will calculate what is the receiving end reactive power. Now it is operating at no load, that means the receiving and reactive power must also be 0, correct? Receiving and reactive power must also be 0. But let's see, if the capacitor, if the like shunt reactor, it is a shunt reactor meaning it is inductor, right? Or whatever is capacitor or reactor, we'll see. So it is not present, then what is the receiving and reactive power? Receiving and reactive power, what was the formula? Vs VR divided by magnitude of B into sine of beta minus delta minus A into magnitude of VR square divided by B into sine of beta minus alpha, right? This was your receiving end power. Here your beta is 90 and this is also 0, right? Reactive power, receiving and reactive power should be 0, but if I assume that currently, let's say it is not 0, okay, let me see what is the receiving and reactive power with the given conditions. So VSVR are equal, right? VSVR are equal, the values are not given to me, okay. So VSVR are equal, so it will be simply VR whole square divided by magnitude of B. Magnitude of B is 200, okay, 200, right? I can take this common. This will be sine of beta minus delta. Beta is 90, so this will be cos of delta, and delta is 0, right? Delta is 0, so this will be simply, okay, let me not do this much simplification. 0.9a into sine of 90. Sine of 90 is 1, right? Because it is beta minus alpha. Beta is 90 degree and alpha is 0 degree, so this will be 1, right? So from here I can see that cos delta is 1, right? Cos delta, because cos 0 is 1. So what comes out, that it comes out to be VR whole square divided by 2000, which is not equal to 0. That means what? The receiving end is receiving some lagging reactive power. But you have told that you are not connecting any load, so QL has to be 0. So someone has to absorb this lagging reactive power. Can capacitor absorb lagging reactive power? No. Capacitor can absorb leading reactive power. It can deliver lagging reactive power. You saw in some place negative sign was coming. When this negative sign came, we told that we have to connect a capacitor. But now this is positive. So some load needs to be connected that can absorb this lagging reactive power so that our conditions match. Otherwise, our condition will not be matched, because at no load the reactive power must be zero, right? At the receiving end. So load must be able to absorb lagging reactive power. Okay, so what kind of load absorbs lagging reactive power? It is inductor, right? That's why they have to ask us what is the value of shunt reactor. Why is it called reactor? Reactor because it can absorb reactive lagging reactive power. That's why it is called reactor. So why is it called reactor? Because inductor is a called shunt, inductor is a called reactor because it can absorb lagging reactive power. Okay, okay, so we have to connect a inductor whose induct reactance is, let's say, XL, right, and whose voltage will be VR in the load side. So what is the reactive power consumed by that? It will be V magnitude of VR whole square, right? All this form, the simple things, I hope you know what is the reactive power consumed by the reactor by XL, right, which should be equals to the, which should balance out this reactance, right, which will consume this reactive power so that the load side receiving side reactive power is 0. So that will be equals to this VR whole square divided by 2000. So from here I can directly say the shunt reactance value will be 2000 ohms. This will be the answer. Okay, some similar question we have solved in the starting of today's lecture. Now this is just the opposite one. Okay, like some more similar kind of questions we have. Three more questions we have. We will solve these three questions. So here, right, we have a single phase 50 hertz system supplies an inductive load of 5000 kilowatt at 0.8 lagging 25 kilometer line. L and C are given, VR is given. Calculate the voltage regulation and transmission efficiency. I guess we have solved something like this, right? Still we can solve again. So overall, what is the, it is a short transmission line, right? Why? Because it's a 25-kilometer line, so that's why it is a short transmission line. And anyways, they have only given R and L, right? They have not talked about capacitance, so of course I have to ignore the capacitance. So what will be the resistance value? It's a 15-kilometer line. So if I do, so it was not 15, sorry, 25 into 0.0195, it comes out to be 0.4875 ohms. And your reactance, right, L is given, okay, 50 hertz. So reactance will be what? XL will be what? XL will be omega times L into obviously the length, right? L1 is the inductance per unit kilometer. So it will be 0.63 into 25 into 2 into pi into 50 divided by 1000. So that comes out to be 4 point. Actually, it is very high. The reactance is quite high. It is 4.95 ohms. Okay, so 4 point 4.95 ohms. Okay, so yeah, that is the case over here. Now they are asking me the voltage regulation and the transmission efficiency. Use approximate result, right? If they are telling me to use the approximate result, I will use the approximate result. Okay, power factor they have told me. Oh, power factor have not been told to us. If the power factor is not told, okay, power factor is told, right? 0.8 lakh. Yeah. So what is the current? It's a single phase line again. So single phase, the current will be simply V by P by V cos phi, right? So power is 5000 kilowatt, that is 5 into 10 raised to power 6, divided by V. V is 10 into 10 cube into cos phi. Cos phi is 0.8. Okay, so this will be 5 divided by 10 into 10 raised to power 3 divided by 0.8, so 6 to 5. Okay, 6 to 5 amperes. 6 to 5 amperes is the current basically. So we have to use the approximate result. So what will be my voltage regulation? Voltage regulation will be simply IR into R cos phi R plus X sin phi R divided by VR into 100 percentage. So this IR divided by VR, V is 10 raised to power 4. So this value comes out to be 0.06 and I'm multiplying by 100, right? So this will be 6.25 into R cos phi R. R is 0.75 into cos phi R. Cos phi R IR is 0.8 into 4.95 sin phi R. Sin phi is 0.6. Okay, so this, right, 0.4875 into 0.8 plus 4.95 into 0.6 into 6 point. Okay, it is actually quite high, 21 percentage. Actually it's very bad, 21%. Okay, this actually is pretty bad, right? 21%. Okay, voltage regulation is 21%. What is the efficiency? Single phase load, so it will be simply P out is 5000 kilowatt or 5 megawatt divided by 5 megawatt plus the I square R loss, right? I will be in kilo because kilo whole square will be mega. So 0.625 whole square into R. R is 0.4875 into 100 percentage. So this will come out to be 0.625 whole square into 0.4875 plus 5 into 5. Okay, so this will come out to be 96.33 percentage. 96.33 percentage is present in option A. So for the first one, option A is correct. Now it is a common data question, so second one also is same only, but in the second part they are asking me find the efficiency and the value of the capacitor to be connected across the load if the voltage regulation is 50% of the above case. So now they are asking me what is the efficiency, the new efficiency, and the new value of and the value of the capacitor that I need to connect across the load, so such that the regulation is 50% of its previous value. Basically I want to reduce the regulation, so I want my regulation VR to be 50% of its previous value, that is 21%. It was previously 21%. I want it 50%, that is 0.5, that is 10.5 10.5%. I want my voltage regulation to be 10.5%, right? This is what I want my voltage regulation to be. So if I want my voltage regulation to be this value, so how will I get this voltage regulation? How will I get this voltage regulation? Right? So the active power that the load consumes will be same. So I have a load here, right? So this is the transmission line basically. This is my 4875, 4875, 4.95, and I have a load connected over here, right? And that load takes a power of 5 megawatt, right? 5 megawatt at a power factor of 0.8 lakh. Now they're telling me what is the capacitance value that I will connect here such that the voltage regulation becomes 10.05%, right? So for this case, right, the power factor will change, correct? The power factor will definitely change here because the power factor that I will observe now will change. It will improve further because I am connecting a capacitor. It will further improve, right? Active power will remain same, 5 megawatt. Capacitance will not take any reactive power. So I know what is the voltage regulation formula. What is the voltage regulation formula? So voltage regulation formula 10.05%, that is 10.5 divided by 100 is basically equals to IR. Okay, what is the current will change? Will it change? IR divided by receiving and current. So this receiving and current will not change, right? This will remain same. So IR we have already calculated. IR divided by VR is what? 6.25 in percentage, right? So but it will be 6.25 divided by 100 actually into R cos phi dash. R is 0.4875. I'm just using the previous formula. Just the power factor has not changed. The power factor that I'm observing here has changed because this reactance is there, right? This reactance is there. Actually, your IR also will change, right? Your IR also will change. Your IR also will not remain same because like from here I'm observing from here now. So what is happening over here? My voltage regulation is reduced. So the current, right, will also change because I'm connecting an additional component here. So current will change. Current will now become IR dash. And your power factor also, receiving and power factor will also change because of course I am connecting of course the load power factor is still same, but as I am connecting a capacitor, it will improve the power factor, right? So this also will become cos phi dash. Okay, but the voltage is fixed. Voltage and the active power is fixed because the active power the load will take, this will not consume any active power, this will consume active power, that is 5 megawatt, and the voltage at this receiving end side is still fixed, that is 10 kilovolt, right? Yeah, 10 kilovolt. So this side voltage is fixed 10 kilovolt, right? But these two things are variable. So what do I know? I know what is my IR dash. IR dash will be power, active power 5 into 10 raised to power 6 divided by the voltage 10 kilovolt into cos phi dash. Now I don't know what is the value of cos phi dash, right? I don't know this. I don't know what is cos phi dash. Now what is the formula for voltage regulation? What is the formula for voltage regulation? Voltage regulation is IR dash because the current has now changed by VR into R cos phi R plus X Sine phi r. Okay. So now uh, oh, this also will change, right? This will be cos phi r dash sin phi r dash. So okay. So what is my IR dash? IR dash is this well, right? This 5 into 10 raised to power 6 divided by 10 raised to power 4. So ultimately this will become basically 5 into 10 raised to power 2, right? Basically 500 divided by cos phi r dash, right? This is phi r. So if I replace this right over here, VR I already know that is 10 kilovolt, right? Into, if I take this cos phi r dash in the inside, this will be r. R is 0.4875, right? Cos phi r gets cancelled, plus x, right? X is basically 4.95 into, of course there is 500 is outside, divided sin phi r dash divided by cos phi r dash, that is basically my tan phi r dash, right? And this is equals to my voltage regulation, correct? That is 10.5 divided by 100, right? This is equals to my voltage regulation. So from here I can easily find out what is my tan phi r, right? So this will get cancelled. Here two zeros will go and another two zeros will go there. So ultimately this will be 0.4875 equals to 10.5 divided by 5. So this comes out 5 minus 0.4875 divided by 4.95 tan inverse. So your phi r comes out, right, 18.04. What is your cos phi r? So your new power factor, right, improves a lot. It improves a lot. Who is helping it improve, right? That capacitance. That capacitance is actually helping it to improve. That capacitor is delivering the additional lagging reactive power to this load, so that the load does not, so that the supply does not have to deliver this, so that the power factor here improves, so that the voltage at this node is increased. So now practically I am showing you with calculations how we actually improve the voltage regulation by connecting a shunt capacitor. But actually what they have asked me the value of the capacitor and the efficiency, right? So value of the capacitor. So I know cos phi r, I will be able to find out my I dash. I dash will be simply this 500 divided by cos phi r, that is 0.95. So this into 500, it will come out to be 525.86 amperes. Okay, that is what your current is equals to. That is what your current is equals to. Now uh, this current what is the angle? Angle is minus of cos inverse, because it's a, now is it lagging? Still it will be lagging, because how can I say it is lagging? Because your voltage regulation is positive. As your voltage regulation is positive, it has to be lagging. So still it will be lagging only. Okay, so current will lag the voltage. So minus of cos inverse 0.95, that is 18. Okay, so this will be 525.86 minus 18. So here, right, my, what I can say, what can I say, what can I say, what can I say? So this, right, is combination of two currents. One is the load current, another one is the capacitor current. So what is capacitor current? IC. IC will be simply equals to V upon J omega C. Correct? VR. And load current, what is the load current? Already know what is the load current. What is the load current? Load current is the previous current only, right? That will not change. So load current previously was 625 ampere, and angle is cos inverse minus of 0.8. Sorry, minus of cos inverse 0.8. So 625 angle will be minus of cos inverse 0.8, that is minus of 36.86 degrees. Okay. Now your I dash is coming here, correct? Are you observing something? Your magnitude of I dash actually is lower than the magnitude of load current. So basically this capacitor is delivering the additional current so that the magnitude here reduces, so that the efficiency improves. So I hope now everything is clear, whatever I was explaining at the starting of this whole chapter, right? We connect a capacitor, we improve the efficiency, everything we improve. So I hope it is clear now. I hope it is clear how are we improving. So we'll see the results. So your I dash is actually a combination of IL plus IC. So from here I can easily find out what is my, because I know what is my VR. First of all I will calculate what is my IC. IC will be equals to I dash minus IL. So I dash is 525.86 minus 18, and IL is 625 minus 36.86. Okay, so this will be 525 into cos of 18. So this comes out to be 500, and the real part will be cancelled, only imaginary part will remain. If you see, if you like, you will be able to see 625 into cos of into 0.8, basically 625 into 0.8, this comes out to be 500. Okay, roughly there will be some real part, that is just some calculation error. Okay, that will be calculation error. Okay, the real part should exactly get cancelled, because the capacitor is not taking any actual reactive power, sorry, active power. So this will be almost equal to 0. This will be 625 sine of 0.86, 625 sine of this into 625. This will be 374.9, and it is negative. Negative will become plus. This will become 374.913. That is what my current is. I'm just thinking, am I making any mistake over here? 525 is there. This is my load current. So I see okay. Actually, sorry. This IC will come here, right? It will absorb some power. IC is the leading current. Here is the IL. Yeah. So I will be equals to I dash will be equals to IL plus IC. Yeah, IL plus IC. So IC will be I dash minus IL. Okay, negative. This is negative. This is minus. Oh, here also I have an imaginary part, right? So 18 sine into 525. So it is actually negative minus, so this is j, this is minus j 162.23. Yeah, sorry, I have made a huge error here. Like your reactance, right? Xc is what? Xc is 1 by j omega c. What am I doing? What am I doing, man? So this will be 1 divided by 1 by j omega c. Actually, this will be j omega c into v. Right? Sorry, really sorry. That's why I was thinking, how is this positive and this is negative? This was coming to be negative, right? Okay, so now we are done. Like we are correct. So this will be, this will come out to be 374.913 minus 162.23. Okay, so two one two 0.683. okay, so yeah, that is your current, that is equals to this IC will be equals to j omega c vc. So your c will be equals to jj will get cancelled, 212.688 divided by omega, that is 100 pi into vc. Vc is 10 kilovolt, sorry Vr, it is Vr basically, that is 10 kilovolt, 10 kilo, right? So I want to write in terms of micro, so I will multiply by 10 raised to power 6 and I will multiply by 10 raised to power minus 6. So this whole thing will be in micro basically. So this will come out to be divided by 100 divided by pi divided by 10 raised to power 4 into, okay, so this will be 67.7 microfarad. Okay, this will be the value of the capacitance that I need to connect so that the voltage regulation improves to 50%, right? 50 improves by 50%, so it becomes 10.5%. Now what is the effect in efficiency? Efficiency is what? Again, it is whatever is the active power output P load upon P load plus the IR square into R, right? Line losses. So into 100. So still my load is taking 5 megawatt of power, that is constant, divided by 5. Now what is the current? If you see the IR current, right, has now reduced. It has become 525 in kilo amperes. It has now become 0.525 into R. R is 0.4875. 0.4875. This will be whole square basically. Into 100%, right? So this will be 0.525 whole square into 0.4875 plus 5 into 5 into 100. Okay, so this will be 97.38%. okay, so this will be my efficiency. If you see, the efficiency has also improved quite a lot. Previously the efficiency was lower. If you see here, what was the efficiency? Efficiency was 96%, right? Now efficiency has improved to 97%, right? So that is better. So that's why we connect a capacitance in parallel to the load. Okay, let's now solve this one. Okay, two more questions are left. Two transmission lines P and Q are connected in parallel to supply a 10 megawatt load. Okay, so I have two transmission lines P and Q. Let's say this, let's name the impedance of the, like these are short transmission line because only resistance and reactance are given, right? So I will replace them with their series impedance ZP and ZQ, and it is delivering a load of 10 megawatt at an operating power factor of 0.8. So PF equals to 0.8. Lagging. So now, what are they telling? Determine the power supplied by P, right? What is the power supplied by P? So this, right, I think we have done, if you remember, using the parallel operation. So if you remember, the power supply, like the ratio of the power supply, right, will be the inverse of their voltages. Okay, sorry, inverse of their reactances. This, right, if you remember the parallel operation of generators, that also is something similar, but here again I will derive it. So let's derive. So here, right, this will deliver some current IP, this will deliver some current IQ. What will be the ratio of currents? Now these two are branches are parallel, so the ratio of currents, right, ratio of currents will be IP by IQ will be equals to opposite reactances, right, ZQ divided by ZP. This we already know, correct? Now the voltage is here is same, right? The voltage is same here at this end, receiving end. So if I multiply and divide by receiving end voltage, right, that will still be same. Okay, so the what I can say is the reactive is the complex power sent by SP, and the complex power sent by SQ will be ZQ upon ZP. But these are not actually the ratio of active power. Okay, but what have they asked? Okay, we can calculate the ratio of the complex power. I need to calculate the value of IP as well, right? How will I? Okay. Okay, VR is anyway same. So let me not go this way. Let me just calculate the currents, and from there I will find out the power. What is power basically? So what is apparent power? Apparent power is VI conjugate. So from this, if I know current, right, VR is constant here. So I will be able to find out the apparent power delivered by the line P, and from there I can derive the active power. Okay. So okay, what is IP upon IQ? So IP upon IQ is ZQ upon ZP. ZQ is 4 plus J3, and ZP is 3 3 plus J4. Okay. Okay. Now one more thing I know, the overall power sent to the delivered will be the sum of the two individual apparent powers SP plus SQ, right? So basically from here I can directly say IL will be combination of, because I will divide by voltage, and voltage is constant everywhere. So if I divide by voltage, it will be IL will be equals to IP simply, right? What is this? It is simply VL into IL conjugate, correct, equals to, because whatever is the power delivered from here, the same, or you can directly write a KCL at this note, right? Instead of doing all this, I can directly write a KCL. IP plus IQ will be equals to the load current IL, right? All these are in phasor, simple KCL, right? So okay, I know what is my IL, I know what is my IL. So what the overall current will, like whatever current is coming out of here, same current will come out of here as well, right? So IL will be what? IL will simply be the power. It's a single phase load, right? Two transmission lines. Nothing is mentioned, so I will assume it to be single phase load only. But they have not given us the voltage actually. Okay, they have not given us the voltage. That is interesting. No voltage is given to us. Okay, power will be V cos I will be V P by V cos phi. So power is given to me, that is 10 megawatt. 10 megawatt divided by V, let's assume that V is in kilovolt, cos phi is 0.8. Okay, this is my IL, and angle will be some minus 36.86. It is simply minus of cos inverse 0.8. So IP upon IQ is this. What is IP upon IL? IP upon IL, right? It will be equals to the opposite impedance plus the summation of these two impedances, right? So it will be basically 7 plus J7. Okay, and I know what is my IL. IL is 10 divided by V into zero point 0.8 angle of minus 36.86 degrees. Now I need to find out the apparent power. So I will take the conjugate on both sides. If I take the conjugate on both sides, this will be 10 upon V into 0.8 into plus 36. Sorry, this value is also there, right? Don't forget this value is there, right? Okay, so let me write the polar format of this. So this actually comes out to be 5 angle okay, 36.86, and this will be 7 root 2 45. Okay, and this will be 1, almost 1 actually. Sorry, this is not almost 1, sorry. 5 divided by 7 divided by root 2 0.5, and the angle 86. Okay, 8.14 degree. So this will be into 0.5 into 8 minus 8.14 degree, right? So this actually together comes out to be okay, sorry, 4 plus 36.86 comes out to be exactly 45 degrees, right? And I have to take the whole conjugate of this. Okay, and 0.5 is also there. So if I multiply 0.5, this will become 5. Okay, and then I will multiply both sides by V, right? So that I can get the expression for apparent power. So this will become, if I multiply both sides by V, this will be SP, because this is VIP conjugate, that is SP only, and here V and V will get cancelled, right? I'm multiplying V by both on both sides. So this will be 5 upon uh, 0.8, that is 25 by 4 angle minus 45. What have they asked actually? They have asked the power supplied by the line P. So power supplied by the line P will be pretty simple. It will be basically uh, just give me 1 second. Yeah, plus conjugate minus, yeah, that is there, minus 8.14. If I take the conjugate of this, yeah, 25 over 6.25, and this seems like I'm doing something wrong over here. 36.86, yes, it is correct. It is not, the top one is there. No, it is correct only. Yes, it is correct. Okay. Yeah. So this your active power will be what? It will be like your SP, right? SP is equals to what? 25 by 4. It is 1 by root 2 minus j by root 2. Okay. So from here I can easily say what is my active power. Active power will be 25 by 4 root 2 minus j 25 by 4 root 2. So 25 by 4 divided by root 2. Okay. So your active power, remember this is in megawatt, right? Everything is in mega. 4.19 mega minus j, this also will be same only 4.419 mega. So this is in MVA basically. So active powers delivered by the load, delivered by the transmission line P will be 4.419 megawatt. Okay. So I'll just quickly explain what I did. So this is simply CDR, current division, right? IL current is coming out, right? So this IL current can be divided IP by IQ, inverse relation of the ratio of the impedance. Simple current division rule. Simple current division. Now I know that if I apply KCL here, like I'm applying KCL, IP IQ will be equals to IL. What is IL? IL will be the power divided by the voltage into cos phi. This is a single phase load. This is a single phase load. Even if you assume it's a three phase load, automatically your V will get cancelled. So it does not matter at the end. Even if you assume three phase load, it does not matter. Everything V will get cancelled. Okay. So your I comes out to be this value. Remember to write the angle. I is a complex quantity. I is a complex quantity. Power factor is given, and it is also mentioned that it is a lagging load. That's why current will be lagging. That's why negative sign will be there. Okay. Then I will write the ratio of IP and IL. What will be the ratio of IP and IL? Either you can write that it is the opposite impedance upon the summation of both the impedances. This we can do, or you can simply add, you can take the inverse of this, right? Take the inverse of this. Like if you're not able to understand this formula, take the inverse. So IQ upon IP is what? It is just the inverse, 3 plus 4j upon 4 plus j3. Then I will add 1 at both sides. If I add 1 at both sides, right, this will be IQ plus IP. What is IQ plus IP? It is simply IL. What is this plus this? 7j. So IL bar upon IP bar will be equals to 7 plus j7, 4 plus j3. Okay. So again, if you take the inverse, you will get back this value. I'm directly writing it, but for the guys who don't understand, I am again explaining it. Like I'm trying to explain each and every step. Okay. Okay. So you get back this value. This ratio becomes a complex quantity. Then after you replace it over here, because I know the value of IL, I will replace IL value over here, right? I will multiply the complex quantities and I will get my apparent power by multiplying by V on both sides. If I multiply by V on both sides, this V and this V will get cancelled. This will be what? Apparent power of the line P, right? And from there I can easily find out the active power sent by the line P, that is 4.419. So I hope it is clear. This question is clear. So that's it basically. This lecture was very long. I am sorry. I hope you have understood everything. Like I know it's a bit difficult. Sometimes it feels difficult, but you have to maintain the consistency. If you don't maintain the consistency, trust me, it will be very difficult to for you. So if you maintain the consistency, trust me, you will be beating 90% of the students. Okay, so yeah, that's it for this lecture. In the next lecture, we will study medium transmission lines. I will see you in the next one. Until then, happy learning. Hi everyone and welcome back to PrepFusion. So today we will discuss about medium transmission lines. So what is a like definition or classification of a medium transmission line? So the length must be between 80 kilometer to 200 kilometer. That's a rough idea. Of course, at 50 Hz frequency. If you are talking about the product, then it should be between 10,000 to 4,000 kilometer hertz. And operating voltage will be between 100 kilovolt to 20 kilovolt. This will be the operating voltage basically, right? Now in this case, what things can be neglected? Because I have told you my actual transmission line is distributed. In case of short transmission line, we lumped the R and L together, right? Because it was series connection. So here what things can I ignore? So the thing that I can ignore is the conductance. I will not be able to ignore the capacitance. Capacitance here will be actually considerable because length has increased. Now there will be more charging current. Okay, because your capacitance, what is your capacitance dependent on? So your capacitance C1 is basically dependent. This C1 is farad per meter capacitance per unit length, right? And what is your reactance? Your reactance will be 1 by omega C1 into length, because I have to multiply the length factor so that this becomes in ohms, right? So the length has increased. If the length has increased, your XC will reduce now. XC will reduce, so your shunt parameter, the reactance has reduced, so it will be considerable now. Higher the reactance, it will be negligible, but if it is lower, then it will be considerable. Correct? Now, G, I have the conductance. Okay, I have the conductance. So, if I have the conductance, can I ignore the conductance? Yes, we will be able to ignore the conductance over here, because the height, because the dielectric strength, right, of air is 30 kilovolt per centimeter, right, and our operating voltage V is basically, if I say even if our operating voltage is 100 kilovolt, but if the length, right, distance between the ground and the tower is much higher, let's say 10 centimeter, then this will be reduced, right? The electric field that it will produce, like roughly, I'm just giving you a rough idea, electric field that I will produce will be 100 divided by 10, that is 10 kilovolt per centimeter, which is still lower than the dielectric strength of air. So that, like, there will not be any current flowing, there will not be any dielectric breakdown. So no dielectric breakdown. So if there is no dielectric breakdown, right, there is no dielectric breakdown, so I can neglect the conductance, but your capacitance I will not be able to neglect. And if this capacitance is present, right, this capacitance is present, so some amount of current actually is flowing from the capacitor to the ground IC, right? So some amount of current IC is going to the ground. Okay, this actually IC current is known as the charging current. We will discuss about this, don't worry. I'm just telling you, I'm just giving you an overview. This current is known as the charging current IC. Okay, that will flow through the capacitors. What is it equals to? This is equals to the voltage upon XC, or simply it is equals to omega C into V. Don't worry, we'll derive this, right? So basically, as the dielectric electric field is lower, so there will not be any dielectric breakdown. Okay, I hope that is clear. Now let's solve this. Basically, let's try to see what kind of different arrangements there are. So actually, your medium transmission line, your parameters will be distributed. Your parameters kind of will be distributed. How it will be distributed? Actually, what will happen is your parameters will be somewhat like this. Just give me 1 second. Let me keep everything in a place just to crowd it. Yeah. So this G I can cancel, this G I can cancel. So actually it is distributed, right? So each of these networks are basically in series. each of these networks are in series. Okay, if you see, so I will not be able to analyze like this will be very difficult, because each, like, let's say 1 meter I have this R, L and C, then again the next meter I have R, L and C. That will be very hectic for me to analyze. What we can do, we can directly model this using approximations. So it will not be exact, it will be approximations. So all these are nominal models. So wherever there is a name nominal, that means basically what it is telling us, that it is the approximate model. So nominal basically means the approximate model. Okay, and the equivalent, right? If whenever there is a name known as equivalent, that means it is the exact model. Equivalent basically means exact model, exact model. So all these are actually approximations, all these are nominal models. Okay, so mainly we'll discuss about n condenser. This is the most important for gate point of view. Okay, for gate point of view, this is the most important one, and mostly questions will be asked from end condenser model only. These are important for ESC. Gate guys also will study this, but less important. Okay, mostly these are important for ESC. So slowly we'll discuss. So how can I understand a T model? So if I see this tower in isolation, so on the left hand side of this tower, right here I have conductor. On the right hand side of this tower I have conductor. So this, right, will be R, and of course this conductor will have a inductance as well, and this both capacitors are connected, right, because insulations are there, and parallel to insulation there will be some capacitors. These are known as the leakage capacitance, okay, of this insulators that will go to the tower. So that's how the capacitance comes, and the leakage conductance goes to the ground, correct? So this capacitance, these two capacitors are there, they are both are in parallel, so I can connect them as a single capacitor, right? And this tower is also actually grounded. Okay, remember it is an insulator, it is not short circuit here. This is a conductor, and this tower also is grounded, so that we can provide the path of the charging current. This tower is also grounded. Okay, this metal side is also grounded. So I have a capacitor here, and on the right side also I have resistor and an inductor. So this is the example of a T model. If I just observe this part, right, if this part is observed, okay, now if I observe this part, right, if I observe this path, what do I see? Or this whole path, right? So here it is a series combination of a resistor and inductor, and these two will provide capacitance, the charging current, to the ground. This is again grounded, this side, top side is again grounded, right? So this will be my capacitance. So this is the end condenser model. This is the T model, this is the end condenser model. What about pi model? So to understand pi model, what we can do is, again, we don't need to see it from the in between, we can directly see this part and this part, right? So what do I see? On the left hand side I have a capacitor, on the right hand side I have a capacitance to ground, and this is simply a combination of R and L, right? Okay, so this is the pi model basically. Okay, so these are the three different models. Which one is preferred? So in T and pi model, what do I see? That I have some voltage here, Vs, sending end voltage and receiving end voltage, and in between I have an inductive link. So this, right, is much easier for us to analyze, much easier. So you remember, right? During stability also, we wanted a link. Basically, I know the potential here, I know the potential here. If I know this link, that's it. But here, right, I will not be able to write down that power formula, Vs, Vr by Xs sin delta, because this is not purely between two voltages. Here I have a note in between. So for load flow analysis, pi model is preferred. Okay. For, I hope you have studied fault. If you have studied fault, then I have explained that between these two voltages, right? I know the voltages between these two nodes and I know the link that is connecting these two nodes, then I can definitely comment about the power and losses. Okay. So for load flow analysis, pi model will be preferred. Okay. Okay, I hope it is clear. Now let's derive few results for end condenser model. First one is voltage regulation, right? Voltage regulation. What is the formula for voltage regulation? General formula, it is VR equals to magnitude of Vs divided by A minus magnitude of VR full load, basically, divided by magnitude of VR full load into 100%. Correct. So what is A here? So I have to find out the ABCD parameters. What is the ABCD parameters? Again, I can write this one as a combination of Z1 and Z2. So this will be Z1 and this will be Z2. Correct. So what is Z2? Z2 is simply 1 by Y, which is simply 1 by J BC. BC is the susceptance, and Z1 is simply series combination R plus JXL. I'm writing it as Z, okay, because a famous formula will be derived here. So now I can simply write down the transmission line parameters for this end condenser model. We know the transmission line parameters for this kind of network, two-port network. That is, this will be 1 plus Z1 by Z2. What is Z1 by Z2? It is Z1 is Z, Z2 is 1 by Y, that is into Y. Here I will have Z1, that is Z. Here I will have 1 by Z2, that is Y, and here I will have 1. Okay. So that is the ABCD parameters. Basically, from here I can directly find out what is the value of A. So what is the value of A? A will be 1 plus Z into Y. That is what my A will be equals to. Okay, A is equals to 1 plus Z into Y. 1 plus Z into Y. Now few more things we can derive. So I hope now your formula for the long transmission line, right, for the end condenser model, this will become Vs divided by 1 plus Yz minus magnitude of Vr divided by magnitude of Vr into 100%. Okay. Okay. So I hope this part is clear, the voltage regulation part. Now one more thing I want to calculate. I want to calculate the charging current at no load. What is the charging current at no load? Charging current at no load. Basically, even though no load is connected, still the transmission line, some current will flow. In short transmission line, if you remember, there was no parallel path for the current to flow, right? If there is no load connected, if IR is 0, IS has to be 0. But this time my IS and IR are not equal. Okay, there is a parallel path. This is what I want to find out. So at no load, my IR will be 0. At no load, my IR is 0, correct? I want to find out my IC. What will be IC? IC will be simply equals to this voltage. IC will be simply equals to whatever is the sending end power. Sorry, whatever is the sending end current, because no current is flowing here. If I apply KCL here, whatever is the incoming current should be outgoing current. This current is 0. So at no load basically means IR is 0. So IC will be equals to IS, right? So I have to find out IS at no load, right? I can use the transmission line parameters again. Vs equals to A VR plus BIR, and IS is equals to CVR plus DIR. Now at no load this will be 0. I have to find out IS. So IS will be equals to C into VR, right? You can write IS equals to C into VR. This is one way to find it out. What is the other way? If I take the ratio of these two, right? If I take the ratio of these two, right? These two, this will go away. IR is 0. So Vs by Is will be equals to A by C, right? So my Is also, this is also another equation. You don't need to remember this, but you need to understand how am I deriving it, right? So this, which will be equals to Is will be equals to Vs into C divided by A. Okay, that is also another way to find out your Is. Okay, basically this is my charging current only. Is is same as charging current. Okay, now from this I can actually find out a value. What is a charging current? Charging current will simply be your voltage at the receiving end by the reactance, that is 1 by j omega C, correct? So from this VR will get cancelled, right? I can say that my C will be equals to simply j omega C. Okay, I got the value of C. The capacitance, this C and this C are two different things. Sorry, this C is simply C angle. This C is the parameter C, so magnitude of C and gamma, right, is equals to j omega C. So it is basically purely imaginary. Your C will be purely imaginary, is it? Yes, because VR divided by 1 by j omega C. Yes, because VR will be some, okay, because if it is no load, right, Vs is here, but VR, no, it will not be purely imaginary because VR anyways is getting cancelled, right? Yeah, so C is purely imaginary basically. This is what my C is equal to magnitude of C. Is it the case? Yes, here also C is what? C is simply Y. That is what we derived, right? C is Y. What is Y? Y is basically 1 by JBC. What is BC? BC is the susceptance, so it will be omega C. So Y is simply omega C. So here I will replace this with omega C. That is what we have derived, right? C is simply omega C, and obviously J is there. It is imaginary. J is there. Okay. So yeah, I hope that is clear now. These things are clear now. Any other formulas that I want to derive? C into, so C is magnitude. If I want to find out the magnitude of charging current, right, this will be equals to, I will replace C with omega C here, magnitude of C, that is omega C into Vs divided by A. This will be handy, magnitude of A. Okay, so this is what my charging current will be at no load. So what do we observe? That there is some current even though my receiving end is not connected to any load, right? There is some current. So this kind of effect is known as Ferranti effect. Okay, so even though even though transmission line is operating at no load, even though transmission line is operating at no load, still there is some current through the transmission line, right? So this effect, right, which is leading in nature, because it is mainly capacitance, the current is due to the capacitance, leading in nature. So this effect, this phenomenon is known as Ferranti effect. Okay, so of course more definitions are there, but like this was the brief about the Ferranti effect. Now I want to draw the phasor diagram for the end condenser model. And how can I actually okay, let me first draw the phasor diagram for the end condenser model. So if I draw the phasor diagram for the end condenser model, right, it will have some load connected, that is XC. Okay, sorry, not XC, sorry, it will have some load connected that will operate on some, let's assume mostly our load is lagging, it operates at some lagging power factor. So cos phi is lagging basically. Okay, so yeah, now if I want to draw the phasor diagram, how will I draw the phasor diagram? So there are three currents, IS, the sending end current, which is a combination of IC plus the receiving end current, which is some lagging power factor, operating at some lagging power factor, right? So the receiving end voltage will be the reference basically. This point voltage will be VR angle 0, right? And this point voltage will be VS angle of delta. So VR, I'm doing all this because they might ask question from phasor diagram. That's why I'm deriving the phasor diagram as well. Okay, so this, right, will be my VR and IR will be lagging to it. IR will not be in same phase. IR will be lagging. Let's assume at any angle. This is what my phi r is equals to. Okay, next. IC, what will happen to IC? IC will lead the voltage, this receiving end voltage, by 90 degrees. So this will be my IC. Okay. Now, what will be IS? IS will be the vector sum of these two, IR and IC, right? So IR will be somewhere here. IC will be, it will still, like it will either be lagging or leading. At no load, right? It becomes leading because IS is IC. But here it will be somewhat lagging only. Mostly it will be lagging only. Or will it be? Let's see. Okay. So it comes out to be somewhat leading or something. Okay. Somewhat leading. Your current comes out to be somewhat leading. I'm just drawing a rough phasor diagram here. Even though your load is lagging, your transmission line current is still leading. Okay, because due to the shunt branch now. Shunt due to the Ferranti effect. Due to the Ferranti effect. Okay. So this will be your IS. What will be your VS basically? Your VS, right? First of all, there will be a drop here from VR. VS is what? VS, right? Is simply VR plus IS into R plus J XL. Okay. So IS into R plus JXL. So what I can say is this, right? I have to add an additional drop of IS into, this will be in parallel with IS. I hope all this phasor diagram, I'm not explaining this phasor diagram. IS into RS drop, R drop, and then 90-degree perpendicular to this will be my IS into XL drop, right? Because it is J into IS into XL. So your V, what color I can choose? VS comes out to be this. Okay. Okay, still the current is lagging somewhat because it lags from VS. Still it is lagging. That's fine. So this is your VS. This is your phasor diagram basically. Okay, at any load, operating at any lagging load. Phasor diagram for end condenser model operating at lagging load. Okay, I hope it is clear. One more thing that you must keep in mind during Ferranti effect, right? I will explain. I will draw the phasor diagram during Ferranti effect. This was the phasor diagram during any random lagging load at load. I want to draw the phasor diagram at no load. Okay, phasor diagram at no load. This will be much simpler. So here your IR current will be 0, right? I will take this picture, take this here again. Load, I will disconnect the load basically. There will not be any load connected. Okay, so IR current is 0. So your IS will be IC. Okay, so if I draw the reference, VR is here. This is the reference. VR angle 0. Your IR current is not there. Okay, IC current will be again leading from VR, purely leading. Your IS is same as IC. So IS is same as IC. This is IS only. This is IS only. Okay. What about your VS? VS will be basically a drop that will be parallel that is Is into R, and in 90-degree shift, right, due to the drop in the inductance. So this will be Is into XL, okay, 90-degree in the clockwise direction. So what do I observe? I observe a very specific thing. The magnitude of Vs, right, is lower than magnitude of Vr. Basically your voltage regulation is negative, right? Isn't this what we have studied, that at leading loads the voltage regulation is negative, because here the load is behaving as leading, right, because due to this shunt capacitive reactance, that's why your voltage regulation is negative. This we already know. This I have proven it to you in phasor as well. In phasor, pictorially we can see that the magnitude, the length of the Vs vector is smaller than the length of the Vr vector. Okay, it is anti-clockwise, remember, because there is a jxl multiplied. Plus j means 90-degree in the anti-clockwise direction. So all this have been taught in the phasor diagram, so I am not explaining here. This has been taught in network theory. Okay, so if you are not able to understand this phasor diagram, you have to go and watch the AC analysis. Every single thing has been explained in detail over there. Okay, so this is the phasor diagram here, operating at any load. Okay, so what are the causes of Ferrand effect? The primary reason for Ferrand effect is the charging current flowing through the line capacitance. In long transmission line, even under no load conditions, significant amount of capacitive charging current will flow due to the line's distributed capacitance. This we have discussed. So this leads, this charging current will lead the receiving end voltage by 90-degree, as we can see, right, as it is capacitive in nature, flows through the line series reactance, producing a voltage drop across the inductance that is in phase with the receiving end. That is actually not exactly in phase, that is in phase opposition. Phase opposition. Phase opposition. Basically it is not 0 degree, it is in 180 degree. How it is 180 degree? We can see from here itself, right, that here this drop Is XL is opposite, Vr is in the going from left to right, Is into XL is going from right to left. It is in phase opposition. That's why overall the length reduces. That's why the length Vs reduces. Okay. This voltage drop adds to the receiving end voltage, making it not higher than the sending end voltage. Okay. They are actually talking about the other part. This is in phase with the receiving end voltage. Okay. So basically what is happening, this is also correct only. This is also not opposition actually. So this, right, this drop. So what is my Vs equals to? Vs, or what is my Vr equals to? Vr equals to Vs minus I into R plus Jxl. Okay, so this will be equals to what? Now, as already this Jxl, right, this I into Jxl, already negative sign is there and another negative sign is there because it is in phase opposition. Basically it gets added. So this will be Vs, this will become actually Vs plus I into XL basically. Okay, because I itself is 90 degree leading. What is the angle of I? I is equals to J omega C into Vr, correct? So I am multiplying this I with minus I is there and I am multiplying this with Jxl, right? What is happening? This becomes I is minus J, so J square becomes minus 1. So this will be 1 omega C into Xc plus, of course, Vs is there, right? So that's why it gets added, because I is what? I is J and J into J is minus 1 and another minus sign is there. So automatically it gets added with Vs. That is what is told over here. We add it with Vs. So overall the receiving end voltage appears higher than the sending end voltage. This we already knew while deriving the voltage regulation, that voltage regulation will be negative when the load is capacitive, but here load is not capacitive, but actually what is happening, due to the transmission line capacitance, it is behaving as capacitive load. Okay, it will occur mainly in medium and long transmission lines. There only the effect of capacitance is present. Okay, it will be more present in higher voltages, because your what is your charging current proportional to? Charging current is proportional to voltage, right? V also will be there. Charging current is proportional to V, so higher the voltage, higher the charging current. Okay, at full load it is negligible, because the full load current itself, what is my sending end current? Sending end current is series addition, is phasor addition of charging current plus receiving end current, right? So what is happening is simply your IR current will be very high, charging current will not be that high, so your IS will be roughly equals to IR only, because the magnitude of receiving end current at full load will be much higher. Okay, that's why we can neglect the effect of charging current at full load, but at no load it is considerable. At no load it is considerable. That's why we only discuss the effect of Ferranti at no load. So at full load we can neglect, at no load Ferranti effect is considerable. Okay, so I hope things are clear now, right? So yeah, few things we want to discuss, right? Few approximate analysis we want to discuss. So what is the first approximation? First approximation is that we will assume that this is my N condenser model, right? We will assume that our reactance will be much higher than the resistance. So basically our resistance will be much lower than the reactance. Okay, our resistance will be much lower than the reactance. So we can approximate this N condenser model like this. Here I will have a inductance and I will have a minus J reactance. Remember, this was the susceptance, that's why it was with plus J. Okay, now few things I want to derive over here. Here one thing we can notice at no load, I just want to observe the Ferranti effect, right? Ferranti effect, what is the charging current at no load? The current IC will be what? IC will be basically, this will be what? This will be J omega L and this will be minus of J by omega C, correct? So IC will be basically equals to, this is operating at no load, correct? So IC will be, if I am applying some voltage over here, Vs, right? What will be your VR? Simple voltage division, it will be minus J by omega C divided by, or I can directly find out what is my IC. IC will be equals to Vs into 1 by J omega L minus J by omega C. Okay, that is what my IC will be equals to. Now one more thing I want to derive. This is the charging current, right? Charging current will be equals to, if I multiply by, if I take common J, right, this will become, or if I multiply by omega C, right, this will be minus J omega C into Vs divided by, this will become omega square LC minus 1. Okay, and generally omega square LC will be generally larger than 1, so your charging current will be this Vs divided by omega C into Vs divided by omega square LC. Now this is what I don't want to discuss. I want to discuss the Ferranti effect. What is the Ferranti effect? Ferranti effect basically tells me that the receiving end voltage becomes much larger than the sending end voltage. So if I compare the delta V, that is the receiving end voltage minus sending end voltage. So what is it equals to? So it is simply, it is no load, right? So these two are in series. So I can apply the voltage division here. Just as I have like I have not actually, I will do that. So this will be minus j by omega c divided by j omega l minus j divided by omega c into Vs. This will be your VR. Okay, so this I can replace over here. So Vs, this will be minus j divided by omega c minus, so this will become minus j omega l plus j omega c divided by j omega l minus j omega c. So here, right, this gets cancelled, and if I take common j, right, or if I multiply, yeah, if I take common j over here, this will become delta V will become minus will be there actually. Okay, minus j omega l into omega c divided by j. I will take common and I will multiply by omega c on both sides. This will be omega square LC minus 1. So this will be minus j omega square LC. Okay, jj will get cancelled. This will be minus omega square LC minus 1. That is the delta V basically. Okay, so here I will write one thing. I will write my inductance in terms of the inductance per unit length into the overall length, right? And I will write my capacitance C1, that is this is in Henry per meter, right? This will be in farad per meter into the length. Okay, so what I can say is I can actually there is one certain formula that is so this, right, this gets converted into L1 C1 L square. Okay, and generally this term omega square into L1 C1 into L square, this will be much lower than 1. This will be much lower than 1. Why? Because the ideal value of 1 by under root L1 C1, right, is actually speed of light. Okay, ideal value is speed of light. So if this is speed of light, so if I replace it over here, right, this will be omega square L square divided by speed of light whole square. This is in normal form, this is under root, that's a whole square. So this speed of light will be much lower than the frequency and the length. Okay, so that's why is this correct? Radian per second, I'm multiplying by length. Yeah, yeah. So this will be much larger, so that's why this will be much smaller than 1. So this I can neglect actually. So this value will come out to be equals to minus omega square LC divided by minus of 1. So this will be omega square LC. This is my delta V, right? So my delta V, or the Ferranti effect Ferranti effect, higher the delta V, higher will be the receiving end voltage than the sending end voltage. Okay, so Ferranti effect is proportional to omega square. It is proportional to L1 C1, that is Henry, like inductance per unit length, capacitance per unit length, and L square. Okay, so L1 C1 into L square. So that is what it is. Uh, that is what the function is. That is what it depends on. So if the frequency is very high, even though the length is smaller, right? If the frequency is very high, that is in the megahertz range, then also Ferranti effect is considerable. Then also Ferranti effect will be considerable. Ferranti effect will be considerable. So intuitively, can you understand? Considerable. Intuitively, if I say frequency is very high, if frequency is very high, this reactance will be very low. So there will be more charging current to the ground. This is providing a short circuit path. There will be more charging current. This capacitor will come into action. So that's why Ferranti effect will be higher, more charging current. Okay. So will be higher. This is observed where? Where do we operate in megahertz range? We operate in megahertz in communication systems, right? Electronics. So even though this is a small board, but here components operate at high frequency. If they operate at high frequency, Ferranti effect will be present here as well. So as in EMFT communication system, we operate at megahertz frequency, Ferranti effect will be present. Okay, Ferranti effect will be present. So even though length is small, so at high frequency, right, things actually behave very weirdly. So you have to be very careful at high frequency. Even though length is very small, so it will behave as a medium transmission line or a long transmission line. Okay, so that's why I told you at the starting of this chapter that at high frequency is a very important parameter. If I increase the frequency, it behaves as a long transmission line. Okay, just be careful regarding that. So what does my Ferranti effect depend on? My Ferranti effect depends on frequency, right? It is a function of omega, it is a function of the inductance per unit length, it is a function of the capacitance per unit length, and it is a function of the length of the transmission line. So this is also very important thing that can be asked as a MCQ, MSQ. What parameters does my Ferranti effect depend on? Okay, this is also an important thing that they can ask. Okay, I hope that is clear. So this actually generally is VC. This is called as the speed. Generally it is near to speed of light, but sometimes if there is some non-idealities, this is called as the speed of propagation of voltage or current. Speed of propagation of voltage or current. This we will discuss in the next lecture. Voltage or current. Okay, don't worry, this we will discuss in the next lecture. This is also kind of a like important formula, this will be discussed. So yeah, that is what my Ferranti effect is equals to, right? Yeah. So how can I eliminate Ferranti effect, right? How can I eliminate Ferranti effect? So Ferranti effect, the problem is there is some charging current at no load. I want to totally eliminate this charging current. I want to, at no load, I want my sending end current to be zero, same as receiving end current, just like in short transmission line, right? That is my purpose. So if I copy it here, what can actually help me do that? So method method to remove Ferranti effect. Okay, so I want my sending end current to be zero. I want my sending end current to be zero. How can it be zero? So the receiving end current is zero already. What I can do is this capacitance is actually taking some leading reactive power, or it is delivering some lagging reactive power, right? So if I connect, like it wants to deliver the lagging reactive power, if I connect a inductor that is parallel to this capacitor, that whatever lagging reactive power this capacitor wants to deliver, it will deliver to the inductor, right? Not here, not to the transmission line, it will deliver to the inductor. Then automatically you will see that your sending end current will become zero. So basically whatever is the current that is charging current that is flowing through here, that will be phase opposition to the inductor. So that will make my sending end current to be zero, right? So basically I want my Is to be zero, right? I want my Is to be zero. So what is my ABCD parameters? ABCD parameters is Vs is equals to AVR plus BIR, IR is 0 simply, and Is equals to CVR plus DIR. Okay. So now one key point is to note here is I am connecting an inductor to the load, right? I am connecting an inductor to the load, but I am telling you this current after the inductor is 0, IR dash. But this current is actually not 0. This current will be what? Here I have the receiving end voltage, and in the load previously nothing was connected. Now I am connecting an inductor. So what is the current? So I am from no load I am connecting an inductor, right? So the new receiving end current will not be 0 anymore, right? I am connecting this inductor because previously this capacitor was sending some reactive power to the transmission line. Now I want this reactive power, whatever this is sending, to here, right? So what, now the IR will not be 0 anymore. What will be the IR? So IR will simply be equals to VR by JXL dash, actually, because XL is already here. It is equals to JXL dash. Or I can say VR by IR or what I can do is I can replace this right here, and I know what do I have to do to nullify the Ferranti effect. To nullify Ferranti effect, my delta V should be 0, that is the sending end voltage and the receiving end voltage should be 0. Basically here there should not be any current, right? So basically delta V is 0, Is is 0, that means your VR will be equals to Vs. VR will be equals to Vs, correct? That is the purpose. So here I can replace this with VR, right? In this equation I can replace Vs with VR equals to AVR. What is your IR into B? IR is VR divided by JXL dash, right? We can write the magnitude over here. I am not considering the, or we can consider the phase as well. No, does not matter actually, because IR already has, IR will have the phase included. I'm just discussing about the magnitude, or no, it's fine. We can take the phase. So your, from here, right, VR will get simply cancelled. Your XL dash will be, JXL dash will be B divided by 1 minus A, or I can write your XL dash will be minus of JB divided by 1 minus A. Okay, don't worry, you don't have to remember the formula, just understand the concept. Just understand the concept. What have we done? So previously there was no load connected, your VR was not equals to Vs, there was some delta V, there was some Ferrand effect. I told you that we have to nullify this Ferrand effect. My capacitor was actually sending some reactive power to the transmission line, due to which the load side voltage was increasing, receiving end voltage was increasing. So what we did, whatever reactive power it is delivering, let it deliver to the inductor, right? So that's why we connected a parallel inductor. Now as I have connected a parallel inductor, as if I have, it's a load connected, right? As if it's a inductive load connected. So that's why your IR current will not be 0 anymore. Although yes, actually there is no load, but as if by connecting the inductor, it is behaving as a pseudo load, right? So here my IR current will not be 0, it will be VR by JXL. So now I will replace this IR current in the ABCD parameters, and I know if I am removing Ferrand effect, my VR will be equals to Vs. VR will be equals to Vs. So that's why simply I will equate this and I will get my value of XL. Okay, I hope that is clear to you. Now let's derive one more thing, that is the losses due to the charging current. So although this is an approximate model and I have lumped everything, right, the charging current will only flow through the receiving end, actually it does not happen. Your conductor is very long, so charging current flows throughout, right? So here, right, the current, let's say initially 10 amperes of current is incoming, so 1 ampere of current will go here, 1 ampere of current will go here, 1 ampere of current will go here. So what is the problem? The problem is calculation of loss is very difficult, right? If I just would have assumed that I am sending 10 ampere of current, right, so this loss will be 10 square into R. But actually what is happening, I am sending 10 ampere of current, then I have some small resistor, right, then 1 ampere of current is going out, so here 9 ampere of current is there, then I have some small resistor, and then again 1 ampere of current is going out, then again I will have a small resistor. So basically what is happening is that this is becoming a problem, right? This will be, first of all, this will be 10 square R plus 9 square R plus 8 square R. That is a problem, right? That is a problem for us. So we will take help of the integration. So I will assume that I will just take a very small section. Let me take a very small section dx. Okay, let me take a very small section dx. So what will be the loss in this small section, right? So let's say if I have traveled till this point, this is x equal to 0, this is x equal to L, and let's say this is the point of x equals to x basically, right? So what will be the loss in this small length dx? What will be the loss? So like I will write down few things. What is the current till x? If I have traveled till x, right, what is the total current here? That is I into x, correct? that is I into x, right? So what is the current in the remaining section? This is the charging current till x, charging current till x, right? I into x, because some I current is flowing, it will be I into x. Now what is the remaining charging current? In the remaining section, it will be charging current in the remaining section this will be I into L minus x. Okay, sorry, overall current will be what? I into L, overall charging current. Like remaining section is I into L minus x basically, because the remaining section length, what is the remaining section length? It is L minus x. This much is x, right? This overall length is L. So this much amount of length will be L minus x. Okay. So this much amount of current, right? This much amount of current is gone here, and this much amount of current is still remaining, that will flow throughout this length, right? That will still flow, that still has to flow. This much amount of current has gone, and this much amount of current, that is IL minus x, has to flow, because overall, what is the charging current? Overall the charging current is I into L, right? That is the overall charging current, correct? Overall charging current is I into L, out of which I into x current has flown out, right? Remaining current is I into L minus x. So if I choose a small section, small length here dx, right? What will be the loss through this dx? Whatever is the current, that is I into L minus x, that will flow through this small length into the resistance, right? So it is I into L minus x whole square into the delta R. What is delta R? If you see, delta R is basically this resistance per unit length into the length, right? That is dx. So this will be basically, this will be my d power loss due to the charging current IL minus x whole square into R dx. Okay, now I can easily integrate, because this is the power in this small section dx. I want to integrate from 0 to overall power, right? I want to integrate from x equal to 0 to x equal to L. So this will be basically, R is constant, R will be outside, I is also constant. This is current per unit length. Now this, right, this integration will be kind of difficult. Okay, minus sign will be there, or I can swap this, right? This will be basically L minus x 3 divided by 3. This will go from L to 0. Like, I hope you can do simple integration. So this will be basically IR, this will be 0 if I put, this will be L cube divided by 3. L if I put, this will be 0, right? So yeah, so this comes out to be I L cube divided by 3. I will just explain one more time, right? I will explain one more time how the derivation works. Okay, so your total charge losses due to the charging current is not equal to simply I square also should be there, right? Okay, sorry, I square also should be there. This is I square, right? This whole square, this will be I square. So I square, it is not simply I square R into L square, right? I square in R into L, it is something else. Okay, like what you would have assumed, that what is your overall charging current? Overall charging current is I into L, charge per unit, sorry, charging current per unit length into length, right? That is your overall IC. And what is your overall resistance? Overall resistance is small resistance R into L, right? So you will assume that your overall loss will be IC square into R, which comes out to be I square L square into R into L, which comes out to be I square R into L cube. But here it is one third of that. Why is that the case? Because you have assumed that all of the current is flowing through this conductor, but it is not the case. I have told you, right? 10 amperes of current is flowing through this section, then 9 amperes of current is flowing through this particular section, then 8 amperes of current is flowing through this particular section. So the losses also will be different in each section. The current is reducing, so the losses also will reduce. Now remember, this is at no load. At no load, that's why only charging current is there. There is no load current. If load current is there, anyways your charging current will be negligible, so we don't have to find out the losses. This is the losses at no load. Okay, no load, remember this is at no load. Now if I am at this particular section X, right, how much of the current has already gone out? Overall current is I into L through this conductor. At this point, overall current will incoming will be I into L. Out of this, I into X current has gone out. I into X current has gone out. So how much current is left for this section? I into L minus I into X. And if I assume a small length, what will be the loss through this small length? That is the remaining current, whatever current is coming in here, that is I into L minus X whole square into the resistance of this section, that is R into dx. Okay, then I simply integrate from 0 to L, right, from here to here. I will get my overall loss due to charging current. Okay, so this is at no load. Remember this, no need to remember the formula, just understand the concept. Now this, right, I can write this in a different term. So I have told you, right, what is the overall current? Overall current I into L, IC is I into L, and overall resistance is R into L. So I can actually change this. So I can write this, my overall power loss due to charging current is I into L whole square into R into L divided by 3. So I into L is IC whole square and R into L is simply R, right? So it is ICR square divided by 3. This also sometimes can be used, but for gate, like, I will recommend you to understand the derivation, because maybe they might ask you something weird from the derivation, right? Okay, for ESC maybe you should remember the formula. Now let's do the same kind of analysis for a T model. Okay, and I will derive the ABCD parameters. You remember the ABCD parameters if you are ESC aspirant. If you are gate aspirants, you don't need to remember, just understand the derivation. How am I deriving it? In the examination hall, you will also try to derive it. Okay. So first of all, this is a symmetrical network. From the right hand side and from the left hand side, I am observing the same kind of elements, right? So network is symmetrical. So A will be equals to D, network symmetrical. Okay, and then we have this what do you call, network is reciprocal because it contains only RLC elements. So ED minus BC will be equals to 1, as network is reciprocal. Okay, now we will find out the values. I think I have already derived how you can find out the values of a simple, like, star network. This is a star network, right? So I can write, this is what this is. Let's assume this as to be Z by 2, right? This to be Z by 2, correct, and this to be Y. So what is its impedance? Impedance will be 1 by Y. Admittance is Y, impedance will be 1 by Y. Okay, now I can simply write the input KVL, because ultimately what do I have to find out? I have to find out Vs equals to AVR plus BIR, correct? So this is my IS, this is my Vs, this is my VR, and this is my IR. Now uh, what kind of KVL I can do, that is what I'm thinking about. I need my, will I be able to get my B and R here? Okay, so this, right, if I apply KVL here, both IS and IR will be there. mm, okay. Okay, so let's do one thing, let's find out A and IS, right? So I know IS is equals to C VR plus DIR. Now let's make IR to be equal to 0, right? Then I will be able to find out A and C, and from that I will be able to find out these values, because I have two equations here as well, right? So if I make IR equal to 0, then Vs by Is will be equals to what? Vs by Is, or what is VR equals to? If this current is 0 here, it will be simply voltage division, right? So it will be, here what is the impedance? It is 1 by Y. It is 1 by Y. It is admittance, inverse of admittance, divided by Z by 2. This is the admittance here, plus simple voltage division, right? 1 by Y. That is what my VR is in terms of Vs. So from this I will be easily be able to find out what is my A. So what will be my A here? So my Vs will be equals to 1 by Y will get there, Z Y by 2 plus 1 into VR. So this is my A basically. This is my A, and this will be my D as well. D and A are same because network is symmetrical. Okay. Uh, yeah. Now, what about C? So I will find out my IS current in terms of Vs. So what will be this IS current? So in terms of VR, right? What is IS current will flow through here only. It's a series circuit, right? So whatever is the potential here, that is VR only, because this drop is 0, right? This drop is 0. VR divided by the impedance here will be my IS current. So VR divided by the impedance, that is inverse of admittance, that will be equals to my IS current, right? So my IS equals to Y into VR, simple as. So my C becomes Y. So I got my A, I got my D, I got my C, I just need my B. So I'll put it here in this equation. So A is this value, 1 plus and D I is the same thing only, right? 1 plus ZY, A is equals to D, minus B I need the value, and C is simply Y equals to 1. So yeah, this will be 1 plus ZY by 2 whole square plus ZY. By. Okay, this 1 will get cancelled basically. Now this y also will get cancelled. So ultimately what will I have? This will be Z by 2, Z square by 4 into Y plus Z, or B is equals to this, or if I take Z common, right? Z if I take common, this will be ZY by 4 plus 1, Z into ZY by 4 plus 1. That is what my B will be equals to. Okay. So yeah, that's the derivation basically. That's it. That's what you have to do. So ESC, you have to remember the result. For gate, derivation is also fine, right? So yeah, let me write down the ABCD parameters here basically. So the transmission line parameters of this star network, right? Star network will be A is 1 plus YZ divided by 2, B is What did the B go? B I just found out, that is Z into and C is Y, and D is D is same as A, right? That is okay. So I hope it is clear now. I hope the ABCD parameters for this T network, or for this simply like nominal approximate T model, or sometimes it is called as nominal T model, right? Nominal T model is clear. Nominal T model. Okay. So yeah, let's do a bit of thing. Let's draw the phasor diagram for this. Let me draw the phasor diagram. So if I take this circuit again, so I hope you know what is Z and Y, right? So I have not explained it, but that is like we have done this already. Z is simply R plus JXL, and Y is simply JBC, or inverse of XC. Okay, like 1 by omega C. I hope that is clear. Let me draw the phasor diagram. Okay, so phasor diagram. Okay, how will I draw the phasor diagram? So this capacitor will deliver some reactive power at the receiving end also. Okay, IC current will be here downwards, right? So my IS current, right, phasor format will be equals to IC plus IR, right? What is IC? Let me assume a potential here, and let me assume this is Y, right? This Y, or I can assume this to be 1 by j omega C. Okay, so this, let's assume this potential to be VC. So IC will be equals to VC divided by 1 by j omega C, right? Or yeah, IC will be equals to j omega C VC. I need to find out what is my VC. How will I find out VC? So if I apply a KVL in this loop, right, my Vs will be equals to Is into R by 2 plus J XL by 2 plus Vc. Okay, so that will be my Vc basically. Is there any other way? Trying to think of any other way, because Vr will be my reference, right? Vr, or instead of writing a KVL in the input loop, let me write a KVL in the output loop. If I write a KVL in the output loop, my Vr, right, minus of Vr. Now current IR is flowing like this, so this is plus, this is minus, right? So this will be minus, KVL will be minus of IR into R by 2 plus JXL by 2, then you have plus VC, right, equal to 0. So your VC is simply VR plus IR into R by 2. These are, remember, phasor, all phasor, plus J into XL by 2. Okay. So VR is always reference, right? The receiving end voltage is always the reference. So VR is here. Then I have IR, and then I have to add, like, IR is, let's assume, any lagging load, right? Any lagging load phi R, like cos phi R. Now I have to add this drop with VR, that is IR into R divided by 2. IR into R divided by 2 will just be in parallel with IR, and I have to add this drop. It will be somewhere here, right? I hope I'm not making any mistakes. Yeah. So IR into R drop will be in the bottom. Then this drop is what? This drop is IR R by 2, and then again I am multiplying plus J. Plus means rotate in the anti-clockwise direction by 90 degrees into XL by 2 into IR into XL by 2. So this will be rotated by 90 degrees, and I have to add this drop, IR into XL divided by 2. So my IC VC will be what? VC will be this whole thing, VR plus this whole drop. So VC will be, like, if I just write this triangle, complete this triangle. So VC will be from the reference, it will be this. This will be my VC. This is my VC. Now what will be my IC current? Now VC is this. IC will be what? IC will be leading VC by 90 degrees. That is the behavior of a purely capacitive circuit. So IC will be leading VC by 90 degrees. Okay. So this is what my IC is equals to. Now, yeah. Now this will be 90 degrees. Now what will be my IS? IS will be, as I have mentioned, IS will be IC plus IR. So IC plus IR, addition of these two vectors, basically, right? Addition of these two vectors. So what do I notice? One thing I notice here is that my IS current, the magnitude of IS current is actually smaller, right? If I see the length of this vector is smaller than length of IR vector. Why is it happening? So the magnitude of IS is smaller than magnitude of IR. What does it mean? This means that this capacitor is actually delivering some reactive power to the receiving end, so that this current is reducing, so that the losses is reducing, right? So this basically means the capacitor is delivering lagging reactive power. Okay, capacitor is delivering lagging reactive power. I hope that is clear. Right now, this is a very important thing that can be asked in MCQs. The sending end current, what is the comparison between the sending end and the receiving end current, right? Now what is my VS? Now VS is what? Now I can apply the key loop in the input KVL. So VS will be what? VS, right, will be simply this drop plus VC. So VC plus IS into R by 2 plus J XL divided by 2. So VC is over here, right? And I have to add this drop IS into R by 2. IS is over here. So IS into R by 2 will be what? It will be parallel to IS, and it will be here, right? And plus J. So this, let me write this first. IS into R by 2, and then I have plus J XL plus IS into J XL by 2. So this will be 90-degree perpendicular to this. This will be okay. Now this overall length will be my VS basically. Now the thing is this, right? I should show it somewhat lagging or leading. Like my VS can lead, actually my like current can be leading due to the capacitive behavior of the line. It can be leading as well. So I'm showing a bit of leading behavior. We exactly will not be able to say whether it will be leading or lagging, the sending and power factor. I will not be exactly able to comment, but it will be somewhat like that only. Okay. 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 So yeah, this is my VS, right? And this is the phasor diagram basically. Now let's do the same for uh, okay. Now like voltage regulation and all those things, I hope you'll be able to do. What is the voltage regulation for a T model, right? Voltage regulation for a T model. Don't need to remember this, just understand, just remember the ABCD parameter. For ESC aspirants, for gate you can derive it, right? I feel this will not be asked in gate, but still no chances. Just understand the derivation and try to solve accordingly, right? So it will be Vs divided by A minus magnitude of VR divided by VR into 100, right? So what is A? A is basically, A is 1 plus YZ divided by 2. So your voltage regulation will come out to be Vs divided by 1 plus, okay, Vs I may not know, right? Vs divided by A. Yeah, Vs will be 1 plus YZ divided by 2 minus VR full load. VR full load will be given to you. Your supply and voltage also will be given to you, right? No load. This is the no load receiving end voltage. VR no load, right? Divided by VR full load. These values Vs, VR, these values will be given to you, right? Into, okay, 100. So this will be your voltage regulation percentage. So I hope it is clear to you. Let's solve a very basic question with this particular concept, and then we will move on to the pi model. Okay. So in a three phase 138 kilovolt, so three phase 138 kilovolt line, okay, transmission, like it is, nothing is mentioned, we'll assume it to be line to line voltage, right? Supplies a 49 megawatt load at 0.85 power factor. Lagging power factor. The transmission line has an impedance Z equals to 9578 degrees. 78 degrees. Admittance y will be, okay, what admittance y is given to us 0.00190 degrees, that is like purely capacitive, and the line is 80 kilometers long. But is it important? Like then it specifies that it is a medium transmission line, basically medium transmission line, because it is 80 kilometers, it has to be medium transmission line, right? Using equivalent T circuit representation, calculate the following ABCD parameters, right? So equivalent T, right? You know what is equivalent T. This kind of questions will be asked in mainly EAC only. So the equivalent T here will be, I will have Z by 2, here I will have Y, here I will have Z by 2. Now as I have just derived the ABCD parameters, I will not again derive it, right? I will directly write the ABCD parameters. I is IR, so this is IR, this is, right? So your ABCD parameters of the T network will be equals to 1 plus zy divided by 2. This will be z into 1 plus zy divided by 4. This will be y. This will be 1. Now this will be 1 plus zy divided by 2. Right? This is what we derived. If I am not, if my memory is okay, yeah, memory is okay. So yeah, we'll just have to put the values over here. That's it. Right? So z into y. So this will become 1 plus, I will not, we can solve it as well. This will become 0.0, so 95 into 10 raised to the power minus 3. Divided by 2 is also there, right? Let me calculate this. Okay, so this becomes 90 plus 78, and this will be z into this, right? So 95, 78. Now this actually is very small, correct? So it will not make much of a difference actually. So this will be roughly 1 only. You got this will be roughly 1. And here as well, the zy by 4 will be again very small compared to 1. So this will be roughly equals to 95, 78 only. And this will be y, this will be 0.01. Angle plus 90, and this will be, of course, this will be again roughly equals to 1. Okay, so I'm just doing rough approximations here. We can do that, right? So yeah, now what they are asking, ABCD parameters, roughly this will be 1, this will be roughly 95, 78. Okay, this will be my ABCD parameters. This is the first answer. Second answer will be the sending end voltage. What is the sending end voltage? So what is the sending end voltage? So what is Vs? I can use the ABCD parameters, right? Vs is equals to AVR plus BIR. What is my receiving end voltage? Face to face. This is a per phase equivalent model, right? Face to face voltage will be 138 divided by root 3. And what is my IR? Angle 0. IR will be, they have given me the load, right? And it's a three phase circuit. If it's a three phase circuit, then it will be a three phase power. So this will be 49. This is in mega, right? I will keep it in mega. I will write the root 3 into VL. VL is 138 into cos phi. Cos phi is 0.85. .85. So angle will be what? Angle will be cos inverse of 0.85, cos inverse of 0.85. So 0.85 cos inverse, this will be 31.78 degrees. So this comes out 49 divided by root 3 into 138 into 0.85, 0.24 degrees, right? So your Vs will be AVR, A is 1, so VR is 138 divided by root 3. Everything is in kilovolt. Current is also in kilo, so that's why it also becomes kilovolt. B is 95 angle 78, and your IR will be this value 0.242 angle minus 31.78. So what it becomes? What does your value become? So this will be into 95, so this becomes 22.912, and 138 divided by root 3, this becomes 79.67 plus, and this has an angle, that is 78 minus 31.78, that is 46.22 degrees. Okay, now 22.912 into 46.22 cos, so this becomes 15.85, 79.67 plus j 46.22 sine into 22.912, so this becomes 16.54. so 79.67 plus 79.67 plus 15.85, 94.52 plus j 16.54, this whole square plus 16.54 whole square whole in the root, it becomes 96.94, and the angle would be 16.54 divided by 95.52 tan inverse, angle becomes 9.823 degrees. This will be your angle. From this you can also find out the sending end current as well. Okay, so yeah, this is your angle basically. So these are all approximate, right? These are all approximate values, because I have, like, in your exam you have to do approximations, like otherwise it will become very lengthy, that those complex calculations. Almost the value will be this only. Okay, you will see exactly, if you find out, you will see this value only. Okay, now let's next what they are asking. They are asking the sending end current. Sending end current, I have to use the second equation of ABCD parameters, that is IS will be equals to CVR plus DIR. So what is my C? C is this 0.001 plus 90, 0.00190. VR is 79.67 kilovolt angle 0 plus D into IR. D is simply 1 and IR is simply this value, right, in kilo amperes. So this will be 0.242 angle minus 31.78 degrees. 0.0001 right here. So 79.67 into 0.001, that is 0.0767 angle plus 90 plus 0.242 0.242. Okay, this I can break it down, right? This will be simply J. This can be broken down into 31.78 cos 0.7 minus J 0.1274. So this will come out to be plus 0.07967 0.0478. Remember, this is in kilo amperes, right? This is in kilo amperes. Everything is in kilo. So this, right, this divided by this whole square plus 0.2057 whole square whole under root. This comes out to be 0.2117. You see, right? One thing you observe, that the sending end current, magnitude of the sending end current is lower. That isn't that what we saw in the phasor diagram, right? So what is the angle now? So 0.0478 divided by 0.2057 tan inverse. It is something negative, minus 13.08. So here, yeah, this current is also lagging, so that is fine. But what do you observe? You observe that the magnitude of IS is less than the magnitude of IR. Isn't that what we discussed in the phasor diagram, right? So this was the third portion. Now they are asking us the power factor, cos phi s, right? Power factor will be what? Sending end power factor. So cos phi s will be simply cos of angle between the sending end voltage and the sending end current. So cos of voltage has an angle of plus 9.823 degrees and minus of 13.08 degrees, right? So plus 9.823 cos, yeah, this comes out to be 0.92. Power factor is lot improved here, right? Lag, but still it has improved. The receiving end power factor was 0.85. So the capacitor, the charging current is actually helping to improve the power factor further. Okay, so yeah, we can now move on to the next model, that is the pi model, right? So pi model, again we can derive the things over here. This will be your z basically, and this will be your y by 2, this will be your y by 2. Okay, so I can write two KCLs at this node and at this node, right? So KCL at node 1, this will be minus of, like here the current is coming, right, IS, here the current is leaving IR. Here the voltage is Vs and here the voltage is VR. So KCL at this node and at this node. So minus of Is plus Vs into y by 2, because it is impedance by impedance. Impedance is basically inverse of admittance, that is 2 by y, right? Impedance is inverse of admittance. What is the admittance here? Y by 2. So impedance will be 2 by y inverse. Then I have plus Vs minus Vr divided by the impedance between these two nodes, that is Z, okay, equals to 0. Okay, I got this value. I actually have to eliminate IR, that is one thing. And if I write the uh, next KCL equation, that is IR plus VR minus Vs divided by Z plus VR into y by 2 equals to 0. So your this is Z, remember this is Z, right? And this is 2 actually, okay. So if I take this Z on the side and if I multiply Z, right, so this will be VR YZ divided by 2. VR is also here, right, plus 1, so this will become yeah, plus 1 VR Z by 2 plus 1, and then I will have this Z into IR, okay. So that is what your like like A and B will be, right? A and B will be this value. Now let us calculate for your B and C. Now is this network symmetrical? Again, this is network is symmetrical because about the middle, if I see yeah, I can break this down, right? This network is again symmetrical. I can break it down, although you can find it out from here, and I have derived how to find out the like parameters for a pi model, right? But we will do it something else. Like of course you can do KVL, KCL, all these things you can do, right? What I can break this down, this network, right? First of all, it is reciprocal, that is for sure. So my AD minus BC will be equals to 1 because it contains RLC elements only. Now is it symmetrical? So I can break this network down like this. Now does it seem symmetrical? Previously I think you were saying that no sir, this is not symmetrical, but now I hope it seems like it is a symmetrical network, right? JBC by 2, JBC by 2. So if I observe on the left hand side, I'm seeing same kind of network, on the right hand side same kind of network, right? So it is symmetrical, so that's why A also will be equals to D. So simply from here I can directly find what is my A. This is my A, this is my B, right? My D will be what? D will be simply A, that is ZY divided by 2, and your C will be C you have to find out. So your C will be A into D, that is this 1 plus ZY whole square, ZY by 2 whole square, minus B is simply Z into C equals to 1. So this 1 will get cancelled. This will be ZY by 2 whole square plus ZY minus 1 will get cancelled. This will be Z into C. So from here my C I will divide by Z, right? So this will become Z y square by 4 plus y. Your C will be equals to y into ZY divided by 4. Okay, that is what your C is equals to. Yeah, so I hope this part is clear. That is what my C is equals to. Now all the parameters are done, so my T for the ABCD parameter for the pi network, A will be like A is same, zy divided by 2, D is same, zy divided by 2, but just the B has changed. I think B was there different, it was Z into 1 plus zy divided by 4, and your C has changed. It is now Y into, like it is just the mirror image, right? Just the mirror, zy divided by 4. Okay, now let's do the phasor diagram. Okay, so if I do the phasor diagram over here, how will I find out the phasor diagram? So to find out the phasor diagram, what you will do, is uh, phasor diagram of pi network. Okay, okay. Huh. How will I draw the phasor diagram over here? That is what I'm thinking. So there are two kinds of current, right? One is this IC1 current, and then I have this IC2 current, right? So let me first of all write this equation, that my IC, this current, right? Whatever is this current, let me name this current as IX. IX is equals to IR plus IC2. Okay. Now, what is my IC2 current? IC2 current will be simply, let me write this as Y, admittance Y, right? Which is simply 1 by J omega C, and my VC, like VC is simply VR, right? It is directly connected across the capacitor. So I can start with the phasor diagram. So okay, two pages, I'm taking 2 pages. Start with the phasor diagram here. This will be my VR, and let's assume that my IR current is lagging, correct? So my VC will be equals to VR, and my IC will be leading the VR current. So this is equals to my VC only, right? IC will be leading the VR current because it's a capacitor current. It has to lead the voltage. Okay, it has to lead the voltage. So my IX, what will be my IX? IX will be this value. This will be my IX. Okay. Now, yeah, I got my IX. Now, what is the voltage here? It is Vs, right? But what is the voltage here? Voltage here will be simply Vs. Vs will be equals to this drop, right? Ix into R plus Jx by 2. So, plus Vr. So, it is Vr plus Ix into R by 2 plus JXL divided by 2. Okay, so VR is here and I have to add this drop Ix into R by 2. So Ix into R by 2 will be parallel to Ix. This will be parallel to Ix. But of course the magnitude will be somewhat lower right here. This will be Ix into R by 2 and then I have another drop, right, that is 90 degree in the anti-clockwise direction. XL by 2, right? So I have to add like this with VR. So basically my Vs will be this, correct? This is my Vs. What about my Is? What is my Is? So Is is actually equals to this current Ix plus this current IC1, right? What is IC1? IC1 is basically Vs divided by like this Vc1 is simply Vs, right? So let me write this capacitor as C1. So this will be Vc1. This is not a Vc. This will be Vc1, and this Vs will be equals to Vc2. So what will be my IC2 current? IC2 current will lead by 90. So this current actually will be IC1, right? And IC2 current will simply lead this Vs by 90, something like this. This will be my IC2 current. Okay. Now what will be my Is? Is will be the addition of Ix. Ix is here and IC2. So it will be somewhere around here. I will not be able to, I have to use some other color and I have to use bit of this, delete this right here. This will be my Is current. Okay, again you can see the magnitude of Is is again smaller than the magnitude of IR. Okay, so this will be the phasor diagram. So this question I am giving you, okay, I'm not giving you as homework. We will solve this question. So let's solve this question. What are they asking? They are asking that a short transmission line is connected in cascade with a medium transmission line. What is the effect of this cascading on the voltage regulation of the medium transmission line? Okay, so they are asking if I am cascading two transmission lines, short and medium, what is the effect, right? So short transmission line is connected in cascade with a medium transmission line. What is the effect of this cascading, right? Okay. Actually, they should have mentioned that the short transmission line is connected at the load end. So if the short transmission line is connected at the load end, will there be any effect to voltage regulation? So here I have the medium transmission line which will have its ABCD parameters, correct? And then to this medium transmission line in cascade, a short transmission line is connected in cascade with a medium transmission line. So a medium transmission line is there which has its own ABCD parameters, right? And then I'm cascading this with a short transmission line. Now will there be any effect at the voltage regulation? So receiving end voltage, right, full load receiving end voltage is fixed, that will not change. I just have to find out the no load receiving end voltage. The no load receiving end voltage, if at the load end the short transmission line is connected, that means here the drop is 0, right, at no load. So whatever is the no load voltage here, same voltage will appear across here. So here, right, the no load voltage is simply Vs by I, right, and that will be same here, Vs by A, that will not change. A of this ABCD parameter, A of this ABCD parameter, right, correct, because no load voltage in no load, in short transmission line, in no load, the receiving end voltage and the sending end voltage is same. For a short transmission line in no load, the receiving end voltage and sending end voltage is same, right? So that's why here the no load voltage and here the no load voltage will be same, because there is no drop. So if this, as if this transmission line was not there, right, short transmission line was not there, it would not have made a difference, because there is no drop at no load. So the no load voltage here without the short transmission line and with the short transmission line is same. So voltage regulation also will be simply same. It will not change. Okay, it will simply not change. Or like this was the one of the way. This was method 1 to understand this. What is the method 2? Method 2 is simply using the cascading formula. So the medium transmission line will have a ABCD parameter like this, right? And the short transmission line will be having a ABCD parameter like this, right? 1 Z 0 1, right? So if I find out the matrix multiplication, it will be A, this will be AZ plus B, this will be C, this will be CZ plus D. Okay, so you see that the A does not change, right? The A of the overall combined network does not change. So if A does not change, then your voltage regulation also will not change, because your voltage regulation is a function of A only, if you remember, because the receiving end full load voltage will be same. Now what if, like this was the case 1, right? Case 1 where first medium transmission line is there, then short transmission line is there, right? So for case 1 voltage regulation will be same. For case 2, if first I am connecting the short transmission line, then I am connecting the medium transmission line, then things might change. Things will change, not might, things will change. Okay, so if that is the case, you can see first of all short transmission line will be connected. So first of all I will write the matrix of, okay, let me just copy this. Let me write the matrix of short transmission line, then I have medium transmission line connected. So here this will be 1 plus, sorry, A plus ZC, this will be B plus ZD, this will be C, this will be D. So here if you see that your A changes, right, overall combined network, so here voltage regulation will change. Your magnitude of A, it seems like it is increasing, so your voltage regulation, because is basically what it is Vs by magnitude of A, right? So if A is increasing, then your overall voltage regulation will reduce. Okay, so in this case VR will reduce, and it makes sense as well, because I am connecting a capacitive network, right? Capacitive transmission line in medium transmission line, the to the short transmission line as if I am connecting a leading load, to the short transmission line as if I am connecting a leading load. So of course if I am connecting a leading load, the voltage regulation will get better, that is it will reach more towards 0, that's why the voltage regulation reduces. Intuitively also you can understand this. Okay, I hope it is clear. What is the effect? Okay, same question is here. Okay, medium transmission line is connected in cascade. Okay, actually this, right, I've already explained this, we don't need to take this question, already have taken the second case, right? We don't need to take this question. Okay, so yeah, that is the case over here. Now in modeling of a medium long, let's do this question. In modeling of a medium and long transmission line, the nominal pi and nominal t circuits are not equivalent to each other, because they are both approximations, right? They will not be equivalent, they are approximation. A star delta transformation can be used to derive the one circuit from the other circuit. Okay, star delta conversion, derive, no, both. Okay, so first of all, in the modeling of medium and long transmission lines, nominal pi and nominal t are not equivalent to each other. Yes, they are not equivalent, but they are approximate models. I have explained them already. So this first statement is correct. So A is true, right? A star delta transformation can be used to derive one circuit from the another. Is it correct? Actually, it is not correct. So your nominal t, here I have z by 2, here I have z by 2, here I have y, right? And your nominal pi is, here I have z, here I have y by 2, here I have y by 2. You tried, right? You try to do the star delta conversion, right? They will not be equal. These will be not equal, right? These are different. These are approximations, different kind of approximations, but these will not be equal. Okay, so R is not true, R is false. So A is true, R is false. So option C will be the correct answer for this question. Okay, so the same thing is written over here. Whatever I've explained, same thing is written over here. Okay, so yeah, that's it basically for this lecture. In the next lecture, we will start with long transmission lines. After that, we will do the assignment questions, and this whole chapter will be finished. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the next topic of this chapter, that is long transmission lines. So we will discuss what happens in long transmission lines. Effect known as transient time effect will occur. Briefly, I have discussed about this transient time effect in the medium transmission line, but here we will go much deeper into it. So let's say this is my sending end and this is my receiving end, right? Sending end and my receiving end. So this point potential is Vs and this point potential is Vr. Now I'm giving a sinusoidal waveform. Sinusoidal waveform, Vs into t. Okay, I'm giving a sinusoidal waveform. Now if the length is much smaller, you will expect that in the output as well I will get a sinusoidal waveform. Of course, the amplitude will be something else, but I will get a sinusoidal waveform here, no problem, right? But in case of long transmission line, of course, this voltage, right, potential at this point, it is traveling from point A to point B. It takes some time to travel from point A to point B, right? So of course that will have effect, because let's say at t equal to t1, here the Vs is maximum Vm, but due to this transient time effect, I will explain what is this transient time effect. The receiving end voltage is not equals to Vm. The receiving end voltage is equals to minus of Vm, right? Now this is very negligible in case of a medium and small transmission line, but for a long transmission line this will be actually considerable. This might have some problems. Okay, and here, right, the parameters are distributed. That's why you cannot simply do the analysis. Parameters will be distributed. I will explain that. So first of all, let us understand what is transient time, right? Let us take example. Let's take example that the length of the transmission line is 1000 kilometers, and let's take example that the speed at which this wave travels, right, voltage waveform travels, is Vc, that is 10 raised to power 8 meter per second. Actually it is pretty near about light only. Okay, so I'm just taking an example that it is 10 raised to power 8 meter per second. Just an example. Now what will be the time required for this waveform to travel from point A to point B? Okay, let me take more examples. Let's take this example that this is the length of the long transmission line, right? Long transmission line. Okay, and let me take another example, length of the short transmission line. Let's take 10 kilometers. Of course, the speed of the voltage waveform will not change. that will be same, that is 10 raised to power 8 meter per second. Okay, 10 raised to power 8 meter per second. Now what is the time taken in the case 1 and what is the time taken in the case 2? So tx1 will be what is time? Time is distance upon velocity, right? Distance upon velocity. So it will be 10 kilometer, that is 10 into 10 cube divided by velocity, that is 10 raised to power 8. This will be equals to 1 by 10 raised to power 4, that is 0.1 milliseconds. Okay, so to travel from point A to point B for a short transmission line, it only takes 0.1 milliseconds. And let's assume that our frequency, right, we're operating at 50 hertz. If I'm operating at 50 hertz, what is the time period? Time period is 20 milliseconds, right? So are you able to see that my transit time, the time it takes for the wave to travel from point A to point B, is much smaller than the time period of the whole waveform. So the effect will be negligible in case of short transmission line. Now if it is a long transmission line, then the distance will be 10 cube into 10 cube divided by 10 raised to power 8. So this will be equals to 1 by 100 or 10 milliseconds, right? Now these are comparable. Now tx2 and t is actually comparable. It is just half. So the time that this point voltage takes to go from point A to point B, already the waveform here has changed. Right? So that is a problem. Now what if I increase the frequency? If I increase the frequency, T will reduce. Let's say I'm increasing the frequency to 50 kilohertz, 50k. What will happen to T? T will become 0.100 if I divide by 100, 0.02 milliseconds. So you're observing, right? If I'm making it 50 kilohertz, now the time period has reduced. Now this also is comparable, like this higher. So that's why I have told you multiple times previously, this frequency is actually very important. Frequency into length is the ultimate factor, right? So in communication systems, if I increase the frequency, then also my short transmission line, even though the length is smaller, it will behave as a long transmission line. There will be effect of transient time. Okay, so that's why this factor frequency is also very important. Not just length. Yes, length is important, right? Frequency is also very important because we compare it ultimately with the time period. Okay, length is important, but frequency is also very important. So the product of frequency and length are the two important things that you need to keep in mind. Okay, so this kind of effect is known as transient effect, right? In long transmission lines, the voltage and current no longer behaves as steady state sinusoids, because when I'm at this point, right, input voltage is something else, here the voltage is something else, here the voltage is something else. So they do not behave as purely like steady state sinusoidal. There will be waves. There will be two waves. I will explain about that. But instead exhibit wave-like behavior due to the significant time it takes for signals to travel along the length. The wave propagation is especially prominent when the product of the frequency and length is very large, that is 10,000. Okay, now as the length of the transmission line increases beyond 200 kilometers, the electromagnetic signals take finite time to propagate from sending end to receiving end. This delay causes a transient effect, while the signal seen at the receiving end may be out of phase or even inverted compared to sending end. Basically, if I'm providing plus Vm at the output, at the same instant I'm getting minus Vm, right? That is inverted. How can you get minus Vm? That means there is a phase shift of 180 degrees. How can you provide a phase shift of 180 degrees? That is not possible. So this behavior can only be explained with the traveling wave theory. So that's why there is a theory known as traveling wave theory. So to explain this, right, phenomena, that I'm providing plus Vm at the source, I'm getting minus Vm at the receiving end. That means someone has to explain this. That behavior will be explained by traveling wave phenomena. Okay, so this effect is known as transient time effect. Okay, so what is happening is, as I am moving along the line, right, so this is my transmission line. Here the voltage will be something else, here the voltage will be something else, here the voltage will be something else. Voltage will be a function of x, it will not be just a function of time. Voltage and the transmission line will be a function of x. Okay, so yeah, that is what I'm trying to explain. So if there is no transient effect, then if your Vs at this particular point is here, then your Vr also will be here, just with a bit of delay, right? It has a bit of delay, so Vr will be Vr will lag, it will be somewhere here. But if the transient time here, right, the transient time is negligible, is negli negli negligible. What is the spelling of negligible? This is the spelling of negligible, right? I was bored. Okay, so and here, right, transient time is considerable. Transient time is considerable. So if your Vr is lying somewhere here, right, let's say if your Vr is lying somewhere here 0, and your Vs will be maximum. Sorry, if your Vs is lying somewhere here, Vr will lag, like maximum. Like Vr will be much slower compared to Vs, right? So those things we have explained. Now, can we ignore stuff? Can you ignore R, L, C, G, all these things? The answer is no. This time I will not be able to ignore. Anyways, we never ignored RL, right? Now we will not be able to ignore G as well. Why? Because the voltage also will operate at high voltage. Why we will operate at high voltage? Because the current must be lower, because this resistance has increased. So we have to lower the current. How can I lower the current? By increasing the voltage. If voltage is increased, then there will be some leakage current to the ground. So this G will be now considerable, cannot ignore, considerable. Now one more thing is that I cannot ignore the distributed parameters, because I've already told you that in case of low frequency, in case of small transmission lines and medium transmission lines, I told you we can lump the resistor, inductor, capacitor together. But in large transmission line, in long transmission lines, I have already told you that your voltage will be a function of x. So here the voltage will be something else, here the voltage will be something else, here the voltage will be something else. So I cannot lump all this. If I lump, right, if you say you're lumping the resistor, you're lumping the inductor, you're lumping the conductance, you're lumping the capacitance, that means voltage here is fixed, here voltage is fixed. But I am telling you that you cannot make it fixed. In medium transmission line, in reality, voltage is not fixed actually. That's why, if you remember, I told you it is nominal pi model, it is nominal T model. Why it is nominal? Because the voltage is not fixed there. But we are very lazy, so we told ourselves that who will do that much rigorous analysis for medium transmission line? Let's do approximations, and our answers will almost match. But in long transmission line, you cannot be lazy. You cannot say I will lump everything and just do the analysis KVL KCL. Here KVL KCL will be violated. KVL KCL will not work. KVL KCL will not work. Why? Because at each point the voltage is changing, and I have to do some different kind of analysis. That is the traveling wave analysis. Okay. So that is the thing. How will I do the traveling wave analysis? I will explain that. But I hope now it is clear that this is a distributed parameter. This is a distributed parameter, right? You cannot do that approximation here. Okay, so I hope that is clear now. I hope that is clear now. Now, what I can do? What can I do? Now, like we have to do the analysis. How can we do the analysis? We will see. So what we'll do is we will take a very small section, right? Very small section. Let's assume that this is my very small section. Okay, let me use some other color. That is delta x. If I take delta x, because here the distance is very small, delta x is very small, right? The transient effect will be negligible. The transient effect in this small section, the transient effect will be negligible. Transient effect will be negligible. Let me just check the spelling of negligible. Otherwise I will mess it up. Negligible, yeah, I'm correct only. Negligible. Okay, so yeah, that is what we will do. That is what we will do. We will try to see that. So if I see a very small section, and let me assume that my this, right, r plus jl xl is z z1 r1 plus jxl1. Let me write this in small, or omega l1. This is z1. What is z1? What is r1? R1 is resistance. I think I have written that somewhere, or haven't I? I have not. Okay, I have not. So R1 is, because whatever we're discussing with length, right? So R is not the whole resistance of the whole wire. R is resistance per unit. So I should actually write this in small, or let me keep it R only. That is fine. But I will break it down. R1 will be resistance per unit length. Okay, your L1 will be inductance per unit length. Your Z1 will be the impedance, series impedance per unit length. Okay, and what about this one? G1, right? Your G1. So I can combine this one as well as Y. Okay, this also can be combined as Y for our simpler analysis. So G1 will be conductance per unit length. Okay, and your C1 will be uh, capacitance per unit length. Let me write down the units as well, so that we don't mess up with the units. So here the unit will be farad per meter. Here the unit will be Siemens per meter. Here the unit will be ohm per meter. Here the unit will be Henry per meter, and here the unit will be ohm per meter. So I'm just considering a very small section. What will be your y? Your y, right, is admittance, y1. So what is your y1? y1 is the shunt admittance, the equivalent shunt admittance. This is the equivalent series impedance, equivalent of R1 and L1. Shunt admittance per unit length. Okay, so I will consider a very small section delta x that will obviously have R, L, G and C, right? So I will write my equivalent here. I don't have enough space, so let me reduce the size of this, or let me reduce the size of this. Let me take few things in the second line. Okay, what will be y1? So let me draw the circuit. So I have here RL. So I'm considering a very small delta x of length, right? So this length, right, is delta x. So there will not be like much of transient effect over here, correct? So I can combine this whole thing. This will be my 1 by j omega c1. This will be my g1. Remember here, right, this length is delta x. So what will be this capacitance value? It will be c1 into delta x. What will be this conductance value? It will be g1 into delta x. What will be this inductance value? J omega L1 into L1 into delta x, and this resistor value will be R1 into delta x. Okay, R1 into delta x. Right, now let's solve this. So okay, how do I solve this now? So the thing is, first of all, this will be my x equal to 0 position, because always the receiving end will be reference. Okay, and this will be my x equal to L, capital L, right? So receiving end will always be the reference. That's why your x equal to 0 will be at the receiving end. Okay, so this, right, whole thing I can convert into Z1. What will be y1? Y1 will be simply g1 into delta x plus j omega c1 into delta x. Okay, I hope it is clear. Now I can convert this whole thing into a equivalent series impedance Z1 and equivalent shunt admittance y1. And the ABCD parameters for this is very simple, not that difficult, but at this point we will not compute the ABCD parameters. So I have told you your current and voltages will be function of time as well as function of distance. That's why it will behave like a wave phenomena. Why wave? Because Why wave? Because wave, in case of wave, this I have taught in machines as well, that your voltage and current will be function of both distance and time. That's why it will be like a wave phenomenon. So if my receiving end is the reference, so if the voltage here is V of x and current here is I of x, can you tell me what will be the voltage here and current here? So this whole length is delta x, and I have already told you that your voltage is a function of displacement. So this side, the current will be I into x plus delta x, and the voltage will be V into x plus delta x. Okay, because this point is x equal to x, and what is this point? This point will be x equal to x plus delta x, because this distance is delta x. Okay, so for this small network I can apply KVL KCL, because here delta x is very small, right? So here I can apply KVL KCL, but in a large network, as it is distributed, I cannot apply. For a it is behaving as a short transmission line, right? So for a small network, I can apply KVL and KCL. So I will apply a KVL here. I'll apply KVL here, right? So if I apply a KVL here, my minus of V of x plus delta x plus I of x plus delta x into z1 plus V of x equal to 0. So I understand that this will be equals to V of x plus delta x. Hold on a second. Okay, this will be z1 into delta x, right? I forgot to write, because z1 is this value, so I have to multiply z1 into delta x. Sorry, this also will be only g1 plus j omega n1. This is admittance per unit length. So if I want to find out admittance, overall admittance, I have to multiply by delta x. I forgot that. So here also I have to multiply by delta x. So this will be z1 into delta x, right? Because this part is constant. Z1 is a constant number, impedance per unit length, but the other part is not constant. Okay, so V of x minus V of x and this is equals to plus delta x, right, into z1 into delta x. Now I can write what is my I, of x into delta x, right? That is what I want to write. So if I put this delta x in the bottom side, so I can say that my I of x plus delta x will be equals to, there will be 1 by z1. Okay, then this will be V of x plus delta x divided by delta x, right? Now I have told you that delta x is very small. What if I tend my delta x to 0? Is this expression familiar? This is nothing but d of vx upon dx, right? If x tends to 0, it is nothing but d of uh, Vx upon dx. This z1 I can keep it over here only, right? So basically the conclusion is, if x delta x is tending to 0, because that is our main purpose, we don't want to do any approximations, I want to make my delta x tending to 0. If delta x tends to 0, I get this first equation, that dvx upon dx will be equals to z1. Here if I put delta x equal to 0, this will be 0, this will be x plus delta x, so this will simply be z1 into I of x. Okay, this is the first equation that we get. Similarly, I can apply KCL now. I'll apply KCL at this node. I have only single node, so I'll apply KCL at this node. So if I apply KCL at this node, if I apply a KCL at this node, now I will apply KCL. Okay, so KCL here will be I of x plus delta x equals to, incoming should be equals to outgoing. What is outgoing? Vx by y1, Vx into, because it is admittance, so Vx, V of x into y1 into delta x plus I of x. That is incoming current equals to outgoing current. Again I will apply the same formula, that I of x plus delta x minus I of x divided by delta x will be equals to y1 V of x. Okay, so now again I will make my delta x tending to 0. If delta x tends to 0, this will be d of ix upon dx will be equals to y1 into V of x. So we get two equations now, right? We get two equations. Okay, so if I differentiate this equation again, if I differentiate, this is equation 1 and equation 2, right? If I differentiate equation 1 again, what will I get? So differentiating equation 1, I will get d square with respect to x obviously upon vx into dx will be equals to z1 into di upon dx, and di upon dx is nothing but y1 into v, right? So this will be y1 into v of x. So we get a standard second order equation. I hope you can solve this standard second order equation, right? Second order differential equation. So this becomes d square v of x by d of x minus z1 y1 into v of x equals to 0, right? It's a very standard differential equation. What is the solution? So this will be what? This will be m square, or this will be d square minus z1 y1 into equal to 0, right? Or m square minus this equal to 0. I'm just like, I hope you know differential equation. Okay, if you don't know, please go and study that. I will not explain here. I will have to find the roots here. So the roots will be, m will be equals to, it is unequal real roots, real and negative roots. So it is plus minus z1 under root z1 y1, right? So I will have, the solution will be c1. So my v of x solution will be c1 e raised to power plus root z1 y1 into x plus c2 e raised to power minus root z1 y1 x. Okay, this z1 y1 has a special name, right? Z1 y1 has a special name, so it is known as gamma. Gamma is equals to z1 y1, which is equals to the propagation constant. Propagation okay, propagation constant, which is equals to the propagation constant. Okay, so now this, right, this can be written, rewritten, v of x can be rewritten as c1 e raised to power gamma x plus c2 e raised to power gamma x minus e raised to power, sorry, as e raised to power minus gamma x. So these two are, both are decaying waves. Now you might have a doubt, you might have a very interesting doubt. Decaying waves meaning that if I am at this point, at this position, I will see two waveforms. One will be on the right hand side, one will be on the left hand side. That's why it is sum of two waveforms. Sum of two waveforms, decaying waves. Now you might have the doubt that how are these decaying? This I understand. Okay, minus is there. So if x is increasing, this will decay. But how, sir, this will decay? How, sir, this will decay, sir? So the thing is, your x, right? If I show you, one wave will travel from right to left. One wave will travel from right to left, right? So it is what? It is backward wave. It is not moving forward direction. It is moving backward. If I'm moving from right to left, my x is increasing, right? If I'm moving from right to left, moving from right to left, right? So first of all, let me draw the x, right? This is x equal to 0, this is x equal to L. So I'm moving from right to left, my x is increasing. Can you tell me what will happen to my e raised to power minus x? If x increases, e raised to power minus x will reduce. So this, right, is the decaying wave in the backward direction. So this is the backward traveling wave. And here, if I go from left to right, what is happening? My x is reducing. What will happen to e raised to power x? If x reduces, e raised to power x, right, also will reduce. So this is also decaying, but in the forward direction. Okay, so this wave is forward traveling wave. Okay, so basically we forward also with respect to time, right? Not with respect to time, sorry, with respect to distance. This will not be time, this will be distance, right? Both will decay. Okay, so with respect to distance, both will decay basically. I hope that is clear now. So I want to derive the expression for the current. So I can see from the equation 1, right, what is my current equal to? Current is equals to dv by dx by z1. So I know what is my voltage. Voltage is this value. So what is dv by dx now? Dv by dx, right, and I have to divide by z1. That will be my current ix. So if I do the dv by dx, this will become c1 gamma into e raised to power gamma x minus c2 gamma. Okay, minus gamma will obviously be there, gamma will be there, minus gamma x, right, and divide by z1. So your gamma is under root L1 by C1. That is what we know, right? Gamma is under root L1 C1, right? Gamma is under root Z1 C1. So what am I talking about? Gamma is under root Z1 C1. Z1 Y1, right? So if I take the gamma common, this will be under root Z1 Y1 C1 e raised to power gamma x minus C2 e raised to power minus gamma x divided by Z1. Okay, so this will be under root Y1 by Z1, right, which is equals to actually under root Z1 by Y1. Under root Z1 by Y1 actually is known as the characteristics impedance, okay, ZC. This is known as the characteristics impedance ZC. Okay, so now this I can replace, right? So this will be C1 e raised to power gamma x, C2 e raised to power minus gamma x. Okay, so this will be C1 e raised to power gamma x minus C2 e raised to power minus gamma x divided by ZC. Okay, this is the equation for current. This was the equation for voltage. And this is the equation for current. I hope it is clear, right? So now we will apply the initial conditions. I mean the H conditions, right? At x equal to 0, what is happening? What is the voltage at x equal to 0? At x equal to 0, right? At x equal to 0, the voltage is what? It is on the receiving side. So voltage is VR, current is IR, right? So V of x will be VR and I of x will be IR. Correct? Because if you see current, right, current is outgoing, right? So at this, if this is the receiving end, this will be IR current, this will be VR current, this is VR voltage. So I will replace here x equal to 0 and I will put V and I. So this will be x equal to 0, so C1 plus C2 will be equals to VR. C1 plus C2 is equals to VR, and your C1 minus C2 is equals to by ZC equals to IR. So C1 minus C2 equals to ZC into IR. Okay, ZC into IR. I can add these two up, so I will get 2C1 equals to VR plus ZC into IR. So C1 will be equals to VR ZC IR divided by 2. Okay, that is what my C1 is equals to. Similarly C2 will be what? C2, if I subtract these two, right, if I subtract these two, and then if I divide by 2, it will be VR minus ZC into IR divided by 2. Okay. So this C1 was for the forward wave and this C2 is for the backward wave. Okay. So this is the forward wave amplitude, and this is the backward wave, right? So these things I hope you can derive, right? So from here, right, we will break it down. We'll break it down. So what is my V of x? As I've told you, what is my V of x? So V of x is C1 e raised to power gamma x plus C2 e raised to power minus of gamma x, which is equals to this value, right? So this is my V of x basically. Now what will be like I can write my current as well. I will put the current later. Let me write the voltage at x equals to L. X equal to L, what will be the voltage? At x equal to L, I am at the sending end side. So my voltage V of x will be Vs. V of x will be Vs when my x is equals to L. Okay. So this will be equals to VR plus ZC IR divided by 2 into e raised to power gamma L plus VR minus ZC into IR divided by 2 into e raised to power minus of gamma L. Okay, I can combine few terms over here. So this will be, I can combine VR by 2. This will be 2, I can keep it inside. VR I can combine E of gamma L minus e raised to power minus of gamma L divided by 2 plus ZC into IR I can take common. This will be E of gamma L minus of e raised to power minus of gamma L divided by 2. Now do you remember what is this? It is simply sine, sorry, this is plus, right? It is simply sine cos hyperbolic of gamma L, right? What is cos hyperbolic of x? It is just the real part, right? Imaginary part you will not consider, because cos of x is e raised to power, if you remember, like these things, I hope you remember these things, right? What is cos of x? This will be used everywhere. Cos of x is e raised to power ix minus of e raised to power, sorry, plus e raised to power minus of ix divided by 2. In case of hyperbolic, you just remove the imaginary. You just remove the I. It will be real. This will be e raised to power x minus e raised to power minus x divided by 2. Similarly for sine of x, right? Sine of x will be e raised to power ix minus of e raised to power minus of x divided by 2 sine h of x equals to e raised to power x minus of e raised to power minus x divided by 2. So this actually is cos hyperbolic of x, and this actually is sine hyperbolic of gamma L. So this comes out, your Vs comes out Vr into cos hyperbolic of gamma L plus Zc into IR. So IR will be here into Zc into sine hyperbolic of gamma L. Similarly, what about your Is? Right? Is also, if you put here, right, at x equal to L, your I of x at x equal to L will be equals to Is. So if I put that, right, if I put here in this equation I of x, okay, before that I have to derive I of s. So let me put it here. Let me go to the next page. Let me derive the I of x. I of x will be c1. So zc, 1 by zc will be there always, into c1 e raised to power gamma x. So this Vr plus Zc Ir divided by 2 into e raised to power gamma x. So this, right, again I can break it down. So again I can combine Vr by 2, Vr by 2. So this will become again cos. So Vr cos hyperbolic of gamma x, right, and this will become this is plus, this is minus, right? Okay, this was plus at that point. This is minus, right? Here I have a minus. Oh, sorry, this is not plus, right? This is minus sign. Minus sign. So this will become minus IR into sine hyperbolic of x. Okay, so yeah, that's the thing over here. Now we will just put x equal to L, right? So my x equal to, at x equal to L, my I of x will be Is, which will be equals to, if I put here L, right, this value will be Vr into cos hyperbolic of gamma L divided by Zc plus, so this will be minus I can take inside, this will be plus IR minus sine divided by ZC. Okay. Okay. So yeah. So from this we can actually derive the ABCD parameters, right? We can derive the ABCD parameters, very simple. So what are the ABCD parameters? Like, what is my ABCD parameters? I know my Vs equals to A VR plus BIR, and my Is equals to CVR plus DIR, right? So from this comparing the equations, right, I can see my A is equals to what? A is equals to this, right? Cos gamma L, cos of cos hyperbolic gamma L, and your B is equals to uh, ZC into sin hyperbolic gamma L, ZC sin gamma L, and your C equals to uh, this will be 1 by ZC into cos hyperbolic gamma L, and your D will be equals to minus, is it mine? Am I correct? It should be minus only here. Minus sign. Okay, I might be making some mistake. Okay. So this is at C, VR by 2. Oh, sorry. I'm really sorry. This is minus, right? That's why you don't do shortcuts. This is minus. This will be minus, right? If this is minus, this will become sine hyperbolic of x. Sorry. This will be sine hyperbolic of x. And this will become plus. So this will become plus cos hyperbolic of gamma x. So this will become minus, and this will become plus, and this will become sine. No, this will be plus only. Sorry. This will be plus only. This will not be minus. This will be also plus only. This will not be minus. This will be plus, and this will be plus cos of hyperbolic of x, right? Yeah, now it is correct. So this will be sine of hyperbolic of x cos, sorry, okay, one more thing. This divide by ZC is there, right? So divide by ZC will be with VR, but here, right, ZC and ZC will get cancelled. So this ZC will not be present. Actually, ZC will only be present in the first one. IR into cos hyperbolic of x. Okay, so this will be ZC will not be present over here. This will be cos hyperbolic of gamma L. How do I understood that I made a mistake? Simply, right, the network should be symmetrical, because if I break this network at the middle, right, I see on the right hand side and on the left hand side both are absolutely symmetrical. So that's why the ABCD parameters also should come out to be symmetrical, and your network is reciprocal because it consists of RLC elements. So if I check the condition for reciprocity, it will satisfy. We can verify that. So your actual, right, this is the exact ABCD parameters of any transmission line, medium, short, long, any transmission line with length L. So this will be equals to the most important one. This, it's good if you are able to remember. ESC they will ask, in gate maybe they won't ask the ABCD parameters, but it's good to remember. Okay, so this will be equals to E is cos hyperbolic of a hyperbole of gamma L sine hyperbolic gamma L So this is very important, right? And this is the exact ABCD parameter. I will show you that how the short transmission line, the ABCD parameter whatever we derived comes out to be this, right? I will show you, don't worry, I will show you that. Okay, so in this, right, if you check the condition of symmetricity, I see that A is equals to D, so of course the network will be, the two-port network will be symmetrical, so it is symmetrical. Now the condition for reciprocity, will be AD minus BC equals to 1. So what is AD minus BC? So AD will be cos square hyperbolic of gamma L minus sine square hyperbolic of gamma L, and if you know the property of hyperbolic cos sine, this is actually equals to 1. So that is also satisfied. So network is both reciprocal and symmetrical, which we already knew, but just wanted to verify this. Okay, now these things are there. Anything else we have to discuss? That is what I am trying to think. Anything else we need to discuss regarding this? Okay, so if you want to find out the, now what are the points you need to remember? This thing you need to remember. Okay, for ESC definitely, for gate maybe you don't need to remember, maybe they will not ask, but it's good to remember. Okay, it's good to remember. For ESC it's very important to remember. For gate I will not say 100% it is important, I will say it is somewhat important. Okay, so this part is important, right? And this part analysis is also important. The voltage at x, so I will write the voltage at x, I will write the exact value with respect to cos hyperbolic of x and sine hyperbolic of x. So voltage at x, right, again I will combine this VR by 2 VR by 2, so this will be e raised to power gamma x, e raised to power minus gamma x, so this will be VR by 2 VR by 2 VR by 2, this will be cos hyperbolic of x, right, VR into cos, so you just replace L with x, right, you just replace L with x, you will get this. So you just need to remember this, just remember this, and if you want to write the exact value of voltage at any point x, right, just replace L with x, just replace L with x, right, remember the ABCD parameters and replace L with x, right, that's how simple it is. So cos hyperbolic of gamma x, this will be plus IR into ZC sine hyperbolic of gamma x, and your I of x will be equals to this will be VR by ZC, 1 by ZC into sine hyperbolic of gamma x plus IR into cos hyperbolic of gamma x. So just remember the ABCD parameters and replace L with X, and you will get your value of V and X at each point. Okay, so now we will discuss about another important parameter, that is the most important one. Okay, maybe this will not that important for gate point of view, right? For ESC this is the most important part. For gate point of view, this part is the most important one. The characteristics impedance of the transmission line, that is known as ZC, that is equals to R, like what is it, is Z1 by, it is Z1 by Y1, right? Under root Z1 by Y1 here. So this is equals to R1 plus J omega L1 divided by G1 plus J omega C1. So remember this, everything is in per unit length. Okay, everything is in per unit length. Remember this, right? Your R, L, C all are in per unit length. These are all are in per unit length. Although here it is written capital, right? But actually these are all in per unit length. So I will not show you this, otherwise you will get confused. Everything is in per unit length. Okay, all the quantities, although it does not matter, if I multiply by length it will automatically become capital R by L, but still you will write in per unit only. I mean you write in per unit length only. Okay, so there are many kinds of lines. It is like, what does it mean actually? It is a function of both R, L, G, C. It is a constant property it of a particular line configuration. It only depends on the like distributed per unit quantities. It does not depend on the overall length of the transmission line. My characteristics impedance does not depend on the overall length of the transmission line, so it is not affected by the total length. Typically the Z0, it is also called as Z0 or called as ZC, the value lies between 300 to 600 ohms. Now we will see the different values of Z0 and ZC, right? If it is a lossless line basically means that where can losses happen? In the conductance and in the resistance. These places losses can happen. So if these are gone, these are not there, these are not present, right? Then what does my ZC become? ZC becomes under root L1 by C1. So this actually is called as the critical impedance. This actually is called as a critical impedance. So we place this impedance to avoid reflection. How? That we will study in the next chapter, that is traveling waves. So this will be explained in the next chapter, that is traveling waves. I will explain this in the next chapter, traveling waves. Okay, just for now understand this. We want our load side to match this impedance ZC, that is L by L, that is L by L1 by C1 lossless line, so that there is no reflection. How there is no reflection, I will explain in traveling waves. Okay, this will be explained in traveling waves. Now there is another condition. The condition is this one actually. Okay, this one is gone. Condition for distortionless, right? So what does distortionless mean basically? So there is one thing. What does distortion means? Distortion means that whatever waveform I'm giving at the input, right? I have a system here, and whatever waveform I'm giving at the input, I'm not receiving the same waveform at the output. The waveform at the output is distorted. That means, let's say if here it is sine omega 1 into t, at the output I'm getting sine omega 1 into t, let's say minus some phi 1. And If I'm giving some input sine omega 2 into t, the output again is distorted in both amplitude and phase, right? In both amplitude and phase. So basically, if I'm providing a 1 or let's say 10 amplitude of sine wave, right? This here amplitude has been distorted, that is known as amplitude distortion. And if I'm providing a 5 amplitude of a sine wave with omega 2 frequency, here I'm getting let's say 2 sine omega 2 t and minus phi 2. So phase also again gets distorted, right? So basically what is happening, that the amplitude and phase both are getting distorted. So with change in frequency, when there is transmission line that we have varying frequency, in a transmission line, if we have signals with varying frequency, due to load changes and switching events, the output waveform may get distorted, right? Both amplitude, this is known as the amplitude distortion, and this is known as the phase distortion. The phase value changes. Here the phase is 0, here it is minus phi 1, correct? Why does it change? Why does it change? It changes because this, right, network, this network will provide some phase difference, right? These values will change depending on the frequency, because your reactance L1 and C1, right, those depend on frequency. Those reactance depend on frequency, right? So I will not prove it to you that what is the condition for distortionless transmission. I will not prove it to you. I will just directly say that the time constant of the series network must be equals to the time constant of the parallel network, right? I will not prove it to you. We don't have enough time to prove. Okay. So this you must understand, that the time constant of the series network must be equal to the time constant of the parallel network. That is, what is the time constant here? It is L1 by R1. And what is the time constant of the series parallel network? It is C1 into the resistance. The resistance is 1 by G1. So it will be C1 divided by G1, right? So L1 divided by R1 equals to C1 divided by G1. So that is what is written over here, just inverted, right? So then what will be your characteristic impedance? This question can be asked, that if the transmission line is distortionless, tell me the value of characteristics impedance. Okay, so then your characteristics impedance becomes this, right? So if I want to derive the characteristics impedance ZC, this is what, this is R. Remember, it is not lossless. Lossless meaning your R and L will be 0. R and G, so R and G will be 0, right? There is no loss component. But here R and G will be present. So R plus, R plus J omega L1 divided by G1, this is R1, this is G1 plus J omega C1. Now basically, like, the ultimate aim is to make our characteristics impedance not a function of omega. It should be independent of omega. That is our main aim, so that there is no distortion. Basically, this impedance is not a function of omega. If this is not a function of omega, right, then whatever signal I provide with different frequencies, as it is not a function of omega, the amplitude and phase will not vary. Hence, I will get a constant voltage output, right? Whatever be the amplitude and phase. So if I am providing different frequencies, the output is also the amplitude, the magnification factor of the amplitude and the phase factor are not changing, right? That is the purpose of a distortionless line. Okay, so we will see that if I put here, if I take common R1 and if I take common G1, right, I will take common R1 and G1. So R1 and G1 I will take common. If I take common R1, this will be J omega L1 divided by R1 so this will be, now I know my L1 divided by R1 is equals to C1 divided by G1 L1 divided by R1. That is the condition for distortionless. That is the condition for distortionless, right? So L1 divided by R1 is same as C1 divided by G1, and this is 1. So these are same. So ultimately your characteristics impedance comes out to be R1 divided by G1, which is same. What is R1 divided by G1? R1 divided by G1, R1 divided by G1 is simply L1 divided by C1, right? Which comes out to be independent of your frequency. That was the purpose, right? That was the aim, that whatever waveform I provide of different frequencies, the transfer function should not change. It should be independent, so that the output, the amplitude also does not change with changing frequency, right? The amplification gain and the phase also should not change with changing frequency, so that it can operate as a distortionless line. So this is not a function of omega. That is what we wanted, right? I'm not proving it to you, but I hope these things are clear. These things you should keep in mind, right? Okay, now let's come to the next point, that is propagation constant. What is propagation constant? It is simply, I've taught you, propagation constant is simply under root z1 c1. Again, you will be confused. It is basically equals to alpha plus j beta, because remember it is a complex number, right? So don't get confused here. This is not r, capital R, right? It will be per unit length. So I have to somehow delete this. It's not correct. This is R1 plus J omega L1 G1 plus J omega C1. Okay. Okay. So this alpha is the attenuation constant and beta is the phase constant, right? So we will see in different conditions what happens for a lossless line. In a lossless line, what happens? In a lossless line, your R will become 0, your G1 will become 0. So this will be basically J into J, that is minus 1 omega square C1 L1. So minus 1 under root minus 1 is J omega into L1 into C1. This will be J omega into L1 into C1, not LC, L1 into C1. So why is this called attenuation constant alpha? If alpha is not there, there will not be any attenuation. Why is it called like that? So let's take an example. Let me take an example. So let's take a lossless line where I don't have any R, I don't have any G. So I have my inductance and my capacitance, right? And now this is my sending end voltage and this is my receiving end voltage, correct? I just need to measure the voltage, that's it. Let's say this is my ABCD parameter. I just need to measure the output voltage if I'm giving some input Vs. So what is VR? Just simple voltage division, that is minus J2 divided by J1 plus, sorry, I made a mistake. I have to choose the parameters. Wait, like I cannot choose this. Choose this as 2 and this as 1. Yeah, now it will work. So like I will explain, just in a second I will explain. So minus J1 plus J2 minus J, right? Simple voltage division. So what do I get? This will be J1, this will be minus J1, that will get cancelled. Only minus 1 will be there. So minus of Vs. So there is only a phase difference. There is only a phase difference. So if I am giving input, let's say Vs to be, let's say 10 angle 30 degrees, right? What will be my output? Output also will be, magnitude will be same. The phase difference, it will be minus 180. Minus 180 means minus 150, right? So magnitude of Vs and magnitude of VR are same. So there is no attenuation in the magnitude. There is no attenuation, no attenuation. In the magnitude. Okay. So now that's why it is called attenuation constant, because if alpha is 0, if there is no attenuation, I will not get any attenuation. Now this is not always true, like we have to choose, like the thing is there will be no attenuation for amplitude for a lossless line with a certain condition. What is the condition? Condition is for proper combination of L and C. So for combination of L and C. Okay. So that's actually pretty important, right? Because if I have chosen a different reactances, then the amplitude will not be same. We have to choose the proper combination. So I get my beta, that is equals to omega into under root L1 C1. Now this also can be written as omega divided by 1 by under root L1 by C1. And what is 1 by under root L1 divided by C1? This, I at the starting of the lecture I told you that 1 by under root L1 divided by C1 is actually the speed of the waveform. Where is it? Have I written it? Okay, I have not written it. Okay, I must have written it somewhere. I don't know. Okay. So this I have not discussed anywhere, but I thought I wrote Vs. Also, I just wrote the actual number Vc. So this Vc, right, actually depends on the inductance and the capacitance of the transmission line. So this you must know that your Vc, or speed of propagation of the waveform, Vc is the speed of propagation of voltage or current waveform. So this will be equals to 1 by under root L1 C1. Remember, L1 is in Henry per meter, C1 is in Farad per meter. Remember this thing, right? Don't mess it up. L1 is Henry per meter. Otherwise, this will not match. Your answer will not match. C1 is in Farad per meter. Please keep this in mind. Okay. So yeah. So this, right, can be converted omega by Vc, right? So one more thing I can do. What is Vc actually? Vc is actually the distance upon time, right? It is distance upon time. So Vc is distance upon time, right? And let's assume that this is my time of a complete wave, and the distance that it travels is lambda, right? Vc is distance upon time. So I'm assuming that it's a sinusoidal waveform, and this is the time, right? Capital T, time period of the waveform, and the distance that it travels is lambda. So it will be distance lambda upon capital T. So what is 1 by T? It is the frequency. So lambda is the elliptical distance covered. Elliptical distance. Hence this also will be elliptical time. That's why the frequency will be the 1 by T. Okay. So that's why this will be lambda into F. So Vc will be lambda into F. That will replace it over here, right? So omega divided by lambda into F. Omega is what? Omega is 2 pi F. So my beta comes out to be 2 pi by lambda. So the unit is radian per meter. That's why the unit here is in radians per unit length. Okay. So this is also very important formula, where lambda is the wavelength of the voltage or current wave, right? Okay. This beta is equals to this only when it is lossless. If the line is lossless, then only this is the beta, right? So this is the beta when line is lossless. Otherwise beta will not be this. You have to solve. Beta will depend on other factors. Okay. Now if the line is distortionless, now this, right, this is elliptical, beta is elliptical radian per unit length. Now beta actually tells me the phase shift. I will explain how it tells me the phase shift by understanding the attenuation constant. Let us first understand the attenuation constant, then I will discuss about beta. Okay. Attenuation constant. So if I discuss about attenuation constant, that my alpha is 0, right? Sorry, alpha, not alpha is 0. My line is, let's assume that line is distortion. Sorry, yeah, that my L1 and C1 are absent. L1 and C1 are absent. Okay. So my gamma will be what? Gamma is again R1 plus j omega L1 into G1 plus j omega C1. So C1 and L1 are absent. So basically your attenuation constant is R1 into G1. So what will be your transmission line? Only it will contain real parts. It will not contain imaginary parts. So basically whatever, it does not matter, whatever is your Vs, right? Your Vr will not have any phase difference. There will be no phase difference. Here Vr will be some constant k into Vs, and k will be real. So no phase difference between input and output. Because why? Because here alpha is under root R1 G1, but your beta is 0. So that's why beta is called the phase shift provider, because beta provides the phase shift. If you see, there is no phase shift between the input and the output here, because k will be real. It is just a simple voltage division, resistive voltage division. Okay. So R will be present for attenuation and L will be present for phase shift. So R and L, real components, will be present for attenuation. So real components will be responsible for attenuation, and imaginary components will be responsible for phase shift. Okay. Now let's come back. Now you have understood that I am providing some phase shift. What is the phase shift basically? The phase shift that I am providing is, let's say I have two waveforms, right? This is my Vs of t with respect to time, right? Vs of t with respect to time, and this is my Vr of t with respect to time. Now if there is some phase shift, basically what will happen, the waveform will be shifted. The waveform will basically be shifted. And what will be the phase shift? What will be the shift? That shift will be decided by beta. That shift will be decided by beta. That shift will be a function of beta, right? So if I know beta is what? Beta is length per unit phase shift. Beta is phase shift per unit length. Phase shift per unit length, because it is radian per unit length, right? Phase shift per unit length. It is phase shift per unit length. Beta is phase shift per unit length, right? But if I want to calculate if the transmission line has a length L, what is the overall phase shift? So overall phase shift, right, will be simply beta into L. That is the overall phase shift of the line. Also it is called as, it is also called as the electrical length. It is also called as the electrical length. Sometimes this beta is the, if beta they are asking electrical length, right? Electrical length. And they are asking, if they are asking what is the overall phase shift, that is in radians, it is in radians, right? This will be simply equals to 2 pi by L, 2 pi by lambda, that is the phase shift per unit length into L. Sometimes beta is defined like this as well, and sometimes beta is defined 2 pi by lambda directly. Okay, it depends really. So this is also another important parameter, that is the electrical length, that is 2 pi by lambda into L. Okay, so I hope these things are clear by you. We will solve few questions and we will understand. Okay, so if the circuit consists both resistive and reactive elements, there will be both attenuation as well as phase shift, because alpha and beta both will be non-zero. So the last point, if the circuit consists both resistive and reactive element, then there will be both, there will be both attenuation attenuation and phase shift, as alpha will not be equal to 0 and beta will not be equal to 0. Alpha is the attenuation factor, beta is the electrical length. So please go through, try to solve these two questions, and I will come back with the solutions. So let's solve this question. An extra high voltage transmission line. Extra high voltage meaning it's a long transmission line. Whenever there is extra high voltage, that means it's a long transmission line with a length L equals to 300 kilometer, can be approximated by a lossless line. That means your R1 is 0, your G1 is 0, and your propagation constant is J omega under root LC. That is, it is equals to beta, J beta, and they have given you the propagation constant beta to be equals to 0.00127 radian per kilometer. Okay, then the percentage ratio of the line length to wavelength will be given by percentage ratio of the line length to wavelength. So line length is L to wavelength lambda, percentage ratio 100%. That is what is required for me. So I know, I've explained that 2 pi by lambda is actually beta if it is given in per unit length. It is given in per unit length, so 2 pi by lambda will actually be equals to beta. So from here I will get my lambda. Lambda will be 2 pi by beta. But I have to find out L by lambda. So L by lambda will be L into beta divided by 2 pi. So this will be equals to L by lambda will be L into beta divided by 2 pi. So L is how much? L is 300 kilometers. Beta is 0.00. Remember, it is in kilometer, so and this is in per kilometer. So kilometer will get cancelled. Divide by 2 pi into 100 percentage. So this, if I calculate this value, 300 into 0.00127 divided by 2 divided by pi into 100 comes out to be 6.06 percentage. 6.06 percentage, and that is present in option D. So option D will be the correct answer for this question. Okay, so let's now move to do the next one. So if the electrical length of transmission line is 5 degree, so now they have given electrical length in degrees. It is in degrees, right? So I will convert, what is it? I will convert this first of all into radians. So it will be 5 into 2 pi upon, pi upon 180. This will be the radian conversion. Now this is equals to actually what is your electrical, what is its corresponding physical length? They are asking me what is its corresponding physical length. So this is equals to beta into L, right? This should be equals to, electrical length should be equals to beta into L, correct? Now if nothing is mentioned, right? So what is beta? Beta is 2 pi by lambda. Beta is 2 pi by lambda. Okay, and they are asking me the physical length. They are asking me the physical length. Okay, but I don't know what is my lambda. What is lambda? Lambda. What is my lambda? That is what I want to find out. Lambda is equals to like we know what is my Vc, speed of the traveling wave. Vc is equals to lambda by time period, that is lambda into f, right? Lambda into f. So actually few things should be mentioned here, that the speed of the traveling wave, wave is lambda is 3, like by default if nothing is mentioned you will assume it to be speed of light, but I will mention it, it should be mentioned 3 into 10 raised to power 8, and the frequency of the traveling wave, right, is 50 hertz. These two things actually should be mentioned, right? So I will copy this thing and paste it over here. So from here I will be able to get my value of lambda. So lambda will be equals to Vc 3 into 10 raised to power 8 divided by 50. Okay, so from here so beta is this, right? So this will be, so what will be my length of the line? Length of the line, this will be 5 into pi by 180 equals to beta. Beta, that is 2 pi by lambda. Lambda is 3 into 10 raised to power 8 divided by 50 into L. So pi gets cancelled. This 3 raised to power, so 5 into 3 into 10 raised to power 8 divided by 100 equals to my length. Remember, this is in meters, so this will be 4, and I will divide by another 1000, so this will be 150 kilometers. That will be the length of the line. Okay, 150 kilometers. I hope I'm not making any mistakes over here. Or let me give yeah, that is also fine. 2 pi, this 2 will 2 into 50, 100 10 raised to power 8 into 3. Okay, 180 is, oh sorry 180 is also there, right? How can I forget the 180? 180 is also there, right? So 100 is gone, this divided by 180, so 150 divided by 180 still comes out to be pretty low. Actually speed of, it should not be that closer to speed of light. Yeah, let me reduce the speed here. Let me make it 10 raised to power 6, 3 into 10 raised to power 6. Now it is correct, into 10 raised to power 6. So sorry, not 10 raised, sorry, what is the speed of light? Sorry, speed of light is actually 3 into 10 raised to power 10 is, right? It is 3 into 10 raised to power 8 kilometer per second, and it is 3 into 10 raised to power 10 kilometer per second. Here also I have forgotten, I have to check. Okay, so no, it is 3 into 10 raised to power 8 only. Okay, I was not wrong, it's correct only. Okay, 100. Oh sorry, here I am messing up, right? This is actually 6. What am I doing? This is fine only. This is 3 raised to power 10 raised to power 8 only. This is fine. And yeah, I was messing up here actually, that was the problem. So here, right, this will be 150 into 10 cube, sorry 15 into 10 raised to power, yeah, 15 into 10 cube divided by 180. So this will be 1500 divided by 18, that comes out to be 83.33 kilometer. Okay, according to given data. Now let's, like, just last one more topic is left regarding the approximation. Okay, if I want to approximate my ABCD parameters, this, right, is important, somewhat important for ESC, for gate. Like, just knowing the exact value is enough, right? How can I approximate it? So I know cos hyperbolic of L, right, can be written, gamma L can be written as 1 plus gamma L by 2 plus gamma L by 2, this will be gamma L by 2 factorial gamma L by 4 factorial, this whole squared, right? This will be like the power, sorry, this will be gamma L by 2 whole squared, then this will be gamma L by 4 whole squared. Like, you can remember this expansion. It is 1 plus x squared divided by 2 factorial plus x raised to power cube divided by 3 factorial, and so on, right? It will go on. So, and I know what is my cos hyperbolic of x in terms of e raised to power x. So from there you can always write down the series equation. So what we assume that your gamma L it's much less than 1. Okay, if it is much less than 1, then this terms, right, can be equivalent to 0. So roughly your cos hyperbolic of gamma L will be written as cos hyperbolic of gamma L will be 1 plus gamma L divided by 2 whole square. Okay, that is what your cos hyperbolic of L will be, right? I hope it is clear. Now you can break it down, right? What is your gamma? Gamma is under root of z1 into y1, right? So it will be 1 plus z1 L into y1 L. Basically I am squaring gamma, if I square it is z1 into y1 I am separating out and y1 I am separating out, then I am multiplying length with each of them. So what is z1 into L? It is capital Z, the overall series impedance. And what is y1 into L? It is the capital Y, overall shunt admittance, by 2. So this comes out to be 1 plus yz by 2. I hope this is familiar to you. This I think we have derived in the medium and the short transmission line, not in the short, medium transmission line. So your A, as the network is symmetrical, A will be equals to D will be equals to 1 plus zy divided by 2. What about B? What is B? B is ZC sine hyperbolic of gamma L. Sine hyperbolic of gamma L. Okay. Now now what I can do is it is ZC. Again I can break down my sine hyperbolic of gamma L. That will be gamma L plus gamma L. Like I hope you can see the breakdown how I can write in terms of polynomial sine hyperbolic of x. So basically sine hyperbolic of x, right, can be written as x plus x cube by, sorry, it will not be plus, it will be minus x cube by 3 factorial. Like the signs will alternate for sine. The signs will alternate for sine function. This will be plus x raised to power 5 by 5 factorial minus x raised to power 7 by 7 factorial and so on, right? So here this will be minus, this will not be plus, this will be minus. Okay, gamma L cube. Yes. Okay, or they will alternate. I also have forgotten. Will they alternate? No, I don't think they will alternate because there is no imaginary term. There was an imaginary term that no, sorry, I'm sorry, that was for sine x, not for hyperbolic function. For hyperbolic function the signs will not alternate. Okay, so this will be plus only, sorry. And again assumption is my gamma L will be less than, much lower than 1, so I can neglect the higher order terms, right? So whatever will come beyond this I can assume them to be almost equal to 0, right? So this will be, what is ZC? ZC is, if you remember, it is Z1 by Y1, and this is, if I take a gamma L common, right, gamma L if I take common, this will be 1 plus gamma L whole square divided by 3 factorial, which is 6, right? So gamma is what, again what is gamma L? Gamma L is gamma is Z1 under root Z1 Y1. So if I multiply under root Z1 Y1, this will actually become, like, I have under root Z1 by Y1 into under root Z1 Y1. So under root Z1 will become Z1 and L is there, and under root Y and the under root Y in the numerator will get cancelled, and this will become what? Gamma into L whole square. What is gamma into L whole square? It is simply Y into Z. Gamma into L whole square is simply Y into Z. Y into Z divided by 6. Now what is Z1 into L? Z1 into L is simply equals to capital Z. Z1 into L will be simply equals to capital Z. Okay, so yeah, so this is my B, and similarly your C will be what? Similarly C, right? Just Y will be there. You follow the same method. Sine hyperbolic is there. Sine hyperbolic is there. Just it is 1 by ZC. For C it is 1 by ZC, not ZC. So what will happen? Just Y will be there in front. The bracket term will be same. So for C, right, it will be Y into 1 plus YZ or ZY by 6. Okay. So your EBCD parameter of long transmission line approximate comes out to be this. It is 1 plus ZY divided by 2, 1 plus ZY divided by 2. It is Z into 1 plus ZY divided by 6, and this is Y. Okay, 1 plus YZ divided by 2. So that is your ABCD parameter. Okay, approximate ABCD parameter. I hope it is clear. Important for ESC, not important for gate. Right, you remember the exact one. Right, you can always approximate, no problem with that. Okay, questions can get asked from this. Maybe I'm guessing maybe. Now let's draw the equivalent pi model. Right, this is the exact one. Right, this is not any equivalent. This is not nominal. This is the exact. This is valid for any transmission line. Right, exact. So it is valid for short transmission line, long transmission line, and medium transmission line. Any transmission line you choose, it is valid for everywhere. Right, this pi model, remember, this was not actually in the medium transmission line. There was a term nominal, so it was not exact there. Right, now what I am trying to replicate here, what I am trying to replicate is I am trying to replicate this model, exact model, as a pi model. So if I have a ABCD network, two port network here, right, I have a ABCD two port network, right, exact one. Previously that was a nominal model. This was not, that was not exact. But now I know the exact ABCD parameters. What I will do, I will replicate this. I will think that okay, this is a black box. Inside this, let's assume that it's a pi network. What is the exact equivalent pi model that will have the exact same ABCD parameters as this one? So that's why it is called equivalent, because here the ABCD parameters of pi will be exactly matching with the ABCD parameters of the exact model. But in nominal, go and check in the nominal case. If you check in the nominal, your nominal ABCD parameter, right, nominal ABCD parameter of pi network will not match with the exact ABCD parameter. It will not match. Okay, so that's why it is called a nominal model, and this will be called as a equivalent model, because here ABCD parameter will match. What am I doing? I'm just assuming that I have this ABCD parameter of a network. What if I assume that it's a pi network and I match the ABCD parameter? That's the task. That is the task basically. So the ABCD parameter of a pi model is this. ABCD parameter of a pi model is this, right? So how will I find out my z dash and y dash, all these values? So this is y dash by 2, this is z dash. So z dash is very simple. Z dash will directly, I can directly say will be equals to zc sine gamma l. Z dash will be zc sine gamma l. I can directly say sine h of gamma l. Right? That is my z dash. Now what is my like this, right? This I have derived the ABCD parameters of a pi model I have derived in the previous lecture. So I am not explaining it over again. Okay. Now I have to write 1 plus y dash z dash by 2 equals to cos of hyperbolic of gamma into L. Okay. Cos hyperbolic of gamma into L. So my y dash, like I need to find out my y, right? Y dash into z dash. This is 2, right? This is 2 equals to cos hyperbolic gamma L minus 1. Okay. From here I can say what is my y dash by 2, because that is what I am interested in, y dash by 2. So this actually is equals to simply sine square 2 sine square hyperbolic of gamma L by 2. Okay. I'm not proving it right now because that is not the purpose of this class, but you can see, you can solve it by yourself, like property, because you can replace your cos hyperbolic of x with exponential and then you can solve, or you can see the properties of hyperbolic of x, right? I'm not deriving it. Now what is z dash? Z dash is zc sine hyperbolic of gamma L. Now I can break down my sine hyperbolic of gamma L as 2 sine hyperbolic of gamma L by 2, like it is simply sine theta is 2 sine theta by 2 into cos theta by 2. So this will be cos h of gamma L by 2. Okay. So this will become 2 sine square h gamma L by 2 divided by 2, like zc will be there, right? Zc is anyways outside, zc into 2 sine h gamma L by 2 into cos h gamma L by 2, right? So from here simply 2 sine h gamma L by 2 will get cancelled, and this will be sine h gamma L by 2 divided by cos h gamma L by 2. So this becomes tan h gamma L by 2 divided by zc. Okay. So your y dash by 2 is tan h gamma L by 2 divided by zc. So your equivalent, this is equivalent, this is not nominal, this is exact, right? I have not meant any approximation here, right? We made an approximation, this one, but in this I did not make any approximation. So if I assume my network, instead of it being distributed, if I assume it to be a pi network, the equivalent pi model will be this, right? This is equivalent, not nominal. The ABCD parameters of this pi model and the ABCD parameters of the actual transmission line will exactly match. So here the equivalent model will be, I will have a ZC over here, that is ZC sine h of gamma L, and here I will have a y by 2, y dash by 2, y dash by 2 is given as to me as 1 by ZC into tan. Now this, right, for ESC guys you might remember, other than that you don't need to remember it. Other than that you don't need to remember much. Tan h gamma L by 2. I'm not expecting they will frame a question, but they can obviously if they want to, because this is in the syllabus, but I'm not expecting they will want you to memorize this thing. And this will be 1 by ZC tan h into gamma L by 2. Okay. The important factor is this, you might want to remember if you want to. For ESC aspirants, of course you have to remember everything, but for GATE aspirants I can say this, right, is very important. This maybe you can remember, other than that you don't need to remember much, right? So anyways, like this is unitless, so of course ZC needs to be present. So Z dash will be equals to ZC sine hyperbolic gamma L, and here as this has a unit of ohm inverse, so 1 by ZC must be present, and with this I have tan hyperbolic gamma L by 2. Okay, so this is bit important, maybe gate aspirants can remember this. Okay, if you want to. So with that, basically we are done with today's lecture, right? We don't have to like all the derivations are done. In the next lecture I will quickly summarize whatever we have learned till now, right? And then we will obviously solve questions. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I am Anish, and today we will start with the lecture 24 of this chapter, performance of transmission lines. So today we at the initial phase, I will summarize whatever we have learned in this whole chapter quickly. What are the important things, and then we will solve questions. So first thing is, we learned about the classification of transmission lines. There are mainly three classifications: short transmission line, medium transmission line, long transmission line. So mainly we classify in terms of length, because in power system, remember, in power system frequency is fixed, right? Of course, it will work in 50 hertz or 60 hertz, right? So that's why mainly we classify in length. But actually, actual classification of transmission lines is based on the product F into L. Why? We have discussed already. Why is it important, right? Also, you can classify in terms of voltage. Automatically this gets classified. Why? Because if I is higher, right? Sorry, if your length is higher, then your like resistance per unit length of a conductor is fixed, right? Your length is higher, so your R into L will become higher because length is high. So your resistance increases, although the current is constant. Your I square R loss increases. If it increases, that means I have to reduce I, but I have to transmit same amount of power, so I have to increase my voltage so that my current is reduced, because power transmitted must be same, right? So that's why as I move along, as the length increases, so does the voltage, because I want to reduce my current, because I want to reduce my line losses. Okay, trust me, no one will explain you all this, right? No one will explain you intuitively like this. They will just say, okay, I want to, because the length is increasing, voltage is also increasing, that's it. Okay, so let's come to short transmission line. In short transmission line, we neglect the conductance due to low voltage, and also we neglect the capacitance due to low length, because if length is lower, this reactance will be very high. So in shunt, high reactance means we can totally open circuit it, right? So only the R and X will be present, and the ABCD parameters are very simple: 1 Z 0 1. This we have derived, right? Not that difficult. Even if you tend to forget it, it will take you hardly 10 seconds to derive it. Okay, your voltage regulation is a general formula. It is VR no load. VR no load for a short transmission line, or for any line, right? For any line, VR no load will always be Vs by A, right? You put in the ABCD parameters, right? ABCD parameters. What are your ABCD parameters? Vs AVR plus B IR IS C plus DIR. Okay, at no load this is 0. So basically your VR no load is simply Vs by A. Simply it is Vs by A because Vs will not change, right? Supply and voltage will not change. So it is Vs by A. That's why it is Vs by A here. Okay, I hope that is clear. So this is the general formula. This will always be valid no matter what. But in case of a short transmission line, A is 1. So your voltage regulation formula comes out to be this. And intuitively also you can understand here. At no load this current is 0. So there is no drop here. So whatever is the potential here, same potential will come across the receiving end side. Okay. Now these are the formulas. So you will use, like, this is the approximate formula. This is the approximate formula. We will use this formula when Vs angle delta, this delta is not given. Okay, when this delta is not given to us, we will use this formula. I hope that is clear to you. Now, what I can say, is this is the exact formula. This is the exact one. Okay, and this is the voltage regulation approximate formula. This is the approximate one. And we also have seen an example where this is almost similar, right? Almost similar. Okay, now then we discuss about the power flow. This is the general formula for power flow with ABCD parameters. And for a short transmission line, this you can remember if you want to. It's good if you can remember, but it's okay if you, even if you feel like I'm not able to remember it, it's fine. Not that important. Just what you have to keep in mind, these all parameters are single phase if your magnitude of V is phase voltage. If it becomes line voltage, it will be root 3 into Vp. So that's why extra term 3 will come, and that 3 basically means it is a 3 phase power. If it is line voltage, this will become 3 phase power. If it is phase voltage, it will be single phase power. Okay, and this power and reactive power comprises a locus in the complex power graph with radius VSBR by B magnitude of B, and center will be, oh, center I have not written. Center will be some C1, I forgot to written, but that is not important. Just the radius is important. Okay, and the maximum power will occur when my delta will be equals to beta, because only this is varying, right? This part is varying, everything else is same. And at this condition, your load has to be leading. At this condition, load will be leading. Okay, so these are the things that you need to keep in mind. It's okay if you are not able to remember the exact formula, but what are the parameters you should always keep in mind? What are the conclusions, right? Then we have like for short transmission line, it is very simple. It is VSVR by X sine delta. QR will be VSVR by X cos delta, because assumption is we have assumed R to be also almost 0, negligible. Only X is there. Only X is there. Okay, so that was the short transmission line. And what is the efficiency? Efficiency general formula is VRIR, output power, receiving power, that is VRIR cos phi r, and input power, sending end power is VSIS cos phi s. Okay, so this is the general formula, and this is the short transmission line formula where we know the current IS and IR both are same. So whatever is the loss through the transmission line will be 3 IS square R, or I can write this 3 IR square R, right? IR square R. So this will be the transmission efficiency. Okay, and roughly your reactive power also roughly can be written as difference of voltage. Reactive power is proportional to difference of voltage, right? And active power is a function of delta, right? So if I increase the delta V, so if I want to reduce the delta V, if I don't want the receiving end and the sending end to be operating at like different voltages, I have to supply the additional reactive power that the load is demanding by myself with the help of the capacitor. Okay, now we have, then we derive for the medium transmission line. In a medium transmission line, there are mainly 3 models: N condenser model, then there is pi model and T model. So these are all nominal. These are not exact. Like we are not exactly modeling it. These are all nominal. Nominal T model. Nominal pi model. Okay, so nominal T model, nominal pi model, these are nominal, these are not exact equivalent. So we have derived the formula for N condenser model, right? ABCD parameter. I hope yeah, this is the ABCD parameter for N condenser model. It is simply Z1 Z2, right? So that is the format here, and we have to use this Vs by A. We don't have any other choice. And we derive what is the charging current. Charging current is basically the current through the capacitor. So that was basically the receiving end voltage upon the into the admittance, right? So that is omega C. So it is VR, because the no load, the charging current will be the highest. So that's why we have chosen the no load voltage, and this phenomenon is known as the Ferranti effect, where the receiving end voltage and the receiving end voltage will be higher than the sending end voltage. Delta V will be much higher, and your Ferranti effect is both a function of omega L C, all these parameters, right? So this we have derived what is the delta V at no load, right? And then I told you that how can I nullify the Ferranti effect by connecting a inductor in parallel with the capacitor that is of this reactance, right? Because at no load, if it was operating at no load, this current is zero still, right? So, but here, as if like this was the ABCD parameter here, as if now I have connected a purely inductive load. So IR current will actually be now this VR divided by XL, right? Previously your IR was zero, but as if I know the ABCD parameter of this network and I'm connecting a inductor in parallel with it, right? So I hope that is clear. So yeah, so um, that's why we will connect inductor in parallel to nullify, and the inductance value will be B upon 1 minus A. I have derived how it came. So it's okay if you are not able to remember it, but understand how have I derived it, right? So that's why I'm drawing the circuit diagram as well. I'm just not writing the formula. I'm drawing the circuit diagram so that you will be able to derive it. Okay. So ABCD parameter is till this much. This much ABCD parameter was known to us. Okay, and then I derived that because like this is a nominal model. Exactly what happens, the current, right, gets distributed through the capacitor. It's not like all of the current will charging current will flow through this point only. No, current will slowly flow. So due to that there will be line losses. It will not be exactly I square R. The loss due to the charging current will be this I square L cube by 3, where I is the current per unit length, charging current, then L is the R is the resistance per unit length. Okay, and of course this I is the overall current, capital I is the total charging current, and your R is the total resistance, which is basically I R into smaller into L, right? So yeah, I hope it is clear. So this is your like equivalent ABCD parameter for a T network, and this is your equivalent, not equivalent, sorry, no, yeah, ABCD parameter for a nominal pi network. Okay, not exact nominal pi network. Okay, so we prefer pi model because it is easier to analyze. In the long transmission line as well, we derive the ABCD parameter, equivalent ABCD parameter for the pi network, not for the T network, because it is easier for us to analyze. Okay, because you see right here seems like it is a bit difficult, that's why. So now coming to long transmission line, length will be very large, so voltage will not be same at the receiving and the sending end. This effect is known as the transient time effect. Okay, this voltage is known as the transient time effect. So one more thing is that we will feel the transient time effect even for a short transmission line if the frequency is very high. This also I have discussed there. Due to very high voltage, ground conductance cannot be neglected now, and of course the like this thing you should keep in mind. What is the peak dielectric strength of air? That is 30 kilovolt per centimeter. This can be handy, so that's why I have put it in the short notes. Now how we derived, we derived using distributed parameters by taking a very small length. So I derived first this one, the change in voltage dV upon dx is equals to z1 into ix. How I have written a key value at this end. So this is x equal to 0, this is x equal to L. I have taken a small length, that is delta x. Then I had written the key value and KCL at that loop and at that node, and then I came to this conclusion. Your dV upon dx is z1 into ix, your di upon dx is y1 into vx. Okay, then we derived that we saw we have two waves. One is the forward wave, this is the forward wave, and this is the backward wave. correct? Forward wave meaning if I'm moving in this direction, this is decaying, right? So that's correct. Or no. So this is the backward wave. Or no. If I'm moving in this direction, yeah, this is decaying. Yeah, this is the backward wave. Okay. If I'm moving in this direction, yeah, this is the backward wave. Actually, sorry, this is the backward wave. Forward wave. Okay. So if I'm moving in this direction, which waveform is decaying? So x is increasing. If x is increasing, this is decreasing. So I'm moving backwards. So hence this is the backward wave. And if I'm moving in this direction where x is reducing, so this waveform is decaying. So this will be the forward wave. Okay. And my ix will be simply this divided by zc. That's it. And of course there was a negative sign if you remember, because my dv, like if I differentiate this and divide it by z1, that becomes my ix. So that is what I have written over here. Okay. So yeah, after this I derived what is my gamma is the propagation constant, which is z1 y1, which is equals to alpha plus j beta, where alpha is the attenuation constant in Napier per meter. I think somewhere I must have written it. Yeah, I have written it later, right? And zc is the characteristics impedance, that is z1 by y1. Okay. And then I derive the ABCD parameter, that is this is the exact one. This is the exact ABCD parameter. This is actually important. This you can remember if you want to. And of course, from this we concluded that the network is symmetrical. Network has to be reciprocal because it contains RLC elements, nothing else. So for a lossless line, your real components will be 0. That is R1 and G1 will be 0. Then your characteristics impedance becomes L1 by divided by C1, right? And so remember the unit here. It is ohm per meter. The unit is ohm per meter. It is not simply ohm, okay? Because L1 is in Henry per meter, C1 is in Farad per meter, okay? Will it be in ohm per meter? No, I don't. This will not be in ohm per meter. Sorry, this will be ohm only. So because per meter will simply get cancelled, right? Yeah, this will be in ohm only. This will not be in ohm per meter. So this is independent of length. This is independent of the transmission line length. Remember, maybe I have not written it over here, that my L1 is Henry per meter and C1 is Farad per meter. And for distortionless line, this will be R1 divided by G1 or L1 divided by C1, right? Because your R1, what is the condition? So the condition for being lossless is simply R equal to 0, R1 equal to 0 and G1 equal to 0. And the condition for distortionless is your time constant. Time constant of the series network must be equal to the time constant of the parallel network, right? Which was basically L1 by R1 must be equals to it is, because it is R into C, R is the inverse of conductance, so it will be G1 into C1. So from this we get the relation that L1 by C1 will be R1 by G1, and you can prove it here, and this will get cancelled. This will not have any imaginary part, right? This will not have any imaginary part. Okay, so your ZC will be purely real, that is there will not be any phase shift. Here also you can understand that if your real components are 0, right, there will not be any attenuation. Attenuation will be 0 here for lossless line. So here alpha will be 0. So for particular value of L and C, you will see that your waveform is not getting attenuated, that is the voltage amplitude is not getting reduced. And also for a distortionless condition, have I written it? No, I have not written it. I should. For distortionless, what will happen? This will become no, not for distortionless. Actually, if your L1 and G1 are 0, then it becomes, then there is no phase displacement. If C1 and L1 are 0, then there is no phase displacement. This will be 0, then your beta will be 0. Only attenuation will be present. Your, like, it will be completely real. Your propagation constant will be completely real. And then we derive the value of beta. Beta we derived it 2 pi by lambda. How I derived it? What I did was, so this is omega into L1 C1, which is 1 by L under root L1 C1, and 1 by under root L1 C1 is simply velocity of the traveling wave of the voltage or the current, and omega is 2 pi f. Okay, so this is Vc f, right? So Vc by f is actually equal to 1 by lambda. So replace it with lambda, right? This is lambda and 2 pi is there already. This is radian per meter. Now if I want to write the electrical length, overall electrical length beta will be per meter radian into the length. Okay, so this will be the overall electrical length. So there are multiple ways to define the characteristics impedance. So one way, first of all, let us see the wave, forward and the backward wave. So I told you this is the forward wave, right? I hope, yeah, this is the forward wave and this is the backward wave, correct? This is the forward wave and this is the backward wave. Now forward wave, if you see, the constant of the forward wave is Vr plus Zc Ir. The constant of the forward wave is Vr plus Zc Ir. So so basically this point potential, right? This point potential will be what? Vr potential plus the drop across the Zc. So that's why it tells that because the potential here is Vr plus Zc, right? That's why it is telling that it will observe an impedance. It will observe an impedance of Zc. It will observe an impedance of Zc. Okay. What about the backward wave? For the backward wave, right? I am seeing for the backward wave, it is Vr minus Zc by R. Minus Zc by R. So what is happening for the backward wave? I am seeing that there is a negative impedance because I am observing that voltage is getting reduced. The backward wave, the forward wave was saying what? It is Vr plus this drop, but actually for the backward wave, what is happening? The voltage is getting reduced because it is observing a, like in the forward direction it is observing a impedance of Zc, or in the backward direction it is observing a impedance of, sorry, it is in the forward direction it is observing a impedance of minus Zc, so that's why there is a negative sign, or in the backward direction it is simply observing a impedance of Zc. Okay, in the forward direction or in backward direction it is observing a impedance of Zc, that's it. Okay, now this, right, remember this backward wave will come into action only if your line is terminated, or it is like your forward wave is seeing some discontinuity. So if your forward wave, if forward wave sees some discontinuity, then only I will get a reflection backward wave, otherwise I will not get a reflection. This is just the reflection. This we will study in the next chapter regarding the reflection coefficients. Okay, now another definition for the characteristics impedance is impedance seen by the forward traveling wave, or impedance seen by the line, like Zc is the impedance seen by the forward traveling wave. That is true because here I have Zc Ir, right? Or impedance seen by the line of infinite length. If the line has infinite length, right, then there will not be any reflection. Then only what will happen? Then the impedance seen by the overall voltage waveform will be just the forward wave, which is basically Zc, right? So if I choose a line of length of infinite length, then what happens? I don't have any reflections. This is gone, right? I don't have any reflections. So automatically the impedance seen by the forward wave will be impedance seen by the overall wave, that is Zc. So that is also another definition of characteristics impedance. Now let's discuss few questions. So this is the first question. The classification of a transmission line is as electrically short, medium, long is primarily, they're asking you primarily. Of course, we discuss in terms of voltage, we discuss in terms of wavelength, that is frequency, right? But primarily we discuss in terms of physical length. Okay, because the first classification is long, short, medium, that is with respect to physical length. Of course, other things mostly are constant. Your frequency is constant, right? And your voltage also, yeah, we will increase the voltage in long transmission line, but that will also be, it's not like there is, if the line is long and my voltage will be 20 volts, no. If the line is very long, voltage has to be extra high voltage. There are no other options. So option B will be the correct answer for this question. Let's now solve the next one. A 200-meter transmission line has a parameters at 60 hertz. Okay, resistance R will be equals to 0.21 ohm per meter, and your series reactance will be 0.78 ohm per meter per phase. These are all per phase. Shunt susceptance, right? It is susceptance, right? Shunt susceptance is B 5.42 Siemens per meter. All these are per phase quantities. Calculate the value of the attenuation constant and the phase constant per kilometer. What is the attenuation constant? So your gamma, what is your propagation constant basically? Your propagation constant is under root R1 plus j omega L1 into G1 plus j omega C1, right? So R1 is given to me, that is 0.21 ohm per meter. Everything is in per unit length. This will be 0.21 plus j omega L1. Now already this reactance is given, omega into L1, right? Is already given to me. I don't need to solve it. So reactance is given to me, that is 0.78. Then the susceptance is given 5.42 and it does not have any conductance, right? So this will become J 5.42 into 10 raised to power minus 6. Correct. So they're asking me to find the attenuation constant and the phase constant per kilometer. These are all in meters, so I can convert definitely it into per kilometer later on. But how will I convert this into under root? So what I can do is I can simply multiply these things, right? 10 raised to power minus 6 can go outside. This will become 10 raised to power minus 3. This 5.42 into 5.42 into 0.21, so it becomes 1.1382 and j is there obviously, minus 5.42 into 0.78, this becomes 4.2276. Then of course whole under root is there. How will I solve the whole under root? I will simply convert this into polar format. This will be 10 raised to power minus 3 under root this whole square plus 1.1382 whole square. So this comes out to be 19 whole under root of this. So this comes out to be 4.378. Angle will be what? Angle will be 4.2276. Now which quadrant is this? Your x is negative, your y is positive. X is negative, y is positive. I am in the second quadrant. Okay, so that is basically, if this is theta, this will be my theta, right? So this will be 180 minus theta. Okay, so 4.2276 into 1.1382 tan inverse. So theta is 15 degrees and 180 minus theta, so it comes out to be 164.93 degrees. Okay, now this I will divide by 2 because it is basically under root, right? I'm doing power of half, so 10 raised to power minus 3, this is 10 raised to power minus 3, which is basically what, kilometer per kilometer, right? It is in per meter. If I multiply 10 raised to power minus 3, it is in per kilometer, correct? Gets converted into per kilometer, right? So this will be like I will not do this per kilometer yet. Let me keep it 10 raised to power minus 3, otherwise you will get confused. And this will be, angle will be 82.46 and 4.378 whole under root. This becomes so this will be basically into 82.46 cos, so this becomes 10 raised to power minus 3 into 0.274 plus j, so this will be 2.092 into 82.46 sine 2.074. okay, so from here, right, I can totally say what is my alpha, what is my attenuation constant. This is my alpha, this is my beta, right? Very easy. So my alpha is 0.274 into 10 raised to power minus 3 Napier, its unit is Napier per meter, correct. So it is written as here also it is written, I guess, np per meter. Now I want to convert this into kilometer. So what is 1 meter in kilometer? 10 raised to power minus 3, right? So we'll convert this meter into kilometer. This will be 0.274 10 raised to power minus 3 Napier per kilometer, like per 10 raised to power minus 3 kilometer, right? So automatically 10 raised to power minus 3 will get cancelled. So this will be 0.274 Napier per kilometer. This will be the attenuation constant of the line. What about the propagation constant? So the propagation constant basically is your beta it will be same, right? 2.7, like same derivation, 2.704 radian per kilometer, same derivation. 10 raised to power minus 3 is already there, so 0.274 and 2.07. So option A is the correct answer. We don't even need the omega because everything is given in terms of reactance. Okay, so let's now solve the next one. So same question only, common data question. Now what they are asking? They are asking us calculate the value of the wavelength and the velocity propagation of the line. What is the value of the wavelength, right? Lambda is what? Lambda is distance, right? Distance is what? Distance is speed upon time, that is 1 by t. 1 by t is speed into frequency, 1 by t is frequency, so it is simply speed into frequency. That is what my lambda is, correct? So is there any other formula? Also I know my lambda is 2 pi upon beta, correct? I have already found out what is my beta per kilometer because everything is in kilometer, so this also will be in kilometers. So 2 pi upon beta is in radian per kilometer, so automatically radian and this radian will be cancelled, only kilometer will stay. So 2.704, that will be my wavelength in kilometers. This into 2 into pi, so this becomes 3.03 kilometer. Okay, so 3.03 kilometer, option B is there, but I have to check the part B, velocity of propagation. So from this formula I can use, right, this formula I can use simply. So my velocity of propagation will be lambda upon f, correct? So this will be 3.03 upon frequency. Frequency is 60 hertz, it is 60 hertz, correct? So 3.03 divided by 60 comes out to be very low value. Am I doing something wrong? Lambda is speed upon time velocity, yes, correct. 2 pi upon beta, beta is correct. Okay. I must have been doing some mistake. Oh, sorry, what am I doing? Sorry, what is distance, right? What is distance? Distance is speed into time, right? What am I doing? Speed into time. So that's why whenever you tend to forget the formulas, understand with basic units, right? So distance is speed into time. Speed is vc, time is capital T, right? Capital T. So frequency will be what? 1 by f. Capital T will be 1 by f basically. So this f should be in the bottom. F should be in the bottom. So your vc will be simply lambda into f, right? So this into 60. So it comes out approximately 181.77, that is kilometer per second, that is almost equals to 182.12. So option C is absolutely correct answer. So go with basics. I also tend to forget the formulas, but I derive it with units, right? I derive it with the units. Go with basics. Okay, so this is clear with just 2 lines. You will see everywhere else they will solve using just, they will directly write the formula and they will not explain you anything, right? They will just tell you to mug up the formula. Okay, so let's now move on to the next one. So in this question, read the question. I will just drink a bit of water. So a 3-phase 60 hertz transmission line has length of 250 kilometers. So it is a long transmission line. The voltage at the sending end is 220 kilovolt. The line parameters are this, right? Per kilometer, everything is in per kilometer. The sending end current when there is no load connected. What is the sending end current when there is no load connected? So we can model this with end condenser model, okay? Because directly also we can do. What is the sending end current at no load? Like there are two ways, either you approximate it or you directly solve. So I will recommend you to solve directly. It's a long transmission line. So what are the ABCD parameters for the long transmission line, if you remember it, right? So here I had a cos hyperbolic gamma L, that I remember, that you need to remember no matter what. This is the basic thing that you need to remember, right? There was a cos hyperbolic gamma L, and I know it is a symmetrical network, so this also will be cos hyperbolic of gamma L, and this right here B has a unit of ohms, so this will be ZC into sine hyperbolic of gamma L, and here has a unit of ohm inverse, so this will be 1 by ZC sine hyperbolic of gamma L. That's how you remember. Okay, now let me just write down Vs equals to AVR plus BIR, Is equals to CVR plus DIR. Okay. So at no load, what will happen? At no load, your IR will be 0, and they are asking me to find out the sending end uh, current. So I can take the ratio of Vs by Is will be equals to A by C, right? So my sending end current Is, they want me to find the sending end current. Is will be equals to Is will be equals to, that's why I have told you, no need to remember the approximate model, just remember the exact one. You will never go wrong. Remember the exact one. You will never go wrong, right? So this will be Is in will be equals to C by A into Vs. So I basically need to find out the C and find out the A. So C is this, A is this, correct? Okay, but you will not be able to write in your calculator cos hyperbolic. I think there will be option of hyperbolic. I guess I am hoping that there will be option of cos hyperbolic of L, right? I guess that option is there. Okay, so but this will not be, this will be imaginary, so this will be something imaginary, this will not be real. Okay, that option is gone. So maybe you have to do a bit of approximations. We will see what kind of approximations we can do. Okay, so this, right, this will be what is gamma? Basically your G is 0, R, X, all these things are there, so gamma is 0.2 plus J 0.8 into J. Now this is in microsiemens, right? Omega C1 microsiemens 5.3 into 10 raised to the minus 6. Okay, so 10 raised to the minus 3 will be outside. This gamma actually will not be real, it will be something imaginary. So yeah, but what I'm observing, your gamma is very low, right? So we have to do a bit of approximation, otherwise you will not be able to put it in the calculator, this imaginary number, right? So gamma is actually very low, right? Then you remember this and then you approximate, right? So what is your cos hyperbolic h of cos hyperbolic h, cos hyperbolic gamma L? So cos hyperbolic gamma L, as gamma is very low, is equals to 1 plus gamma L by 2 factorial, and all the other terms will be gone, right? 0. So it is basically 1 plus gamma L by 2, 1 plus gamma L by 2. Now what is gamma L? Gamma is this value, right? This one. So gamma is this. Okay. So what is gamma L by 2? This I have to anyways, this I will have to find it out. This I cannot approximate. This I have to find it out. Gamma L by 2. I was already calculating gamma L here. So okay, what is my length? They have not. They have given the length. Okay, okay. So what will be like? What will be this value? This will be under root 5.3 into 0.2, and J is there. So J 1.06 plus, so minus 0.8 into 5.3. Okay, 5.3 also can go outside, right? Oh, that's not a problem. 5.3 also can go outside. What is 5.3 under root 2.3. So 2.3 will be here, no problem, just the j will be multiplied here. This will become j 0.2 and this will be minus j 0.8, sorry, minus 0.8, that's it. Yes. Now this number is anyway very smaller than 1, so that's why we can approximate cos hyperbolic to be 1 plus gamma L by 2. So this will become uh, 0.2 whole square plus 0.8 whole square whole under root. So this comes out, then whole under root again. This comes out to be 10 raised to power minus 3 into 2.3 into 0.9. Okay, 0.9, and your angle. So again this is in the second quadrant. So 0.8 divided by, sorry, 0.2 divided by 0.8 tan inverse, then plus 180, and then divide by 2. So this angle is 83 degrees. Angle is 83 degrees. Okay. So that is what my gamma is. What is gamma into L? Gamma into L, right? Gamma into L will be this into 250, because this is per kilometer, right? Because everything is in per kilometer. If you see, everything is in per kilometer, I will just multiply by 250 and not in meter, right? Not in meter, I will just multiply in kilometer. So this will be 2.3 into 0.9 into 10 raised to power minus 3 into 250. So this becomes 0.5175 angle 83 degrees. Okay, so now this will be basically, this will be equals to what? Your cos hyperbolic of h will be 1 plus gamma L by 2. So this, right, divide by 2 is 0.26 basically. Angle is 83 point, I'll just write the exact one, 875 83 degrees. Okay, so what will be this value? So this into 83 cos, so this is 0.01 plus 1, so this is 1.031, 5 plus j, this will be 0.25875 into 83 sine, so this is 0.257, right? So basically your A, right, A will be this whole square plus 1.0315 whole square whole under root, okay, something gone wrong, 0.257 whole square plus 1.0315 whole square whole under root. So this will be angle, so 0.257 divided by 1.0315 tan inverse, so this is 14 degrees. So that is what your A is equals to. Okay, I hope I am not making any minor mistakes over here, right? I'm just thinking whether I'm making any minor mistakes. Okay, minus 160, this is divided by 2, yes, this gamma L divided by 2, 1 plus, okay, okay, no, this seems fine. Okay, This is fine. Still it is quite higher compared to whatever we actually computed. That's fine. Let's now calculate the C value. What is C? C is this one, right? C is this. So I have to calculate the approximate value of sine hyperbolic of gamma L, which will be like here there will not be any plus minus, it will be just gamma L plus gamma L by 3 factorial. I will just consider the term till the disorder, then I will not consider. So okay, this will be equals to gamma L is this, right? Gamma L whole cube. Gamma L whole cube will be okay. This will be actually lengthy. Because this will be even smaller, right? Because this is already gamma L is 0.51. So if I do the cube, right, the magnitude will be even smaller. But not that small, but still it will be much smaller, 0.1 something. Still it will be, and I'm dividing this by 6, right? So it will become even smaller. So I can neglect this. Again, I can neglect this. The answer will come out to be approximate, but we don't have any other option. Otherwise, the calculation will be very high. So gamma L is simply 0.517583, and it is not your C. C is what? C is sine H of gamma L divided by ZC. So what is your ZC? ZC we have to calculate. ZC will be under root R1 plus j omega L1 divided by G1 is 0. So it is simply j omega C1, right? So already your susceptance is given 5.3 microsievens, right? So this is 5.3 microsiemens per kilometer that is given to you, right? But here your impedance is comes out to be R.2 plus J.8, right? So this, right, now what will be this value? So this will be again minus of J 0.2 plus 0.8. Just the a negative sign is there. A negative sign is there, right? Just a additional negative sign is there. So if I take minus 1 common, right? So a j will be multiplied here. I will take minus 1 root 3. Minus 1 root 3 is simply j. Sorry, minus 1 root is simply j. And this will be, I have taken common minus 1. So this will be j 0.2 plus minus 0.8, which I already have solved it over here. That is equals to 0.983 degrees. And this j is simply 1 angle 90. And this will be 0.983 degrees divided by 2.3. That is what my ZC is equals to. Okay. So I have to divide sine H by ZC, right? If I divide this, automatically the 83 angle gets cancelled, right? Only this 1 angle 0 will be there, and this 2.3 into 10 raised to power minus 3 will go at the top. And of course, don't forget you have to multiply by L as well, right? I forgot to, no, this is already multiplied by L, sorry. So So this 2.3 into 10 raised to power minus 3 into 1 angle 90 divided by, automatically this 83 angle and this 83 angle got cancelled, but still at the top I will have 0.5 0.5175, right? I'm just simply dividing, right? So my C is this by Z, this right here, my C is this by Z, this, okay? So this will be 0.5175 divided by this term ZC. So okay, ZC have to, okay, this should not go at the top, right? Sorry, this will be at the bottom. This 1 angle 90 will be at the bottom, this 0.9 will be at the bottom. Basically the angle got cancelled, this 83 and this 83 automatically got cancelled. So this value will be what? This will be 2.3 into 0.5175 divided by 0.9. So this comes out to be 1.3225 angle of minus 90 into 10 raised to power minus 3. That is what my C is equals to. Okay. So now I will simply solve. I will simply solve. So I know my A, I know my C. I can easily solve. What will be my like this current IS? But I am thinking generally the E is lower than 1. How is it coming? Okay, because there is a plus sign here. That's how it is coming, plus. But in my derivation there should be a plus sign only, right? Yes, there should be a plus sign only. Yes. Gamma, there should not be any negative sign. That is, both are getting added. If I go and see in the derivation, right? I forgot what was cos hyperbolic. Oh, sorry, that is what I'm missing, right? Here this should be square. Sorry, because that term is gone. It will only consist of even term. Okay, that's why I was thinking, like, how is it possible? It has to be something wrong, something I've done wrong, right? Okay. Sorry. That is what I was thinking, because A value has to be less than 1. So if this is square, right, this actually becomes yeah, this actually is not that difficult. So this is square, sorry, this will be square. If this is square, then I have to square it again, right? So the squared format will be point, that is what I was thinking. I'm making some sort of mistake. 0.51 whole square divided by 2, so this becomes 0.1 0.134, and this angle will be 83 into 2. Okay, so now things will be a bit different. This will be 0.134, sorry, 83 into 2, right? That is 166. So 166 cos into 0.134 plus 1, so that is 0.87. Okay, 166 sine into 0.134, this will be J 0. Anyways, the imaginary part does not matter actually. It will almost be 0, 1 to 4. So from here, right, A actually something, A will be generally less than 1. It cannot be higher than 1. Generally it is less than 1. So 0.87 whole square plus 0.03. Don't worry, I will explain at the end again. What am I doing? Okay, explain at the end. 0.87 only, and the angle will be very near to 0. So 0.0324 divided by 0.87 tan inverse, it is 2.13 degrees. Okay, so now I know my A, I know my C, right? So I will be easily able to find out my IS. IS will be Vs is given to me. They are just asking me the magnitude of the sending end current. Magnitude of the sending end current will be simply magnitude of C upon magnitude of A into magnitude of Vs. So magnitude of C is 1.3225 into 10 raised to power minus 3. Magnitude of A is 0.87, right? And magnitude of Vs is 220 kilovolt. 220 kilovolt. Okay. Remember, this is line voltage, right? And we assume transmission line to be connected in phase. So whatever the this parameters, I forgot to mention actually, this Vs, Is parameters, right? These are all phase quantities. These are not line quantities. Okay. So here, right, in the summary, you should also write this will be all phase quantities. ABCD, what is the ABCD parameters? Yeah, these are all phase quantities. Okay, phase quantities. This is phase, not line, okay, phase quantities. Please remember this. And one more thing, this approximation will come in handy for you. So this also you remember, this cos hyperbolic approximation. You can put it in the short notes. I will put it in the short notes. Where did it go? Okay, we don't have space here. I will put it somewhere around here. Yeah, the approximation for this, right, simple approximation for this will be 1 plus gamma L whole square divided by 2 factorial, and the approximation for this one will be simply gamma L. If your gamma is much less than 1, then only you can do all these approximations. Okay, keep this in mind. Okay, these things you keep in mind. Okay, so this, right, here I will have to write 220 kilo, that is 10 cube, divided by root 3. Okay, finally we are at the final position. So this will be 1.3225 into 220 divided by 0.87 divided by root 3, that is 193 amperes. This will be your magnitude of the sending end current. This will be the answer. This will be the answer simply. Okay, so yeah, I hope it is clear. 132, everything is correct. I hope I'm clear about this. Although, like, I've made a bit of approximation here. We could have chosen that one, but that's fine. 193 amperes is fine. They will give you enough range. Because like, where you can go wrong, actually the exact approximation will be better if you choose the third order term as well here, right? If you choose a third order term, that is plus gamma L by 3 factorial, but that will be anyways very low. It's fine, this one is fine. Okay, so what I did basically is, I know the exact transmission line parameters. I will not be able to find out the hyperbolic of gamma L. Why? Because gamma itself is a complex number. I will not be able to put it in the gate calculator. And don't worry, this kind of questions, I don't feel this will get asked. Simple questions will get asked, right? When your gamma is purely real. Okay. Then what you will do, you will approximate it. You will find your gamma first. Then you will, because I need A and C to find out the no load sending end current. Because if I make IR 0 and I take the ratio of these two, so VR will get simply cancelled. VR is common, non-zero will get cancelled. Vs by Is will be A by C. So your Is will be simply C by A into Vs. Okay, this is what your Is is equals to. Okay, then what you can do is, I just need to find out C and A. So I know what is gamma. Then I will multiply by L. That will be gamma L, and there will be two approximations. One will be for A, one will be for C. For A, it will be simply 1 plus gamma L square by 2. I forgot this, there was a square. You will calculate this. And for sine, You will calculate gamma L plus gamma L by 3. I have assumed it to be 0, but they can choose this, they can take this as well. This will be near about this value, whatever is the approximated value, and then you have to find out ZC as well, because remember there is a divide by ZC. So then ultimately you will put it in the equation, magnitude you will put, and you will get the current. Okay. So I hope it is clear. So yeah, this question is lengthy, and this I am expecting to come in ESC. In GATE, my expectation is this kind of question will not get asked, lengthy one. In GATE, these kind of questions can get asked. Okay. So at no load condition, 3-phase 50 Hz lossless power transmission line has a sending end and receiving end voltage of 400. So sending end voltage is 400 kilovolt and receiving end voltage is 420 kilovolt at no load, that is at the condition IR equals to 0. So when IR equals to 0, then the sending end voltage and the receiving end voltage is this, right? Assume the velocity of the traveling wave Vc to be equals to speed of speed of light. Okay, 3 into 10 raised to power 8 meter per second. They are asking me what is the length of the line in kilometer. Okay, a lossless power transmission line. Okay, no load. So no load, right? What is the no load condition? In no load, right? My IR is 0. My IR is 0. So I can write this value Vs equals to A into VR, because your IR is 0, B into IR will be simply 0, right? So from here I can find the value of A, but phase is not given to me. Phase is not given. Magnitude of A I know. Magnitude of A I know. Magnitude of A will be Vs, that is 400 divided by 420. So magnitude of A will be 400 divided by 420. That will be 0.9524. Okay, this is the magnitude of A. Now what is A actually? What is the exact A for a long transmission line? If you remember, it was cos hyperbolic of gamma L, right? So what is gamma L? Gamma L, I don't know. What is gamma L? I don't know. But it has told me that it is a lossless line. If it is a lossless line, that means your R1 will be 0, your G1 will be 0. What will be your gamma? Gamma will be simply J into J into J into what am I thinking? I'm thinking something else. So J into, it will be J into omega L1 into J into omega C1, right? So ultimately it comes out to be Jj will be -1, -1 will be simply J only, omega under root L1 C1. Okay, this is your gamma, correct? And I know what is the speed of wave, that is 1 by under root L1 C1, correct? So from this I can directly write that under root L1 C1 will be simply equals to 1 divided by 3 into 10 raised to power 8. Okay, omega is given to me. Omega should be given. Omega is not given. Omega is given. F is given, right? 50 Hz. Correct. So omega is 2 pi F, that is 100 pi. Now, what do I know regarding cos hyperbolic of Jx? If x is a real number and like inside the hyperbolic function, a imaginary term is there, right? Purely imaginary. This is purely imaginary. So I know what is cos hyperbolic, even if you tend to forget, right? Never forget the basics. cos hyperbolic of x is equals to e raised to power x minus e raised to power minus x, sorry, plus e raised to power minus x divided by 2. Just replace x with jx. This will be e raised to power jx plus e raised to power minus jx divided by 2. What is this? It is simply cos of x. It is simply cos of x. So this will be cos x, right? So basically cos hyperbolic of jx is simply cos x. It became even simpler, right? Became even simpler. So this will be just cos of x. X in our case is omega into under root L1 by C1. So everything is actually given to me. What do I need to find out? Okay, that is what I'm thinking. What do I need to find out? Everything is already given to me, right? Okay. Okay, this is just the gamma, right? But this is gamma into L. So what is cos hyperbolic of gamma into L, right? Which is equals to cos hyperbolic of gamma is this, right? J omega L1 C1 into L. Now I have just told you this is completely real, this is imaginary, so it will be simply equals to cos of omega under root L1 C1 into L, which is what? Which is equals to A, right? Which is equals to, if I am talking about just the magnitude, right? This is anyways real only. So this will be simply magnitude of A that is given to me. This value, right? 0.9524. So I know the magnitude of A, that is 0.9524. And then so I can do the cos inverse, right? I can do the cos inverse, and I will keep this omega in radians. I will keep this in whatever. So omega under root L1 C1, what will be this value? This will be 100 pi omega into under root L1 C1 will be 100 pi divided by into 10 raised to power 8. Okay. So I will do the cos inverse here on both sides, right? Because this is anyways real. This is totally real, right? I don't need to take the like magnitude. This is anyways real. So magnitude I don't need to take. This will be anyways real only, right? This is real. So this will be 0.954 524 0.9 cos inverse. Okay, so cos inverse in radians, not in degrees, in radians. This will be 0.3, and this is actually 100 pi into L divided by 3 into 10 raised to power 8. So this is 0.31 actually into 3, right? This becomes 0.93 into 10 raised to power 6 divided by pi. That is the length in meters, but they have asked in kilometers, so I have to divide by 10 cube. This is in meters actually. So your L in kilometer so this will be 10 cube divided by pi, so it comes out to be 295.88 kilometers. Okay, 295.88 kilometers. Now you go and see the P by Q book of any publication. They will use some formula, right? it will be, the solution will be 3-page long. Okay, you go and see any PYQ book. But what we have solved, we have just solved with basics, just with basics, right? So I want you to have that intuition. I did not use much form, like of course I used the formulas, but I derived from the basics, right? These things I knew already. Okay, I never once I have written beta, but you will see everywhere else they will solve with beta. They will try to solve with beta, but without beta I am solving. Okay, so if you have enjoyed this concept, make sure to hit the like button and say in the comments below that I have understood this concept of long transmission line. So question 30, I am present. Okay, so trust me, no one will solve like this. No one will solve. Everyone will just have a 2-3 page simple formula derivation. Okay, so let's move on to the next question. So it is a ESC question. So equivalent T model, equivalent T circuit of a long line is preferred to equivalent pi circuit. No, pi circuit is T circuit is not preferred. Pi circuit is preferred. The nature of reactive power compensation is different for peak load and off peak load conditions. The nature of reactive power compensation is different for peak load and off peak load conditions. Let me read the other statement as well. Ferranti effect is significant only in long and medium lines. This statement is absolutely correct. So 3 is correct. 3 is correct, but 1 is definitely not correct. This is gone. This is gone. This is gone. Right? So only option C is present, which is satisfying. So 2 also has to be correct. So let's see why 2 is correct. So let's see the statement. The nature of reactive power compensation is different for peak load and off peak load condition. During peak load, the reactive power consumed is mostly inductive load. Your fans, your washing machine, mostly motors are there, right? Mostly motors. So during peak load, the reactive power compensation might be different. You have to provide capacitor banks that will deliver lagging reactive power or absorb leading reactive power. During off-peak load, the line capacitance dominates. At no load, line capacitance dominates, that is Ferranti effect. Right? So if you see, right, how to nullify Ferranti effect, we use inductive compensator in parallel, right? If you remember, that will absorb the extra charging current. That will absorb the leading reactive power. Okay, so that's why the reactive power compensation will be different for peak load and off peak load. Okay, I hope it is clear. And Ferranti effect already we know. I hope I don't need to explain the Ferranti effect. Okay, let's now solve the next question. So this is the next question basically. So here we have a 200 kilometer transmission line. So it is a long transmission line, right? So they are asking us to find out the sending end voltage and calculate the line charging current. Okay, so if these kind of questions are asked, right, sending end voltage and line charging current, that basically means they should have mentioned although that you're operating at no load. Line charging current basically it will only be present mostly when you are operating in no load. So what is the sending end voltage, right? So again ABCD parameters are given. So Vs equals to AVR plus BIR and IS equals to CVR plus DIR. Okay, now so my sending end voltage is 230. Remember, this is line to line, nothing is mentioned, it is always line to line, right? And we are operating in no load, so they are asking me to calculate the charging current. So charging current will be the whatever current I am sending from the supply side, so IS. So we are operating in no load, so this is 0 only, and the sending end voltage is given to me. Okay, so again I have to, like, my IR is 0 at no load and IS will be the charging current. So again if I take the ratio of these two, right, it will be IS by Vs will be equals to C divided by A. So basically my charging current IC will be equals to C divided by A into Vs. They have just asked us the magnitude, so I will directly compute the magnitude. Magnitude of IC will be magnitude of C, magnitude of A into magnitude of Vs. So C is 0.0 1 into 10 raised to power minus 3. So 10 raised to power minus 3. A is 0.938. 0.938 into Vs. Vs is 230 kilovolt, but it is line to line. So I have to divide by root 3. Right? So from here I can easily find out what is my IC. So this will be 230 divided by root 3 divided by 0.938, 141.56 amperes. So 141.56 amperes is present in option A. So option A is correct. Let's now read the second one. Calculate the maximum power corresponding and the corresponding reactive power per phase. That remember per phase they are asking, right? So you have to put the phase voltage, not the line voltage, that can be transferred at 220 kilovolts. So if my VR is 220 kilovolts, they are asking me what is the maximum power that can be transferred. When we get maximum power, I just remember one. Okay, you have to, unfortunately, if you don't remember the formula, you will not be able to solve this. Okay, so I will tell you how to remember the formula. So here, right, I have Vs VR, that will always be there, magnitude of Vs, magnitude of VR, right? And in the denominator I remember that B is to used to come and cos will come, right? Because in short transmission line, purely inductive link, VSVR sin delta used to come, and that sin delta was basically 90 minus delta. Cos 90 minus delta, 90 means basically angle of the impedance angle, right? Series impedance angle. The 90 is basically beta, right? So that's why cos beta minus delta will be here. Cos beta minus delta will be here. Okay, minus, then remember there was a square. What was square? Sending end already have taken, square will be receiving end, right? It will be magnitude of VR whole square into, there was E, right? Because here if you remember, beta used to come and minus alpha used to come, so this minus alpha is due to the E here. Okay, divided by, again, magnitude of V will be there. So that's how you remember the real power formula. And if you know the real power formula, the reactive power is very simple. Just instead of cos you put sine, that's it, right? So just remember the real power formula, and just instead of cos you put sine, you are good to go. Okay, so now you put beta equals to delta for maximum power transfer. So the condition is beta equals to delta, right? We have to calculate the maximum power. So PR max will be basically equals to VS VR, I already know, that is 220 is the VS voltage, sorry, that can be transferred at 220 kilovolt. Okay, they have not told me what is the sending end voltage, right? Sending end voltage I will already take from the previous question. So previous question, it is a common data question. So previous question they have already told you the sending end voltage. So that's why they are not telling you here again. So actually they should have told you that the sending end voltage is 230, but it's a common data question. So I hope it is clear, right? So Vs will be 230 volt from the previous question, right? Remember you have to provide per phase because we have to find out the per phase power. So this will be 230 divided by root 3 into 220 divided by root 3 divided by B, magnitude of B, magnitude of B is 131.2, right? 0.2, and anyways beta will be equals to delta, so it does not matter. So minus A is 0.938 divided by B, that is 131.2, into VR whole square, that is 220 divided by root 3 whole square. It is in megawatt. I am not writing kilo whole square is mega, so I am not writing it. It is beta minus alpha, beta is 72.3 degrees, alpha is 12, sorry 1.2. So your PR max, this will be a task, 72.3 minus 1.2, 72.3 minus 1.2 cos, so this comes out to be negative actually, minus 0.4, this into 220, just hold on, 220 divided by root 3 whole square into 0.938 divided by 131.2, so this is negative, so this becomes plus 46.4172, and this will be 230 into 220 divided by 3 divided by 131.2, so this becomes 128.557 plus 46.4172, so this becomes 175 megawatt. So this is the PR max, but this is not correct. Okay, maybe I have made some sort of mistake, right? What kind of mistake I made, that is what I'm trying to figure out. VS is this, root 3 I have divided, everything is correct. Why the answer is coming? Okay, negative sign was there, cos, oh, so why is it this? Okay, this should not come negative, right? Why is it coming negative actually? 72.3 minus 1.2. Okay, sorry, this was in radians. Oh, sorry, this is not actually correct. This is 0 point, my calculator was in radians, that's why things got messed up. Be careful, be very careful, right? If your calculator is in radians, right, you will mess up. Don't mess it up. All calculations will go wrong. Okay, all calculations will go wrong if your calculator is in radians. Don't do it. It is in degree right now. Okay, so now I think this will be 220 divided by root 3 squared into 0.938 divided by 131.2. So this is actually much lower. How it became much lower? This cannot be much lower, right? Just give me 1 second. Minus 1.2 cos of this into 220 divided by root 3 whole square into 0.938 divided by 131.2. Yeah, this becomes 37. This will be negative 37.362. This plus 128.557. Yeah, this becomes 91.2 megawatt. So your PR max per phase, right? This is per phase, is 91.2 megawatts. Now, of course, I will calculate the QR. So in QR, right, beta will be equals to delta. So this term is anyways gone. Only this term is there. Minus 0.938 divided by 131.2 into VR max. VR max is 220 divided by root 3 whole square into sine of beta minus delta, that is 72.3 minus 1.2. Okay, so this will be basically 72.3 minus 1.2 sine into 220 divided by root 3 whole square into 0.938 divided by 131.2. So it comes out to be 124. QR. Okay. MVR. This will be negative. Remember, don't forget a negative sign is there. Negative meaning load is leading. Right. Load has to be leading. Okay. So this will be the reactive power basically. So that was the answer. So 91.2 and 109.1 MVAR. Okay. So I hope this is clear. Now let's move on to the next one, and this is the last question basically. So we have been given a lossless line with extra high voltage, and it is operating at 50 hertz, and series reactance is this in per unit, right? Okay, and shunt susceptance is this much. Determine the approximate wavelength of the line in kilometers. So what do I know? Wavelength, right? Wavelength basically they are talking about the lambda. They want the lambda. So lambda is equals to what? It is a lossless line, right? So what is your propagation constant? Propagation constant is simply j omega L1 into j omega C1. So it basically is j omega square under root L1 C1. So your beta is omega square under root L1 C1. What is your beta is equals to beta, if you remember this correctly, omega square by Vc, correct? Omega square by Vc. What is the lambda? Lambda is distance, it is speed into time. So it is Vc into time, or 1 by time is frequency, Vc by f, right? So I can replace my Vc over here. I can replace my Vc over here, right? Yes, I can replace my Vc over here. So because I know, what do I know? I know these values. So I know my Vc already. So what is my Vc? They have given me the reactance. So omega into L1, right, is given to me, and omega into C1 is given to me, correct? What is Vc? Vc is 1 by under root L1 C1. Vc is 1 by under root L1 C1, but omega into C1 and L1 is given to me, right? So I can take this inside, I can take this, sorry, omega square will not be there, omega will be there, right? Or okay, omega square, omega will be there, sorry. So omega will not be there. These values are given to me, right? This under root omega L1 into omega C1. Omega L1 is given to me, omega C1 is given to me. Okay. So how do I find out my Vc? I can find out because omega I already know. So so omega L1 is given to me, that is 0.00 whatever this value is. So what will be L1? Let me write this as x1. Let me write this x and y, right? So omega L1 is given, omega C1 is given. So what is L1? L1 is simply x by omega, and C1 is simply y by omega. So I can replace it here. This will be under root x by omega, y by omega, which we already knew actually, y by omega. And but x and y values are known to me, so that will be easier for me. So here and my Vc here, right, from this equation, Vc is simply lambda into f. So lambda into f will be equals to omega divided by under root x into y. X, y values are known to me. Lambda will be equals to, automatically this gets cancelled, right? This is 2 pi f. This will be 2 pi f will get cancelled, under root x y. So from here I can easily find out what is, like I'm not like I could have directly written lambda is 2 pi by beta. I could have done that, okay, but I'm trying to derive everything from scratch because it may happen that you might not remember the formula. So what if you don't remember the formula? How will you solve it? That is what I'm teaching. Okay, 2 pi, everything is in per unit, right? Everything is in per unit. So automatically unit will be correct only because you're taking under root this times this. Automatically this is in pu and kilometer square, under root is kilometer. So unit is correct. So this will be under root. Now this will be difficult. Now this is what? This is actually 5.2, 1, 2, 3, 4. 1, 2, 3, 4. Right? 4, 10 raised to power 4 if I multiply, I will reach here. 1. So if I multiply this, this will be 1, 2, 3, 4. So 5.2 into 10 raised to power minus 4 into 1, 2, 3, 4. So 14 into 10 raised to power minus 4. Remember, it is already in kilometer. Don't do anything. It is already in kilometer. So this will be 2 pi divided by 10 raised to power minus 4. That is 10 raised to power 4 in the top. And this, right, 5.2 into 14 whole under root comes out to be 8.5323. Okay. So what will be your wavelength? So this, right, into 2 into pi into 10 raised to power 4 comes out to be 7364 kilometers. 7364 kilometers. I've tried to use like as little formulas as possible. I've tried to derive in the question directly so that you don't have to remember the formula. Of course, you can remember the formula. Lambda is 2 pi by beta. Always you can do that. Lambda is 2 pi by beta, right? Method 2, simple as lambda is 2 pi by beta, and your beta, right, in lossless case is simply omega square under root L1 C1. That's it. And if you take the omega inside, this will be omega L1 into omega C1. So this will be overall XL, and this will be XC. That's it. You're good to go, right? So simply your lambda will be 2 pi by under root XL by XC. I do understand, like it will take you hardly 30 seconds, but sometimes it might not happen that you will remember the formula. Now you remember the formula because you have just studied it, right? So either you have to revise or you have to go by basics. So we have covered the whole performance of transmission lines comprehensively, right? Every single thing. I've derived everything. I've told you what points are important, what you should keep in mind. I've solved the questions as well. I've tried to solve with basics as well. In the next lecture, we'll move on to the parameters of transmission lines. Thank you, and I will see you in the next lecture. Until then, happy learning.